Welcome to Learn Kubernetes from a DevOps Guru, where you will learn the ins and outs of the exciting container orchestration technology, Kubernetes. I've focused on building production global scale technology systems and leading and mentoring the technical teams that make them a reality. I've worked through the evolution of production systems from client-server technologies to virtualization to containerization and now to container orchestration. That's why I'm excited for you to discover the ease with which Kubernetes lets you create performant, scalable, reliable, and robust applications in this course. Using Kubernetes on your laptop all the way up to large production, high availability systems in the world's largest public cloud. We'll examine the ins and outs of actual deployments on real clusters. And you'll gain experience and wisdom that can only come from doing it in real life. I'll be with you every step of the way to point out pitfalls, gotchas, and other things you can only get from experience. I'm excited to be a part of the next step in your DevOps journey as we explore Kubernetes together.
Technically, Docker is one implementation of the container-based virtualization technologies. Let's take a look at how virtualization technology has evolved over time. In the pre-virtualization days, we're using big server racks. Underneath, we have the physical server. We install the desired operating system on it. Then we run the application on top of the operating system. And each physical machine would only run one application. So what was the problem with this model? First of all, we have to purchase a physical machine in order to deploy each application. And those commercial servers can be very expensive. And we might end up only using a fraction of the CPU or a memory of the machine. The rest of the resources are simply wasted, but you have to pay for the whole hardware upfront. Secondly, deployment time is often slow. The process of purchasing and configuring new physical servers can take ages, especially for big organizations. Thirdly, it will be painful to migrate our applications to servers from different vendor. Let's say we install our application on an IBM server. It would take us lots of effort to migrate to Dell servers. A significant amount of configuration change and manual intervention is required. The rescue is the hypervisor-based virtualization technology. Let's take a look at this virtualization model. Underneath, we have the physical server. Then we install the desired operating system. On top of the operating system, a hypervisor layer is introduced which allows us to install multiple virtual machines on a single physical machine. Each VM can have a different operating system. For example, we can have Ubuntu installed on one VM and Debian on another. In this way, we can run multiple operating systems on a single physical machine, and each operating system can run a different application. This is the traditional model of virtualization, which is being referenced as the hypervisor-based virtualization. Some of the popular hypervisor providers are VMware and VirtualBox. In the early stage, users would deploy VMs on their own physical servers. But nowadays, more and more companies have been shifted to deploy VMs in the cloud with providers such as AWS and Microsoft Azure, which means we don't even have to purchase physical machines upfront. There are some huge benefits with this model. First of all, it is more cost-effective. Each physical machine is divided into multiple VMs, and each one only uses its own CPU, memory, and storage resources. We pay only for the compute power, storage, and other resources you use, with no upfront commitments, which is a typical pay-as-you-go model. Secondly, it's easy to scale. With VMs deployed in the cloud environment, if we wanted more instances of our application, we don't need to go through the long process of ordering and configuring new physical servers. We can simply click the mouse and deploy more VMs in the cloud. The time taken to scale our application can be reduced from weeks to just minutes. This results in a dramatic increase in agility for the organization. This hypervisor-based virtualization model has obvious advantage over the one application on one server model, but it still has some limitations. First of all, each virtual machine still needs to have an operating system installed. This is an entire guest operating system with its own memory management, device drivers, daemons, etc. When we're talking about a Linux operating system, we're talking about a kernel. For example, here we have 3 host operating systems and 3 kernels. Even though they can be 3 different kernels, we're still replicating a lot of the core functionality of Linux. In this traditional hypervisor-based virtualization model, we have to have an entire operating system there simply to run our application, which is still not inefficient. Secondly, application probability is not guaranteed. Even though some progress has been achieved in getting virtual machines to run across different types of hypervisors, there is still a lot of work to be done there. VM portability is still at an early stage. Finally, the container-based virtualization technology comes out. Docker is one implementation of the container-based virtualization technologies. Let's take a look at the diagram here. Underneath, we have our server, and this can be either a physical machine or a virtual machine. Then we install our operating system on the server. On top of the OS, we install a container engine, which allows us to run multiple guest instances. Each guest instance is called a container. Within each container, we install the application and all the libraries that application depends on. The key to understand the difference between the hypervisor-based virtualization model and the container-based virtualization model is the replication of the kernels. In the traditional model, each application is running in its own copy of the kernel, and the virtualization happens at the hardware level. In the new model, we have only one kernel, which will supply different binaries and runtime to the applications running in isolated containers. So the container will share the base runtime kernel, which is the container engine. For the new model, the virtualization happens at the operating system level. Containers share the host's OS, so this is much more efficient and lightweighted. You might want to ask, what do we gain by running those applications in different containers? Why can't we just run all applications in a single VM? This comes through the nature of isolation. As you know, most applications depend on various third-party libraries. Let's say we want to run 2 Java replications with 2 different JREs. This is going to be quite challenging if you want to run those 2 applications in the same VM without introducing any conflicts. By leveraging containers, we can easily isolate the 2 runtime environments. Let's say application A requires JRE 8. Then we just install JRE 8 in the first container and run application A in the first container. For container B, it requires JRE 7. Then we just install JRE 7 only for second container and run application B inside the second container. In this way, we have 2 containers on the same machine running 2 different applications, each with a different JRE version. This is what we call runtime isolation. Comparing to hypervisor-based virtualization, container-based virtualization has some obvious benefits. Firstly, it's more cost-effective. Container-based virtualization does not create an entire virtual operating system. Instead, only the required components are packed up inside the container with the application. Containers consume less CPU, RAM, and storage space than VMs. That means we can have more containers running on one physical machine than VMs. Secondly, faster deployment speed. Containers house the minimal requirements for running the application, which can speed up as fast as a process. A container can be several times faster to boost than a VM. Thirdly, great portability. Because containers are essentially independent self-sufficient application bundles, they can be run across machines without compatibility issues. That's it for this lecture. I'll see you later. Let's talk a little bit about Docker's client and server architecture. Docker uses a client-server architecture with the daemon being the server. The user does not directly interact with the daemon, but instead through the Docker client. The Docker client is the primary user interface to Docker. It accepts commands from the user and communicates back and forth with the Docker daemon. There are two types of Docker clients: the typical command line client and Kidmatic, which is a Docker client with graphical interface. So if you don't like working with commands, Kidmatic is something you should check out. The daemon is the persistent process which does the heavy lifting of building, running, and distributing your Docker containers. Docker daemon is often referred as Docker engine or Docker server. On a typical Linux installation, the Docker client, the Docker daemon, and any containers run on the same host. You can also connect a Docker client to a remote Docker daemon. We will cover more about this later. But you can't run Docker natively in OS X or Windows, because Docker daemon uses Linux-specific kernel features. So on OS X or Windows installation, the Docker daemon is running inside a Docker machine. The Docker machine is a lightweight Linux VM made specially to run the Docker daemon on OS X or Windows. Let's get started on installing Docker on our local machine. This lecture applies to you if you're using Linux or you are using Mac and your Mac version is OS X 10.10.3 or newer, or you're using Windows and your Windows version is Windows 10 or newer. Otherwise, you can skip this lecture and follow the instruction of the next lecture to install Docker Toolbox on your local machine. Here we Google Docker install. The first entry is Docker's official installation page. Just click the link to enter the installation page. The steps required to install Docker vary depending on the operating system you use. If you're using Linux, you can just follow the corresponding installation instruction on this page to install Docker on your operating system. Since Docker is a technology built around Linux containers, people developing on non-Linux platforms would need to use some forms of virtualization to run Docker. If you're running Windows, just scroll down and click the Windows installation link. As you see, there are two options for installing Docker on Windows: Docker for Windows and Docker Toolbox. Now, if you have Windows 10 or a newer version installed, you will be able to install Docker for Windows. Docker for Windows runs as a native Windows application, and it has a built-in virtual machine inside the app, which saves you tons of efforts from managing the VM by yourself. Docker for Windows is the desired way to run Docker on Windows machine, as long as you meet minimum requirement. You can just click the Getting Started with Docker for Windows link to start the installation. Since I'm using Mac, I'll be demoing how to install Docker for Mac on my Mac machine. But the steps should be very similar between Windows and Mac. Here, I scroll down and click the Mac installation page. Similar to Windows, you also have two options here. You can either install Docker for Mac or Docker Toolbox. If your Mac is 2010 or a newer model, and the Mac version is OS X 10.10.3 Yosemite or newer, it is recommended to install Docker for Mac, which runs as a native Mac application. I'm running a relatively newer version of Mac. Here, I just click Getting Started with Docker for Mac. Let's download the stable version. As you see, it is downloaded the installer. I'm fast forwarding the video until the download is complete. Now the installer is downloaded. Let's click it. Then drag the whale to the Applications folder. Just type your password to proceed. Then open the Applications folder and double-click the whale icon. Click Next. Now installer is asking for privileged access, as it needs to install its network components. Just click OK and type password to proceed. Docker has been installed on my local box. As you see, we have a wheel icon on the menu bar on top of our desktop. This initialization phase might take a while to complete. I'm fast forwarding the video until it's finished. This is what you would see if everything goes well. Now Docker is starting. Finally, we got Docker up running. Let's open a command line terminal. Then type docker info. Docker info would display the system-wide information about Docker. As you see, Docker is running inside a Linux virtual machine. You can also configure your Docker preference by clicking the wheel on the top menu bar, then select Preferences. Now we're under the General tab. Docker for Mac is set to automatically start when you log in. We'll leave this option checked so that we can have Docker automatically start when we log in into our desktop. You can also configure the number of CPU processors. You can increase processing power for the app by setting this to a higher number, or lower it to have Docker for Mac use fewer computing resources. By default, Docker for Mac is set to use 2 GB runtime memory, allocated from the total available memory on your Mac. You can increase the RAM on the app to get faster performance by setting this number higher. That's it for this lecture. I hope you've enjoyed it. In this lecture, we'll see how to install Docker Toolbox on your local box. This lecture applies to you if you're using Mac and your Mac version is older than OS 10, 10.10.3, or you're using Windows and your Windows version is older than Windows 10, or you want to install Docker Compose, Docker Machine, or Kitematic instead of Docker Engine. Otherwise, you can skip this lecture and follow the installation guide of the previous lecture. Here, we Google Docker install. The first entry is Docker's official installation page. Just click the link to enter the installation page. The steps required to install Docker vary depending on the operating system you use. If you're using Linux, you can just follow the corresponding installation instruction on this page to install Docker on your operating system. Since Docker is a technology built around Linux containers, people developing on non-Linux platforms will need to use some forms of virtualization to run Docker. If you're using Windows, just scroll down and click the Windows installation link. Then click Docker Toolbox. Then you can click Get Docker Toolbox to download Docker Toolbox installer for Windows. Since I'm using Mac, I'll be demoing how to install Docker Toolbox on my Mac machine. But the installation steps should be very similar between Windows and Mac. Here, we click the Mac OS X link to go to the installation guide for Mac. Then click Docker Toolbox. As you see, we'll be installing Docker Toolbox, which will install all the components you need to run Docker on Mac OS. Just be aware that you need OS X 10.8 Mountain Lion or newer version to install Docker Toolbox. Here, we click Get Docker Toolbox link. Then download the installer for Mac. The download is going to take a while. I'm fast forwarding the video until the download is complete. Now the installer has been downloaded. Docker Toolbox includes a minimum boot to Docker virtual machine, which will run inside VirtualBox. If you have VirtualBox running, make sure to shut it down before running the installer to avoid conflict. Let's double-click the icon to run the installer and accept all the default. The installer is going to install Docker Client, Docker Machine, Docker Compose, Kitematic, and Quick Start Terminal app. Docker Machine is a tool that lets you install Docker Engine on virtual hosts and manage the hosts with Docker Machine commands. Docker Compose is a tool for defining and running multi-container Docker applications. Kitematic is graphical Docker client. If you don't know what they are, don't worry. We'll talk about them in more details later. Type in the password to proceed. Now the installation is complete. Here we choose to start with the Docker Quick Start terminal. Now it is provisioning the Docker machine. The first time you run it, it would take a while. We'll just fast forward the video while the machine boots up. This is what it looks like if everything works successfully. This terminal is effectively a Docker client which takes the user input and send them to the Docker daemon. Here we can run Docker Machine ls command, which will last all the Docker virtual machines. As you see, We have our default Docker machines up. The Docker daemon is running inside the Docker machine. If you run Docker version command, it will print the version for both client and Docker server. Docker server refers to the Docker daemon. Here, if you launch the VirtualBox, you'll find out the installer has installed and configured a boot Docker VM, and the Docker daemon is running inside the VM. Before we finish this lecture, let me show you how to run Docker next time. Once you have the Docker toolbox installed, you can access Docker anytime by opening the Docker Quick Start terminal again. See? We get back our Docker client. In this lecture, we'll learn how to create and run our first container. We're going to create a container from an image. The image we're going to use here is called BusyBox. Let's go check it out. Here, we're at Docker Hub website. Just search for BusyBox. Let's click the first one, which is the official BusyBox repository. We quickly scroll down the document. As you see, BusyBox is a tiny image, which is only about 1 megabyte. This is the main reason we choose BusyBox, because of its tiny size, so it would take little time to download. Let's check out the tags tab. BusyBox has various different tags. Here, we pick tag 1.24 to run our container. Let's close the browser and open the Docker Quick Start terminal. If you have installed Docker for Mac, Docker for Windows, or you are using Linux, you can just open up a normal terminal. When we use the image to create a container, Docker will first look through our local box to find the image. If Docker is able to find the image locally, it will use the local image to create the container. If Docker can't find the local copy of the image, it will download from remote registry. To find out what image you have in your local box, we can run the Docker images command. See, we don't have any images in my local box. Now let's start running our container. To run a container, we will use docker run command. Docker run command will create the container using the image we specify in the command line, and it will spin up the container and run it. As we talked about in the previous lecture, an image is specified by the repository name and tag. We need to put a column between the repository name and the tag. So let's use BusyBox image with tag 1.24. After that, we need to specify what command we would like to run in that container and pass the argument for that command. The command we're going to run is echo, and let's put the argument hello world. So the Docker should output hello world after spinning up the container. Then hit enter. As you see, Docker goes ahead and downloads the image from the remote repository. That is because we don't have BusyBox 1.24 on our local box. After Docker downloads the image, it will create the container from the image and run the container. See? Docker outputs hello world, which is what we expected. Now, if we run Docker images command again, as you see, we have one image, which is the one we just downloaded, BusyBox 1.24, and the image has a unique ID. When we run the container again, Docker will use local copy of the image to create and run the container. Let's see it in action. Notice how faster the execution is. It prints out hello world right away. This is because we already have the BusyBox 1.24 image in our local box. So Docker just creates the container from the local image right away, without the need to download the image from remote registry. Let's see another example. Let's say we want to display all the contents in the root directory of the container. Just do docker run BusyBox 1.24, then ls command /. There you go! Docker outputs all the contents under the root directory of container. We can also run container in an interactive mode so that we can go inside the container. we need another two options, -i and -t. The -i flag will start an interactive container. The -t flag will create a presto tty that attaches standard input and output. Let's see this in action. Here we do docker run -i-d. We'll keep using BusyBox 1.24 again as the image. Now we hit enter. There you go. It gets me right inside the container. We can run ls command. See? It gives us all the contents in root level. Let's say we want to create a new file here called a .txt. After that, we do ls again. We can see the file is created. Now we can type exit to exit the container. Note that once we exit the container, Docker also shuts down the container. If I run the same container using the exact same container run command, Docker will spin up a container. But this time, Docker starts a brand new container. So if I go check out the file I created previously by running ls command, you can see it is not there. As you see, when we run docker run command, it spins up a new container. The container we created previously with a text file has been shut down. There are several important concepts we must understand before we start playing with Docker. The first two concepts are containers and images. Images are read-only template used to create containers. Images are created with a Docker build command, either by us or by other Docker users. Because images can become quite large, images are designed to be composed of layers of other images, allowing a minimal amount of data to be sent when transferring images over the network. Images are stored in a Docker registry, such as Docker Hub. We'll talk about it in a minute. Next, we'll talk about containers. To use a programming metaphor, if an image is a class, then a container is an instance of a class, a runtime object. Containers are hopefully why you're using Docker. They're lightweight and portable encapsulations of an environment in which to run applications. We create a container from an image and then run the container. And inside that container, we have all the binaries and dependencies we need to run our application. Here are another two important concepts about Docker: registry and repositories. A registry is where we store our images. You can host your own registry, and you can use Docker's public registry, which is called Docker Hub. Inside a registry, images are stored in repositories. Docker repository is a collection of different Docker images with the same name that have different tags. Each tag usually represents a different version of the image. Let's take a look at the Docker Hub. Docker Hub is a public registry which contains a large number of images you can use. Here we Google Docker Hub. The second entry is what we are looking for. Just click the link. Here we click Browse to see what we can find. As we see, there are some popular official repositories listed here, such as Nginx, Ubuntu, and Redis. Official repositories are certified repositories by Docker. For each repository, we can also see the number of stars and pulls, which indicate the popularity of each repository. You can also search other repositories here. Let's say we want to find some MySQL images. Let's type MySQL and hit enter to search. See? So Docker Hub found some MySQL repositories here. Note the first one is marked as official. New Docker users are encouraged to use the official repositories in their projects. These repositories have clear documentation, promote best practices, and are designed for the most common use cases. Docker Incorporation, which is the company behind Docker, sponsors a dedicated team that is responsible for reviewing and publishing all official repositories content. It is also ensured that security updates are applied in a timely manner for official images. So when we get started with Docker, try to use official images so that we can get the most support from the community. All the other repositories are also MySQL repositories, which presumably contains MySQL images. They are contributed by other users in the community. So how can we tell which one is an official image and which is not? First of all, as we mentioned before, official images usually come with an official mark. Also, the name of an unofficial image usually has a namespace before the actual image name, which is often the username of the user who created the repository. Here, let's click the link of the official MySQL repository. We can see the information about this REPL and clear documents about how to use this image. If I scroll up and click the Tags tab, we can see the repository has several tags. In most of the cases, the tag means the version of the application or tool in this image. So an image is specified by its repository name and tag. Even the same image might have multiple tags. If you don't specify a tag, Docker will use the default tag, which is latest. We'll get into more details about this when we start playing Docker run command in the next lecture. Hello, and welcome back. In this lecture, we're going to deep dive into Docker containers. We'll learn how to run containers in detached mode, how to specify Docker container name, and how to use Docker PS and Docker inspect commands. In the previous lecture, we have seen how to run containers in the foreground. But in most cases, containers are actually running in the background. We can start a Docker container in detached mode with a -d option, so the container starts up and runs in background. That means we can start up the container and could use the console after startup for other commands. Let's see this in action. We'll keep using our BusyBox image. In order to keep the container running at the background, we can run the Linux sleep command to suspend execution for a while. Let's do docker run -d busybox 1.24 sleep 1000. Then hit enter. See? Docker returns us the long container ID. Now the Docker container should be running at the background. But how can we verify that? We can find out all the running Docker containers in our local box by using Docker PS command. See? The container we just started up is currently running. As you see, the Docker PS command displays some container information such as container ID, image name, and the command we run. The container ID displayed here is the short container ID, which is the prefix of the long container ID. What if we want to display all the containers in the local box, including ones which have stopped? We can add the -a option at the end of the Docker PS command. See? Docker also shows all the containers that I have previously run. If we do not intend to keep the container, we can add rm option in the end, so the Docker would automatically remove the container when the container exits. Here we do docker run --rm busybox 1.24. Let's sleep for 1 second, then hit enter. The container runs for 1 second, then exits. Here we run docker ps-a to list all the containers. As you see, we don't see the sleep1 Docker container we just run because it has been removed by Docker as soon as it existed. Here is another useful option. We can also specify the name of the Docker container we want to run. Here we type docker run --name. Hello world. BusyBox 1.24. Now, let's run docker ps-a to list all the containers. As you see, The new container is named as Hello World. If we don't specify the container name, Docker will automatically generate a container name when we run docker run command. As you can see here, we get some funny name here, such as Boring Rosaline, Matt Lemire, and Kick-Ass Hopper. Before we finish this lecture, let me show you another handy Docker command. Docker inspect. Docker inspect will display low-level information on a container or image. Let's see this in action. Let's start up a new container in the detached mode. Docker returns us the container ID. Then let's run container inspect. Copy and paste the container ID and hit enter. See? Docker inspect renders the results in a JSON array. It displays the IP address and MAC address of this container. Let's scroll up. As you see, Docker inspect also outputs some useful low-level information, such as the image ID and log path. I hope you've enjoyed this lecture. I'll see you later. In this lecture, we'll talk about Docker port mapping and Docker log command. We'll be using a new Docker image, the Tomcat image. Tomcat is an open source web server that executes Java servlets. Let's check it out. Here we're at the Docker Hub page. We search Tomcat and enter the official Tomcat image page. Let's scroll down. As you see, Tomcat page by default runs on port 8080. We can expose a port inside the container and map the port to another port on the host by -p option. In this way, the Tomcat web server can be accessed by using the host URL and the mapped port. If you're running Docker on Linux, the host here refers to localhost. If you're running Docker on Windows or Mac with Docker machine, the host here refers to the Linux virtual machine running Docker. The format for -p option is -p host port, container port. Let's see this in action. Here, we open up the Docker Quick Start terminal. Just make the font size larger as before. Let's do docker run -it -p8888 column 8080 to expose the container port 8080 to host port 8888. Then Tomcat 80 and hit enter. Tomcat image is about 300 megabyte large, so it takes quite a while to download. It is recommended to run this Docker command when you have good internet connection. I'll fast forward the video until the download is done. Now the image is downloaded and the container is up running. We can access Tomcat server through web browser. First, we'll scroll up to find out Docker machine IP. Just copy it. If you're running Docker on Linux, or you're running Docker for Mac or Docker for Windows, the host IP is just localhost. Then we open our browser, paste the host IP, and go to port number 8888. See, we have opened the Tomcat console page. In most cases, especially in production, we would run containers in the background. Previously, we have learned -d will allow us to run containers in detached mode. Let's try it out here. Then we check the container status by running docker ps-a. As you see, our previous Tomcat container has existed. Let's go back our previous container run command and add -d option. Hit enter. See, Docker returns us the long container ID, and the container should be running at the background. We can check out the logs of running container by docker logs command. Just type docker log and the container ID. Oops, it should be docker logs, not docker log. Let's redo it again. See, we're seeing the container logs. In this lecture, we're going to talk about Docker image layers. A Docker image is made up of a list of read-only layers that represent file system differences. Image layers are stacked on top of each other to form a base for the container's file system. Take a look at this diagram here. Each image consists of multiple layers, and each layer is just another image. The image below is referred to as the parent image. We call the image at the very bottom as the base image. Docker is pulling the images layer by layer. You can also check the full set of layers that make up an image by running the Docker history command. As you see, BusyBox image consists of two layers. The base layer is to add a file, and the second layer is to run bash. When we create a new container, you add a new, thin, writable layer on top of the underlying stack. This layer is often called the writable container layer. All changes made to the running container, such as writing new files, modifying existing files, and deleting files, are written to this thin writable container layer. The major difference between a container and an image is the top writable layer. All writes to the container that add new or modify existing data are stored in this writable layer. When the container is deleted, the writable layer is also deleted. The underlying image remains unchanged. Because each container has its own thin writable container layer, and all changes are stored in this container layer. This means that multiple containers can share access to the same underlying image, and yet have their own data state. The diagram shows multiple containers sharing the same Ubuntu 15.04 image. In this lecture, we'll take a look at the second approach to build a Docker image using Dockerfile. A Dockerfile is a text document that contains all the instructions users provide to assemble an image. What is an instruction? It can be, for example, installing a program, adding some source code, or specifying the command to run after the container starts up, and so on. Docker can build images automatically by reading instructions from a Docker file. Each instruction will create a new image layer to the image. Basically, instructions specify what to do when building the image. Let's go ahead and create a Docker file. A Docker file must not have any extension. It must be named as Dockerfile with capital D. The Docker file gets created. Let's open it up. We add our first instruction, from instruction. Docker runs the instruction in a Docker file in order. The first instruction must be from to specify the base image from which you are building. Here, we just use Debian Jesse as our base image. So Debian Jesse is the argument for the from instruction. The instruction is not case sensitive. However, convention is for them to be uppercase in order to distinguish them from arguments more easily. Let's move to the next instruction, run instruction. Run instruction will specify a command to execute. It can be any commands you can run in a Linux terminal. Here, we do apt-get update first. Then we install git. Make sure we put -y option, because we won't be able to answer the prompt. Next, let's install vim as well. Now we have our Docker file ready. Just save the file. It is time for us to start building the Docker image. We have a new command to learn, docker build. Docker build will build the image using instructions given in the Docker file. Here we type docker build. Docker build takes a -t option to tag the new image we're building. As I did in the previous lecture, I'll tag the image with my own repository name, jameslee/debian. Docker build command also requires a path, which is the path to the build context. The path specifies where to find the files for the context of the build on the Docker daemon. For example, if we would like to copy some source code from local disk to the container, those files must exist in the build context path. Remember that daemon could be running on a remote machine, and that no parsing of the Docker file happens at the client side. When the build process gets started, Docker client would first pack all the files in the build context into a tarball, and then transfer the tarball file to the Docker daemon. What's more, by default, Docker will search for the Docker file in the root directory of the build context path. If your Docker file doesn't live in the build context path, no worries. You can tell Docker to search for a different file by providing a -f option. Here, my Docker file is at my current directory, so I can just use the current directory as the path. Now, we hit enter to start the build process. Let's go through the build output to get a better understanding about how Docker is building the image. First, it outputs sending the build context to Docker daemon. As we mentioned before, now the Docker client is transferring all the files inside the build context, which is my current folder from the local machine to the Docker daemon. Step 1. From Debian Jesse. That is the from instruction. As you can see, Docker is going through the instructions in the Docker file. Then step 2. Run apt-get update. Docker is executing the run instruction. It says running in, followed by a container ID. What happens is that Docker starts a new container from the base Debian image and is executing the apt-get command in the container. Now, when step 2 is about to finish, it prints out removing intermediate container and followed by a container ID. You might have already noticed the two container IDs are exactly the same. So Docker spins up a new container and afterwards just removes it. Let me explain to you what is happening here. Docker daemon runs each instruction inside a container. A container is a writable process that will write file system change to an image. In our case, it installs a program. Once Docker has written changes to the image and committed that image, Docker removes the container. So, for instruction, Docker creates a new container, runs the instruction, commits a new layer to the image, and removes the container. Basically, containers are ephemeral. We just use container to write image layers, and once they're finished, we get rid of them. Images are persistent and read-only. Let's continue digging through the output. Now it says step 3. apt-get install -y git and followed by a container ID. What happens is that at the end of step 2, Docker committed our container as a new image. And it starts a new container from that image for the next instruction. Now it is installing Git. When step 3 is about to finish, it is repeating the same process to commit the intermediate container as a new image and remove the container. Let's move to step 4. It says run apt-get install -y vm, and Docker is executing the command in a new container from the image it committed in the previous instruction. Once all the steps are finished, the build completes successfully. Let's run Docker images to make sure the new image is created successfully. As we can see, the image we just built is tagged with latest because we don't specify a tag when we run the Docker build command. The new image we created is about 250 megabytes. The base Debian image is only about 125 megabytes. The new image almost doubled the size of the base image. So the extra layers we added by installing Git and Vim are about 125 megabytes. That's all for this lecture. I'll see you later. In this lecture, we'll learn how to build Docker images. There are two ways to build a Docker image. We can either commit our change made in a container to make a new Docker image, or we can write a Docker file to build an image. In this lecture, we'll start looking at the first approach. Here is what we'll do in the lecture. Firstly, we'll spin up a container from a base image. Secondly, we'll install git package in the container. Finally, use docker commit command to commit changes made in the container to build a new image. Let's see this in action.
This time, we'll be using Debian Image, which is one of the most popular Linux distributions. Here, we're at the Docker Hub website. Search for Debian.
Let's pick tag Jesse.
As you see, Debian is also a relatively small image, which is about 125 megabytes and consists of 2 layers.
Open up our terminal
And type docker run-it debian jesse.
Since Docker can find the image locally, it is pulling from Docker Hub. I'm fast forwarding the video until the download is done. Now the image has been downloaded and we're right inside the shell of the container. We can do ls command to show the root directory structure of the container.
As you see, it is typical Debian file system.
What if we want to use git command here? Just type git. Oops, looks like git is not installed in this container. Let's install it by using the apt-get package management tool. Here we do apt-get update and apt-get install -y git. We put -y here so it would automatically confirm yes to prompts. Now, as you see, it is installing Git. I'll fast forward the video until it is done. Now it has installed the Git package. Let's verify Git has installed correctly. First, we clear the screen and type git again. See? Git shows me the help message. What I will do now is that I'll exit the shell and we're going to commit our container as a new Docker image. We have a new command to learn. That is docker commit. What docker commit command does is to save the changes we made to the container's file system into a new image. When running this command, we specify the ID of the container we're committing and the repository and tag of the new image. Let me show you in a second. Here we do docker ps-a to get the ID of the container we just run. Then we commit the container by running docker commit. Just copy and paste the container ID here. Next, we need to provide the repository name and image tag.
For the repository, I'll put my own Docker Hub repository name, which consists of my Docker Hub user ID, James Lee // and the official Debian repository name.
And we'll tag the image with 1.00. Then hit enter. Docker commits our changes to a new image and returns the long ID of the new image. If we do Docker images here,
We can see our new image, James Lee Debian.
and tagged with 1.00.
It's a little bit bigger than the official Debian image because I extended the file system.
We have learned previously, images are made of the file system layers.
The base layer of this new image is Debian.
And we have extended the base image with a new layer, so it takes a bit more size on disk. Here we can spin up a container based on this new image. Now we're in the shell of the new container. We can do ls command to show the file structure. Let's try the git command here. See? The git command has already been installed. the changes we have committed are persistent in the new image. I'll see you later. Hello and welcome back. In the previous lecture, we have seen how to write a Docker file to build an image. In this lecture, we'll learn a little bit more about the Docker file syntax and some best practice to write Docker files. First of all, we'll take a look at how to chain run instructions. One thing to keep in mind is that each run command will execute the command on the top writable layer of the container, and then commit the container as a new image. And that new image is used for the next step in the Docker file. So each run instruction will create a new image layer. It's recommended to chain the run instructions in Docker file to reduce the number of image layers it creates. I'll show you how to do this in a second. Here, we modify the Docker file. Instead of having 3 instructions, we'll do apt-get update and apt-get install git. And Vim to aggregate those 3 instructions into one. Let's save the Docker file and rebuild the image. As you see, we have only 2 build steps instead of 4, which means it is only adding 1 more layer on top of the base image instead of 3. Another good practice when writing the run instructions is to store multiple line arguments alphanumerically. This will help you avoid duplication of packages and make the list much easier to update. Let's say we want to install Python package as well. We need to put Python between Git and Vim so that they're sorted alphanumerically. Now, we'll move on to the CMD instruction. CMD instruction specifies what command you want to run when the container starts up.
If we don't specify CMD instruction in the Docker file, Docker will use the default command defined in the base image. In our case, it is Debian Jessie, and the default command is bash.
Unlike the run instruction, the CMD instruction doesn't run when building the image. It only runs when the container starts up. You can specify the command in either exec form, which is preferred, or in shell form. Let's see this in action. We modify the Docker file. Add CMD instruction after the run instruction. Here we echo hello world. Let's rebuild the image. The build completes successfully. Now let's start a container from this image. Just copy the image ID here. See, it prints hello world. We can also overwrite the CMD instruction at runtime. When you do Docker run, you can specify a different command to run.
Let's rerun the container from the image.
And overwrite the CMD instruction with echo hello Docker. See? This time it prints out hello Docker instead. The next topic we're going to talk about is Docker cache. You probably have already noticed, last Docker build is much faster than the first build. That is because Docker cache. Each time Docker executes an instruction, it builds a new image layer. The next time, if the instruction doesn't change, Docker knows the image layer already exists, rather than building it again. Docker will simply reuse the existing layer.
As you see, the last Docker build does not redo step 2. It just reuses the image built previously.
This helps to make our build much faster.
If you're building many containers, this can greatly reduce build time.
However, if Docker cache is used too aggressively, it may cause issues. For example, say you have a Docker file like this. After building the image, all layers are in the Docker cache. Suppose you later modify apt-get install by adding extra package curl. Docker sees the first and second instruction are not changed and reuses cache from previous steps. Because the apt-get update is not run,
You can potentially get an out-of-date version of Git and curl.
the solution is to chain the apt-get and apt-update command as a single instruction, so that whenever the apt-get command is modified, the whole instruction will rerun to ensure you get the latest version of the package. You can also tell Docker to invalidate cache by using the no cache flag when issuing the Docker build command. Next, let's talk about copy instruction. The copy instruction copies new files or directories from build context and adds them to the file system of the container. Let's see this in action. Here, we add abc.txt file in my current directory. Let's modify the Docker file. Remove the cmd instruction and add a copy instruction to copy the abc.txt file to the container. Then save the file. Just rebuild the image and run the container. Let's enter the source directory. See? We get our abc.txt file. There's another instruction which is very similar to copy. That is the add instruction. Those two instructions are quite similar. The difference is that add can do more magic. Add allows you to download a file from internet and copy to the container. Add also has the ability to automatically unpack compressed files. If the src argument is a local file in a recognized compression format, then it's unpacked at a specified test path in a container's file system. Generally speaking, copy is preferred. That's because it's more transparent than add. Copy only supports the basic copying of local files into the container. Copy is really just a stripped-down version of add. Ultimately, the rule is this: use copy, unless you're absolutely sure you need add. I hope you have enjoyed this lecture. I'll see you later. Hello, welcome back. Previously, we have learned how to build a Docker image, either by manually committing the changes we made in a container or by writing a Docker file. In this lecture, we'll see how to push our extended images to a Docker repository so that other developers can use that image, or we can pull that to our production environment and run it as a container. The easiest way to make your images available is to use the Docker Hub, which provides free repositories for public images. First, we need to create a Docker Hub account. Let's go to Docker Hub, where you sign up for your account. Just type your Docker Hub ID, email address, and password. After you have signed up and you have logged into your account, it looks like this. I just created a Docker Hub account for this tutorial. JLead tutorial is the Docker Hub ID. In order to push the image to the right repository, we need to associate the image with the Docker Hub account. The way to link the image with the Docker Hub account is to rename the image to something like Docker Hub ID / repository name. The command to rename this image is docker tag. Let's see this in action. First, we issue Docker images command, which displays all the current images in my local box.
The image we're going to push is this extended Debian image.
Now let's rename this image. Just type docker tag, copy and paste the image ID.
then the repository name, jetutorial/Debian.
We also need to specify a tag for this image. If we leave it blank, Docker will just use the default latest tag. But try not to use latest tag unless you have to. Let me explain why. Docker will use latest as a default tag when no tag is provided. But beyond that, the latest tag has no special meaning. A lot of repositories use it to tag the most up-to-date stable image. However, this is still only a convention, and it's entirely not being enforced. Images which are tagged latest will not be updated automatically when a newer version of the image is pushed to the repository. If you're shipping Docker images to a production environment, you should just ignore the latest tag. Don't use it. Don't be tempted by it. It's easy to look at it and think that your deployment script should just pull latest. However, this is not enforced. It takes a lot of discipline to make that work. The safest way is just to versionary tags every time. Here, we just explicitly specify tag 1.01, then hit enter. Now let's do Docker images again. See, the image has been tagged with a new name. The first and the second image have the same image ID. Because they're the same image and have exactly the same content but tagged with different names. The next step is to push the image to Docker Hub. In order to do this, we need to issue the command docker logging. We'll need to type our Docker Hub account credentials. Now we're logged in. Finally, we can do docker push, followed by the repository name and tag. And hit enter. Now it is sending the image to Docker Hub. This is 250 megabyte image, which might take a while to push. I'm fast forwarding the video until the image has been pushed. This is what you will see if everything worked out successfully. Now, let's go back to our Docker Hub account and refresh the page. We can see the new image appears under my account. Now we can click the image and check the image details, such as image tag. And that's it for this lecture. I hope you've enjoyed it. Hello, and welcome back. In this lecture, we'll learn how to containerize a simple Hello World web application. The application is written with Python and Flask web framework. The reason we choose Flask is because it's lightweight web framework and very easy to get started. You can visit Flask website to learn more about it. Don't worry if you have never used Python or Flask before. In this lecture, we'll be focusing on how to work with Docker and how to Dockerize a simple web application. We won't get into technical details about Python or Flask. Also, all the dependencies are managed by Docker, so you don't have to install Python or Flask in your local box. It should be quite easy for you to follow along. I just created a GitHub account for this course and uploaded the source code of this web application to GitHub. You'll need to have Git installed in your local box to download the source code. In case you don't, just Google Git installation and follow the instruction to install Git. Or if you don't want to install Git, you can also download the source code from the supplementary material. I already have Git installed on my local box, so I just issue the git clone command here. You might have noticed that I'm using a -b option here. The reason being I'm using different tags for various stages of the code through this course. The source code for this lecture is tagged with v0.1. So after Git downloads the repository, it'll check out tag v0.1 as a new branch for you. Now hit enter to start calling the repository. Let's see what has been downloaded. The repository is named as Docker app. We enter the repository and clear up screen. Let's check what's inside the repository. There are only a Docker file and a directory in this repository. The Docker file is used to build the Docker container for this web app. The app folder is our application folder, which holds our Python code. Just enter the app folder. There is only one file here. This is one Python program which will initialize and start a Python server. Let's check out the code. I'll quickly go through the logic of this piece of code. The first two lines basically import Flask module, initialize Flask, and create the application object. The second part of the code registers a view function for a given URL/. When the given URL/ is requested, the hello world method would be called, which just returns hello world. The last piece of this code initializes and starts the Python Flask server. Just be aware that do not use this run method to start an application in a production. It is not intended to miss security and performance requirements for a production server. Instead, use UWSGI or CGI. You can Google Flask deployment options to find more information about it. In this lecture, we'll be sticking with this run method just for the sake of simplicity, as Flask is not the major focus of this course. But make sure you don't do this in production. Here, I'm using the application server at 0.0.0 instead of localhost or 127.0.0.1. This is needed if we want to have the server available externally, so that your app server can be accessed by other containers as well. Now, let's move on to take a look at the Docker file. First of all, it is the from instruction. We're using the Python 3.5 as a base image, which already has Python installed. Then we install Flask 0.11.1 using pip install, which is a Python package management tool. Next, we add a new user, admin. The MS option will create a default home directory for this admin user. And we're setting the default shell of this admin user to bash. The following user instruction ensures that we'll be running the app server under the admin user. In general, you should always set the user instruction in your Docker file to run your process as an unprivileged user within the containers. Otherwise, your process will be running as a root within the container. It is concerned that if an attacker breaks the container, he would have root access in the host machine because the UIDs are the same. In theory, a root user within a Docker container cannot escalate to be root on the host machine, but many people believe that it's possible to do so. As far as I know, it is certainly harder to do so with Docker containers because of the capacity restrictions enforced by Docker. But if security is a big concern, we should stack up multiple safety mechanisms. So as a good practice, we should use a non-privileged user to run the app server. The next instruction is workdir. This instruction sets the working directory for any run CMD. Enter point, copy, and add instructions that follow it in the Docker file. Here we are using /app as our working directory. Then we copy the app directory to the container. Finally, we run our Flask application. Because we have defined our working directory to be /app, so here I can just use the relative path of the app.py file. Now we're ready to build the container for our Flask application. Here we do docker build -t, name our Python app as Docker app, then tag it with v0.1. The build context is the current directory, because the Docker file sits here. Just hit enter to start the build. It might take a while for you to download the Python base image if you have never downloaded it before, because the base image is about 600 megabytes. This is how it looks like if everything goes well. Let's check out our Docker app image by running Docker images. See? The first entry is the image we just built. It's time to run our Docker app container. Here we do docker run -d to run the container in the background. Then -p to expose the port. By default, the Python Flash server will be running at port 5000 inside the container. Let's map port 5000 on the container to port 5000 on the host, so that we can access the Python container from our local box. Lastly, just copy and paste the image ID to run and hit enter. See, Docker builds the container, starts it up at the background, and returns us the container ID. Let's access our Python app server to see if it is up running. First, we need to find out which IP the Python server is running on. If you're using Linux, the Python server should be running at your local box. If you're using Mac or Windows, Python server is running on the Docker virtual machine. You can find out the IP of the Docker machine by running docker machine ls. See, it displays various information about the default Docker machine. Just copy the IP of the Docker machine. Then open the browser and copy the IP to the address bar.
If you're running Docker on Linux, or you're running Docker for Mac or Docker for Windows, you should put localhost here.
We have exposed the port 5000 on the host. So here we just type port 5000 and hit enter. There you go. We get hello world. Our app is up running. We can also log into our container. In order to do that, there is a new command to learn. Docker exec. Docker exec allows you to run a command in a running container. Let's run docker exec -it to run the command in interactive mode. Then we copy and paste the container ID. Lastly, we need to specify which command we would like to run inside the container. In this case, we run bash. Just hit enter. See? We're right inside the container and we're logged in as the admin user. As you can see, we're at the /app directory, which is the working directory we defined in the Docker file. We can also enter the home directory of the admin user. Here, if we do ps-exu, it displays all the running processes on this container. See, our Python application is running under the admin user, which is exactly what we defined in the Docker file. That's it for this lecture. I'll see you later. Hello and welcome back. In this lecture, we'll turn our Hello World application into a small key value lookup web app. We'll start with implementing this key value lookup web app as a single service. Then we will look into splitting this application into two small services and run them in two different containers. And we'll see how this naturally leads to a microservice approach. Let's take a quick look at what this simple key value lookup web app looks like. This is the front end of the application. Here we can put Arabic number 1 and English number 1 as a key value pair. Just click the Save button to save the pair. Let's save Arabic number and English number 2 as another key value pair. After the two key value pairs have been saved, we can then look up the value with a key. Let's type Arabic number 1 as the key and click load. See? The app returns English number 1, which we saved previously. We can also look up Arabic number 2 as well. Looks like a very simple app, right? Let's see how this app is implemented. I have already tagged the source code of this application as v0.2. You can just enter the Git repository you downloaded in the previous lecture and run git stash to stash any changes you made in your working directory so that we can have a clean working directory, and git checkout v0.2. Then just open up the repository. Here I'm using a Sublime text. You're free to use your favorite text editor. Let's expand the directory structure. As you see, we have added a new template file, index.html. This file defines the layout of the web page you saw at the beginning of this lecture. Now, I'll quickly walk you through the updated source code of this application so that you'll have a rough idea about how the system works. First, let's take a look at the index.html file. This file defines the skeleton of the web page you just saw. It defines two input text fields. The first one is linked with variable key. The second one is linked with variable cache value. Those two variables are both defined in the controller, which is the app.py file. It displays two submit buttons. One is to save the key value pair. The other one is to load the value with a key. Let's move on to take a look at this app.py file. Here, we are using a Python built-in data structure dictionary to store all the key value pairs in memory and initialize the dictionary with a single entry. The second part of this code registers a view function for the URL/ for both post and get HTTP methods. If we first load the web page, this is going to be a GET request to the server. If we click the Save or Load button, the browser will send a POST request to the server. By default, the view function only handles GET method. So we need to explicitly specify both POST and GET methods here, so that the view function can handle both cases. Here we assign the default value, which is Arabic number 1, to the variable key, so that if we first load the web page, the app will display a default key value pair. If the user specifies the key in the form, we then override the key variable. Next, if the user clicks the Save button, we'll go ahead and save the key value pair in our in-memory dictionary. Then we do a key value lookup in the dictionary to get the key value pair and pass it to the template to render the HTML page. Those are all the changes we made in this controller file. The Docker file says the same as before. Nothing is changed. Then what we do here is to rebuild the Docker image and retag it with v0.2. Now it's time to spin up the container. Just issue the docker run command to start up the container. Let's switch to browser and refresh the page. See? Our service is up running. So far, we have demoed how this simple app is implemented as a single service. In the second half of this lecture, we'll be looking into how we can split this app into two small services by introducing a Redis Docker image. Redis is an in-memory data structure store often used as database, cache, and message broker, and has built-in replication and different levels of on-disk persistence. It's widely used in lots of critical products in the field, such as Twitter timeline service and Facebook newsfeed. Let's see how we can integrate Redis into our key value lookup service. Since our application is written in Python, we'll need a Python Redis client so that our application can interact with the Redis server. You can find this Redis Python client web page by Googling Redis Python client. As you see, the Redis API is very simple. It has a GET API to look up the value with a key and a SET API to save the key value pair into Redis. So let's start with updating the app.py file to use the Redis service. First, we need to import the Redis client module. Then we can just copy the Redis client initialization code from the Redis Python client web page. This would construct a Redis client object for us. Note that this host parameter here specifies the hostname of the Redis server, which the Redis client would connect to, because we'll be running the Redis server in a separate container. Here, we just put the container name Redis here. Later, I would show you how we can link the Redis container with our Python server container. Let's put the same initial value into the Redis service. We also need to replace the Python dictionary code with the Redis API. Just update the code about saving the key value pair with Redis set API. and also update the get API here. By default, Redis would return us a byte string which has a character B prefix. We'll need to decode the byte string with UTF-8 decoder. Don't forget to update this Python dictionary lookup code with Redis API as well. We're done with updating this controller file. Let's continue to update the Docker file. Because we're using the Redis client in our Python code, so we need to ask Docker to install the Redis client package for us. Just type Redis and install the latest version, which is 2.10.5. Now, we're done with the code modification. We'll see how we can start up our Python apt container and the Redis container, and how we can link them together. I hope you have enjoyed this lecture. I'll see you later. Hello, welcome back. In the previous lecture, we have integrated Redis into our application. In this lecture, we'll learn how we link the Redis container and our Python app container, which will allow them to talk to each other without having to expose any network ports. This can be done using Docker container links. Container links allow containers to discover each other and securely transfer information about one container to another container. When you set up a link, you create a conduit between a source container and a recipient container. The recipient container can then access select data about the source container. In our case, the Redis container is the source container, and our app container is the recipient container. The links are established by using container names. Let's see this in action. First, let's run the Redis image in a container and give it a name Redis, which will be used to establish the container link. Here, we use the latest Redis image, which is 3.2.0. Now, Docker is downloading the Redis image. After the download is complete, we run docker ps to verify the Redis container is up running, and it's named Redis. Then, in the second step, we build our Python app image and tag it with v0.3. The build completes successfully. Now, it's time to run our Python application container, which is the recipient container. This time, we start the application container in almost the same way as we did before, except we add the double dash link option and specify link to the Redis container so that the app container can connect to the Redis container using the container name Redis. Do you remember in our app.py file, we have used the Redis container name as the host name? This is where the Docker container link's being used. Now we just hit enter to start up the container. The container starts immediately. Let's switch to browser and refresh the web page. See? The application is up running. Here we do some basic key value lookup to verify the app is functioning as expected. Great! Everything worked well. So far, we have demoed how to use Docker container links to get our app container working together with a Redis container. You might want to ask how container links work behind the scenes. I'll show you in a second. Let's log into the Python app container first. What I will do is that I'll open the etc hosts file. When a Linux machine gets started, it will need to know the mapping of some host names of the IP addresses before DNS can be referenced. This mapping is kept in the etc host file. What you see there is an entry created for our Redis container. Here is the Redis container name and the container ID. So hostname Redis will be resolved as the IP address on the left column. The IP is the IP address of the Redis container. Let's approve that. Just run docker inspect Redis container ID to inspect our Redis container. And grep IP. You see? The Redis container IP is 172.17.0.2. We can also verify that by pinging Redis inside the app container. Let's log on into the app container again and ping Redis. You see? It is directing the echo request to 172.17.0.2. Let's summarize here. The main use for Docker container links is when we build an application with a microservice architecture. We're able to run many independent components in different containers. Docker creates a secure tunnel between the containers that doesn't need to expose any ports externally on the container. You'll note when we started the Redis container, we did not use -p flag. That's a big benefit of linking. We don't need to expose the source container, here the Redis container, to the external network. That's it for this lecture. I'll see you later. Hello, and welcome back. In this lecture, we'll learn how to automate our current Docker workflow with Docker Compose. Currently, we have to start up the Redis container first, and then start up the app container and link it to the Redis container. This manual approach works well for small applications, but it would get rather impractical when the number of containers and the number of container links grow. What if our application have more than 20 components and they're all running inside containers? It would become very complicated to start and link all the containers. Here is where Docker Compose comes in handy. Docker Compose is a tool for defining and running multiple container Docker applications. So with Docker Compose, we can define all the containers in a single file called Docker Compose YAML file. We can run a single command to start up all the containers. Here is what the Docker Compose YAML file looks like. You can find this web page by Googling Docker Compose. If you installed Docker using the Docker toolbox, you should already have Docker Compose installed. If not, you can always follow the installation guide at this Docker Compose web page to install Docker Compose. You can verify if Docker Compose is already installed by running Docker Compose version command. See, it displays the current Docker Compose version. Now, it is time to write the Docker Compose YAML file for our application. Just create a docker-compose.yml file. There are two versions of the Compose file format. Version 1, which is the legacy format, which does not support volumes or networks, and version 2, which is the most up-to-date format and is the recommended format. To specify version 2, we just put a version column 2 entry at the root of the YAML. In this file, we define the services that make up our application. For each service, we provide instructions about how to build and run the container. In our application, we have two services, Docker App and RAIDs. First of all, let's work on the Docker App service. The first instruction we'll write is the build instruction, followed by column and dot. The build instruction defines the path to the Docker file which will be used to build the Docker App image. Because our Docker App Docker file is sitting in the same directory as this Docker Compose YAML file. Here we put dot, which means the current directory. The second instruction we'll write is the port instruction, which defines which ports on the container to expose to the external network. The port instruction is analogous to the -p argument of the Docker run command. Mapping ports are defined in host port column container port format. Here we just type port 5000 column port 5000 to expose container port 5000 to host port 5000. The next instruction is the volume instruction. A volume is a designated directory in a container, which is designated to persist data independent of the container's lifecycle. A typical use of volume is to share data between container and host machine. Volume instruction is defined in host directory, column, container directory format. Here, we bind mounting the app directory in the host machine to the app directory in the container. In this way, we can share the source code on the host machine with the container, so that we don't have to use the copy instruction to copy the source code from the host to the container in the Docker file anymore. And this allows us to make changes to the source code from the host machine and see the effect right away without rebuilding the image. Now, we're done with the Docker app service. Let's move on to the Redis service. The only instruction we need is the image instruction. The image instruction defines which image to run a container from. In this case, we use Redis image 3.2.0. As you see, we can either run a container from an existing image, or we can build an image from a Docker file. All service would either need an image or build instruction. We're done with writing Docker Compose file.
You might want to ask why we don't need to define the linking between Docker app service and Redis.
This is because the version 2 Docker Compose format supports Docker network feature, which allows containers to be discovered by its name automatically. And any service can reach any other service at its service's name, so linking is not required anymore. However, if you're using the version 1 Docker Compose supports, you do need to add container linking here. Before starting up our containers, we can remove the copy instruction from the Docker file, because we already have defined the volume instruction in the Docker Compose file to share the app folder between the container and the host. Now it's time to run our application. To run the app, we simply use the command docker compose up. The up command will build the images for all services defined in the YAML file. Create and start all the containers. We can run docker ps to verify the Docker app container and the Redis container are up running. Let's summarize. We have demonstrated how to automate our Docker workflow with Docker Compose command. Docker Compose is a very handy tool to quickly get Docker environment up and running. It uses YAML files to store the configuration of all the containers, which removes the burden to maintain our scripts for Docker orchestration, such as starting, linking, and stopping our containers. In the next lecture, we'll learn more about Docker Compose workflow. That's it for this lecture. I'll see you later.
Hello and welcome back. In this lecture, we're going to learn more about Docker Compose workflow. In case you didn't follow the instruction in the previous lecture to write the Docker Compose file, I've uploaded the source code to GitHub. You can get the source code by running git stash and git checkout v0.4. In this lecture, I'll demonstrate how a typical Docker Compose workflow looks like. Here I'm at the directory where the Docker Compose file lives. Usually, a typical Docker Compose workflow starts with the Docker Compose up command to start the application, often followed by a -d option to run the Docker Compose command in the background. After all the containers start up, we can run Docker Compose ps to check the status of the containers managed by Compose. As you see, both two containers are up running. Another useful Docker Compose command is Docker Compose logs, which will output colored and aggregated logs for the Compose managed containers. You can also add a -f option to follow log output
It would output appended log when the log grows. Docker also allows you to output the logs of a specific container by appending the container name in the end. When we're done with the application, we can issue Docker compose stop command to stop all the running containers without removing them. The same containers can be restarted if we run docker compose up or docker compose start command. Or if you want to completely remove all the containers, you can do docker compose rm. Now Docker is asking if you really want to remove those containers. Just type Y and hit enter to confirm. Now the containers are deleted. Now if we do docker compose ps again, see? All the containers are gone. A typical Docker compose workflow usually invokes making changes to the source code or images and rebuilding the containers afterwards. Let's just open up the Docker file and change the username to James. Now the question becomes, how can we let Docker rebuild the image? By default, Docker compose up will only rebuild the image if the image doesn't exist. Let's prove that. Just run docker compose up again to start up all the containers. Run docker ps to verify all the containers are up. We log into the Docker app container. Now we're inside the container, but as you see, we logged in as admin, not James. So our change doesn't take effective. This is because Docker compose up doesn't rebuild the image because Docker found out the image exists. You might want to ask, how can we force Docker to rebuild the image? We need to use the docker compose build command, which will rebuild any images created from the Docker files. Let's give a try. See? Docker rebuilt the image and printed out all the instructions. Now let's rerun docker compose up. This time, Docker recreates the Docker app container because it found a new image. Let's do docker ps. We can see the Docker app container is newly created. If we log into the Docker app containers again, now we logged in as James. So the takeaway here is to use docker compose build whenever you need to update an image. I have demoed a lot of docker compose commands in this lecture. Let's review what we have learned about docker compose workflow so far. Docker compose up starts up all the containers. Docker compose ps checks the status of the containers managed by docker compose. Docker compose logs outputs colored and aggregated logs for the compose managed containers. Docker compose logs with -f option outputs appended log when the log grows. Docker compose logs with the container name in the end outputs the logs of a specific container. Docker compose stop stops all the running containers without removing them. Docker compose rm removes all the containers. Docker compose build rebuilds all the images. That's it for this lecture. I'll see you later.
Welcome to Master Kubernetes. In this course, we'll explore Kubernetes, the leading package in one of the most exciting and lucrative areas of computing technology today, container orchestration and deployment. We'll focus on hands-on learning, but first, let's explore the trends that have given rise to containers, the need for container orchestration, and how that has created the space for Kubernetes to rise to dominance and growth. The growth of technology into every aspect of our lives and days has created immense demand on software, the companies and organizations that sell and deliver products based on software, or just use software in their businesses. This really is nearly any business and anyone who doesn't live entirely off the grid. This pressure has spurred innovation and standardization, and the needs and stakes are so high, it has fundamentally changed how software is developed and deployed into production. But this evolution isn't without precedent. Could you imagine the world's economy relying on methods like this for the trade of goods? There would be no way you'd get your new iPhone in time. Now we take it for granted that shipping containers efficiently move between different modes of transportation, different ship owners and shipping companies, and they've standardized, ubiquitous, and available anywhere in the world. Almost always, no matter what it's in, if it fits, it ships. Modern software is becoming quite similar. As software systems become more complicated, this complication has driven software to be divided into smaller pieces such as microservices. Whether they're called microservices or not, these smaller pieces of software each need to be packaged, built, deployed, and accessed by other pieces of software around them to function as a total system. These small pieces of software can be deployed into containers that allow them to run on the same machine, virtual or real, but making it appear to the software that it's the only process running. Here's where we depart from the shipping container metaphor a bit. While a shipping container's sole job is to keep things contained within itself, typically interesting and useful software depends on other software around it to do its job. Here is where the need for container orchestration is born. There are definite benefits in keeping logically distinct software separate from each other. You can develop, deploy, scale, and maintain each small piece without too much fuss between the other parts of the system when it's not all in the same module. However, at some point, different parts of your application likely need to communicate with each other to do something interesting. For example, an API may need to communicate with business logic. It needs, in turn, to access information in a database. Containers themselves keep logically distinct pieces of software separate so they can be built, deployed, maintained, managed, and scaled on their own without unduly affecting other parts of the system. Container orchestration, on the other hand, defines how these containers interact as a system, the needs between each other, and how they come together to a performant, manageable, reliable, and scalable system. It is currently safe to say that Docker is the dominant leader in both technology and in adoption in containers. While others exist in the space, their dominance is so great, when you mention containers, it is almost synonymous with Docker. Other players exist in niche applications, and some movement around standardization is occurring. Although it is nascent, the Docker file standard is essentially today's standard, and Docker repositories define the dominant way of hosting versions of a container between developers and between systems that need to use them, such as orchestration systems like Kubernetes. Since container orchestration is a much newer space, only growing since the adoption of containers, the technologies are newer and still evolving. However, Kubernetes is quite advanced, and with Amazon Web Services finally joining its competitors in embracing Kubernetes, it now has the backing of nearly every major player in cloud computing through the Cloud Native Computing Foundation, also known as the CNCF, the organization that now governs Kubernetes. It has essentially become the de facto standard, especially now that it's nearing alternative or competing technology, Docker Swarm. Docker's solution to container orchestration has now announced support for Kubernetes-style configuration and processing. It is clear that Kubernetes is now the de facto standard, if not the acknowledged standard, in the industry in container orchestration. Containerization changed how software was developed and packaged. Container orchestration is changing how containers are deployed into bigger, useful systems. From here on out, we'll focus on how to use Kubernetes as your framework for container management using Docker containers. In the next lecture, we'll focus on the growth, lineage of, and why the market has chosen Kubernetes. In the previous lecture, we discussed how the evolution of deploying software modules into standardized packages that could run nearly anywhere was called containers, or containerization. You may recall that this movement towards containerization has created a new need to define and manage the life cycle of these containers and how these containers interact with each other to create a larger, interesting, and useful software system. The de facto standard for container orchestration is now Kubernetes. Kubernetes was born out of a project of Google's internal need for container orchestration. It was first announced in 2014 and has grown into a mature product, currently at version 1.8, with support and growth in the enterprise and most major cloud providers. Kubernetes, as a product, is governed in standards and deployment and development by a public process led by the Cloud Native Computing Foundation, also known as the CNCF. Much like the Linux model, Kubernetes has itself been repackaged into distributions with support and other commercialized offerings by large vendors, many of whom themselves are members of the CNCF, with many of the changes and improvements that they make going back into the open source project. Kubernetes enjoys a major lead in technology maturity and adoption for a variety of reasons. First, Kubernetes and its predecessor, Google Borg, go back to the very beginning of container orchestration. It simply has a head start on solving a very complicated problem. But that's not enough to sow a large advantage, of course. That dovetails with the second. Kubernetes and the people around it, especially its founders, have taken this organizational knowledge and preserved and grown it through the CNCF and a public stewardship process that allows Kubernetes to grow unlike proprietary technologies. Kubernetes has been free to be bigger than any one vendor's market share and has gained the trust and commitments of its users and the open source community at large, in large part by avoiding vendor lock-in, but allowing access to the kind of support and assured quality large vendors can offer through their own distributions. That is not to say that Kubernetes was or is without its competitors. Docker, the company that created Docker containers themselves that Kubernetes uses by default, has its own orchestration offering, for example. However, as it relates to Docker Swarm or even Apache Mesos, another mature orchestration project, Kubernetes has several distinct advantages at the moment. First, its lineage has given it quite a lead time in both time and pedigree. It never hurts to be born at Google, solving problems at Google scale. Second, it's not just achieved critical mass, it's actually grown to sustainability. And the CNCF organization provides some permanence to this, especially as every major cloud vendor and many major software vendors have joined the organization. As for the code, just look at the commits, follows, and stars of the various Kubernetes projects. They speak for themselves. Third, Kubernetes offers auto-scaling that continues to mature and does not introduce provider-specific details, but lets you leverage many cloud providers' implementation by abstracting them intelligently into common configuration files. This makes for an ease of deployment across hybrid clouds or public clouds or any type of deployment infrastructure. Kubernetes is a technology and software package you can run on your own, on your laptop, your own server hardware, your data centers, cloud providers, or a combination of them all if you'd like. In the next lecture, we'll discuss where to get started, how you can set up Kubernetes on each, no matter where or what path you plan to choose or need in your particular application. In the previous lecture, we discussed how Kubernetes can run nearly anywhere Linux does, on your laptop, your own server hardware, a cloud provider, or a combination of them all. In this lecture, we'll discuss with more specificity how and where Kubernetes is deployed. Kubernetes has a healthy ecosystem that carries with it many advantages. As it relates to setup and where Kubernetes lives, this means many people and companies have created both formal and informal support for Kubernetes use cases for nearly anyone's needs. For evaluating and learning Kubernetes, many people choose the Minikube distribution of Kubernetes. It sets up a Kubernetes cluster locally on any modern macOS, Linux, or Windows machine. It is not suitable for production by any means, but quite friendly and favorable for development and evaluation needs, as changes are quickly and easily propagated onto a local instance of Kubernetes without any major networks to slow you down. For larger development or staging work in production, Kubernetes can run on bare metal hardware or on cloud providers. Many cloud providers even provide a Kubernetes offering, which takes care of many of the more menial administration, configuration, and other tasks associated with running a Kubernetes cluster for you. Google Cloud Platform and Azure offer mature Kubernetes offerings that handle setup, management of your Kubernetes clusters on their cloud with ease, even through a friendly web interface designed and integrated with their cloud consoles. Amazon is rumored to have one of their own in development, or to bring Kubernetes compatibility to their existing Elastic Container Service to do the same. Regardless of where and how you run Kubernetes, you can always elect to stand up your own Kubernetes cluster on any cloud provider's virtual machines if they do not offer a Kubernetes service, or if you'd rather not use theirs. However, most managed Kubernetes offerings in the current marketplace provide a good value for many cluster use cases. Amazon does not yet offer a Kubernetes service, although with their recent introduction into CNCF, it is all but assured that one will be coming soon in some form or the other. Running Kubernetes on Amazon Web Services requires the user to set up Kubernetes on virtual machines and configure networking either on their own or using the CNCF-managed KOps deployment toolset. Using KOps whenever possible is highly recommended, as it reduces error, simplifies the work, and maintains consistency. Naturally, as the birthplace of Kubernetes, Google Cloud Platform has mature support for Kubernetes as a managed software offering through its Google Container Engine product. As you'll see later in this video series, Kubernetes setup requires a master, a few data stores, and the like to function. Google Cloud Platform's Container Engine offering abstracts these away and provides a management interface in their Cloud Console for these items. Of course, you can always set up your own cluster on bare virtual machines too, manually or using KOps. However, if the economics of Container Engine are reasonable, it's always wise to consider their managed service to avoid having to run and maintain certain parts of your Kubernetes infrastructure. For developing and testing applications on Kubernetes, and especially training, it rarely makes sense to stand up a large Kubernetes cluster in the cloud. So Minikube has been created to allow you to run the actual Kubernetes code locally on your machine to avoid the complexity, expense, and slower response time of a full remote cluster. We'll use Minikube in this video series almost extensively and exclusively for just this purpose. Minikube is well supported for development testing, however, it is not a production technology. It runs the actual Kubernetes codes. It is not emulation. However, running Kubernetes locally defeats many of the purposes of container orchestration and cannot be relied upon for production workloads. But it is very convenient for training and evaluation, so we'll leverage it extensively for this, as it excels in this area. The previous 3 lectures have focused on setting the stage for why containers and container orchestration are so important. By this point, you may be wondering, with software dedicated to such large tasks at such a large scale, how does one get started and interact with it in a manageable, easy way? Luckily, there's a very good answer to this question that's easy to approach and easy to get started with. As we discussed in the last lecture, this is what Minikube is all about. A distribution and package of the actual Kubernetes code that runs in an entire Kubernetes cluster on your laptop. Remember, Minikube isn't something you'd want to use in production or even staging for an application. What makes it great for training, development, and learning makes it quite useless for production. It's a great way to get into Kubernetes quickly, easily, and without the headache and hassle of a number of other things that are required for production use. Let's get started by installing Kubernetes. But first, make sure you have a Linux machine with the latest version of VirtualBox installed, or a Mac with the latest version of VirtualBox or VMware Fusion. As we set up Minikube, take notice of how we interact with it, the patterns of the commands and the like, how they're structured, for example. These should be pretty familiar, if not identical, to how you work with full Kubernetes clusters. Because remember, Minikube is the actual Kubernetes code, and we will use the actual Kubernetes command line tools to interact with it just as if it was a full production remote cluster. As we've mentioned before, Minikube requires Linux or Mac machines capable of virtualization with a hypervisor installed. On Mac OS, this can be any number of hypervisors, such as XHYVE, VirtualBox, or VMware Fusion. On Linux, this can be VirtualBox or KVM. VirtualBox is by far the most popular and is available at http://www.virtualbox.org. We'll start with installing a package called kubectl. This is the command line control tools for Kubernetes clusters. Whether it's a Minikube or a full-blown cloud-hosted cluster, you'll use this command line package to interact with your cluster of choice, including the Minikube cluster we're setting up today. Then we'll actually install Minikube and go through a few basic commands on how to work with it. As we dive into our first hands-on example, it's time to discuss a bit of detail as to how Kubernetes organizes concepts and a bit of terminology so this will all make sense. First, a central concept in Kubernetes is the deployment. It is a large, general, high-level construct that groups together the various parts of an application. You can, for now, consider a deployment to be akin to an application that you'd like to deploy, thus the name deployment. Second, deployments have pods. A pod is a group of one or more containers for an application. A pod is an instance of a container image, and there can be many of them in a deployment as needed. Third, services are endpoints that expose network ports to the outside world and are mapped to a port on a given pod for a deployment. This is how end users or intermediate services might access the services exposed by your pod or your container image you're looking to deploy. There are various types of services that we'll get into later in the lecture series. For now, just consider services as network ports that expose an application. First, let's install kubectl, the command line utility used to interact with Kubernetes clusters. You'll use this tool for both our local Minikube instance and any remote clusters you may manage or interact with. These installation instructions are built against Kubernetes 1.8 and guide you through manually installing and downloading the kubectl executable and installing it into your path. If you're familiar and comfortable with your specific operating system's package manager options, it may be beneficial to use such a route to install and maintain the latest version. For example, on macOS, the Homebrew Package Manager provides simple and straightforward installation and maintenance of the kubectl package. And several unofficial Debian sources exist for use with the apt package system on various Linux distributions. If you're comfortable and aware of how to use your operating system's package manager, we recommend using it to install and maintain the kubectl command set. You can skip these installation instructions if you'd like to use your operating system's package manager. If so, rejoin us on the next slide for testing your installation and moving on to Minikube. We'll begin by using Google to find the appropriate documentation. Let's Google install and set up kubectl. The first hit's exactly what we're looking for, the Kubernetes documentation on setting up kubectl. Let's go here and scroll down to the area that includes the URL to download for our platform. We'll choose Linux. Let's copy the URL and the command all at once so we don't have to retype it. With this copied to our clipboard, we'll now begin installation. And remember, we copied the URL, but you're also free to copy subsequent commands out of the Kubernetes documentation if you'd like to avoid retyping them. We'll start by downloading the appropriate package for our operating system, in this case, Linux. Once the download's completed, we'll make it executable. This step is not required on Windows. Now, we'll finally copy it into our path so it's executable no matter what directory we might be in. Now that you have kubectl installed, let's check to make sure it works properly. At the command line, type kubectl --version. It should output something similar to what you see on the screen here. Your version numbers may be different, and your git commit numbers are certainly going to be different. But as long as the command was found and it returns something similar to what you see here, you can be relatively confident that your install went well. Let's run this command on our Linux instance to see what its output looks like. Don't be alarmed at the error. This is just because we haven't set up a Kubernetes instance. Now that we have kubectl properly installed and working, let's move on to installing Minikube. Again, these installation instructions are built against Kubernetes 1.8 and guide you through manually installing and downloading Minikube and installing it into your path. If you're familiar and comfortable with your specific operating system's package manager, again, we recommend that you use that option to install Minikube. On macOS, the Homebrew Package Manager sometimes provides the Minikube formulas, and on unofficial Debian sources exist for use with the apt package management system again. Once again, let's consult Google for the appropriate page. We'll Google installing Minikube release. Again, the first result in this case is what we're looking for, the releases page on GitHub from the Minikube project. Let's go there. Let's scroll down on the latest release to the installation instructions and URLs. Again, let's copy the appropriate one for our platform to avoid having to retype it. Remember, you can continue to do this for subsequent instructions if you'd like to avoid retyping them. With this on our clipboard, let's move on to the actual install steps. We'll use the appropriate command to install Minikube for our operating system. Now that you have Minikube set up in your system, let's go through some basic Minikube commands. Before we get started, remember, you can copy and paste these commands from the text lecture at any point. Each one of these commands is available for you to copy and paste in this lecture and in subsequent examples. To begin, let's actually start our Minikube cluster by typing minikube start. It will take some time to download the various images and get the cluster started on your machine. If your machine's as slow as mine, you may want to go get a beer. You'll notice the kubectl is configured to use the cluster. Minikube does this for us automatically. Let's use kubectl to actually deploy the Hello Minikube sample application. We use the kubectl run command to deploy a sample image to our Kubernetes cluster. This command is worth noting. We'll use it extensively throughout this example and in future lectures. This command provides a simple and quick way to run a given Docker image on your Kubernetes cluster. While you may want to package a Docker image with more sophistication for full orchestration capabilities, the kubectl run command provides you the ability to quickly and in a straightforward way run a given image on a Kubernetes cluster when you need to. It's a useful command that you should note. We'll go further in depth about the usage of the kubectl run command in further lectures. Now that it's deployed, let's expose the Minikube sample application using the service command. This command will take the application, which is running locally in our Kubernetes cluster, and allow external IP addresses to access it. You may have noticed the use of the word deployment. In Kubernetes, a deployment is any set of resources that deploys a container, an application, a set of containers, or pods. We'll go further in depth as to what deployments are and how to work with them later in the course. The kubectl expose command is another command that you'll likely end up using quite frequently throughout your time with Kubernetes. Take some time to understand exactly what it does. In this case, we're exposing the deployment Hello Minikube with a service of type node port. There are a variety of types of services that are available. Specifying a node port allows us to have an external IP address connected to the port on the container that we just deployed using kubectl run. Other types include cluster IP, which is a private IP not available to the external world, and load balancer. Load balancer requires external functionality from either the hypervisor, the cloud provider, or the host upon which Kubernetes is running. We'll get into the specific types and other varieties later on in the course. You'll see the service was created. We can use the git pod command of the kubectl command line tool to see the status. It's running, has no restarts, and has been running for 46. We can now access the cluster and actually access the data on the service using the curl command. You'll notice in this case, we used the Minikube service to be able to get the URL of our pod. The output, as we expected, gives us an HTTP response. And finally, when you're done with the deployment, or no longer need a deployment, or would like to replace it, you can use the kubectl delete deployment command to specify a deployment for deletion. You can also use the Minikube stop command to stop your local Minikube cluster and free up any resources when you're completed. In the previous lecture, we used Minikube to deploy a sample application to verify that we had our local Kubernetes cluster installed properly. By now, you're probably wondering, what exactly is the application that we deployed? How does Kubernetes know which Docker image to pull? How does it know what to do with that Docker image? How does it know how the Docker image works together? How does it know how it scales? And how does it know how it fails? These are all very good questions. We'll start at the beginning. Your first Kubernetes application, a very simple deployment of the Tomcat application server. We'll look at how deployments are described and how we can deploy them to Kubernetes. So what does a Kubernetes application look like? Remember, deployments are the central metaphor for what we consider apps or services within Kubernetes. Deployments are described as a collection of resources and references. Deployments tell Kubernetes what Docker containers are interesting to us, describes a little bit about them, and how they work together, what's required to keep them healthy, and what to do when they may become unhealthy. Deployments can take many forms based on the type of service being deployed. Whatever form they take, they're usually described in a YAML format. You can store this deployment in a file for replication across many Docker containers, across many Kubernetes systems. However complicated they get, ultimately, deployments simply describe the containers used in an application, how they work together, and the care and feeding of them. Deployments, as you can imagine, can get relatively sophisticated for complicated applications, but let's keep it simple and start with something small and understandable. A deployment of the Tomcat application server. In this example, we'll deploy the Tomcat app server using the official Docker image. Our key tasks will be like any deployment you might plan, no matter how small or how large. First, we'll define the deployment, what containers we use, what services those containers might offer, and where they come from. Then, we'll expose the services to the world. What TCP ports and what HTTP services are defined in the containers, and where to reach them. Finally, we'll take that configuration information and we'll deploy it to our cluster. The first step is to define the deployment. The most simple deployment in Kubernetes is a single pod. Remember, a pod is an instance of a Docker container. Deployments can have any number of pods required to get the job done. They can range from one instance of a single image, like we're doing today, and grow to hundreds of images of different types. The most simple deployment simply has one pod. No redundancy, no separation of services, just one pod deployed to Kubernetes. The source files for both this lecture and subsequent lectures are available on GitHub. If you're familiar with how to use Git, GitHub, and associated tools, feel free to clone the repository on your own. If you're unfamiliar how to do it, follow along and we'll download the appropriate tools and do it together. The GitHub repository is available via the web at github.com/jleetutorial/Kubernetes-demo. If you're going to clone this on your own, feel free to go ahead, clone it, and join us in the rest of the example. Otherwise, open a web browser and head to this URL. There are a few ways that you can access this source code and save it to your computer. We'll use GitHub Desktop. Perhaps you have it installed and perhaps you don't. Whether or not you do, click on the green Clone or Download button, where you're presented with a choice. You are free to download a zip file of the repository, which doesn't require any extra software other than unzip in order to access the files. We're going to choose Open in Desktop. When you click Open in Desktop, it will prompt you, if you don't already have it downloaded, to download the GitHub Desktop program. In this case, we'll download it for macOS. Once the download is completed, open the file, install it appropriately for your given operating system, and open the program. Once GitHub Desktop is installed and open, go to the File menu and click Clone Repository. Ensure that the URL tab is selected. Choose a local path to where to download the files. And type or paste the URL of the repository. Remember, that's http://github.com/jleetutorial/Kubernetes-demo. Click Clone, and this will copy the repository files to your system. Those files are now available at the directory you selected initially in this dialog. Let's start with the text editor open with a blank deployment.yaml file. We'll define a deployment so we can send it off to our Kubernetes cluster to understand how deployments and pods work. Now would be a great time to locate the files we most recently cloned from the GitHub repository and open the file named deployment.yaml in the Introduction to Kubernetes /your first K8s app directory. The goal of the deployment.yaml file is to provide Kubernetes with the basic information of what the application needs to do, the resources required to accomplish it. There's a wide variety of robust tools available to define how pods fail, how pods stay healthy, and what to do when they're unhealthy. We'll go over the most important aspects of the deployment YAML file. If this looks a little intimidating, don't worry. There are only a few aspects of this which are key to understand at the moment. We're going to go in depth in future lectures about items like metadata, labels, selectors, and the like. Right now, the important things to note are the image name, the number of replicas, the container port, and the name of the application. We'll go through each of these individually. We'll explore the other items in depth in future lectures. Right now, the key items to review and retain are the ones that we're about to go over. For now, we're going to keep it simple. We're going to define a deployment named Tomcat-deployment that only has one replica, so one instance of one Docker image. This image is named Tomcat version 9.0. If we don't specify an external repository, Kubernetes will default to the public Docker hub. Finally, we let Kubernetes know that the Docker container Tomcat version 9.0 exposes a port 8080. This is where the Tomcat application server will listen by default on the Apache supplied image. You might remember from our previous lecture that we have to expose any ports in our deployment to the outside world. For that, we'll use the kubectl command similar to what we did when we were testing Minikube. We'll use the kubectl expose deployment command to expose our service named Tomcat-deployment as a node port. Don't worry about the various types of services and what they might be. In this instance, node port tells Kubernetes that we'd like to export or expose the container port of 8080 in our previous file to the external world on an external port. Let's see the details of how this works. First, let's start by verifying the deployment.yaml is proper. Looks good. We'll use the kubectl apply command to take the directives from this file and apply it to our cluster. You'll see that our deployment was successfully created. The next step is to expose the deployment as a service. The kubectl expose command will create the actual service and explore it to the world. In order to find what port it was created on, we'll use the minikube service with the name of the service --URL command. This will provide us with the URL, including the port number, that we can access our given exposed service on. Copying this URL, we'll use curl to access our local service. As you can see, we'll get the HTML of the default Apache Tomcat welcome page. We can verify using this tool that our service is indeed working. Let's review what we did here. First, we defined a deployment.yaml file that indicated what image to use and what services that image exposed. Then we mapped those exposed services from the container to the outside world. Next, we asked Minikube what port it chose to expose to the outside world. Finally, we verified using the curl command that we indeed could access our service at the given port. As you've probably noticed, the kubectl command is relatively important in managing Kubernetes. kubectl provides access to both local and remote clusters and is essentially the primary gateway to interacting with any Kubernetes cluster. Since it's the primary command line access tool, it's important to get to know it well. By now, you've used it to deploy some data and deploy a Tomcat deployment to a cluster. However, you can use it for a variety of other methods too. We'll go over the most common kubectl commands here. kubectl commands all share a relatively similar format and command set. Notice the patterns between the commands we'll review here and throughout the course. The kubectl get pods command lists all pods in a namespace. If we were to take our current Minikube setup and run kubectl get pods, we would have one single pod listed, the Tomcat deployment that we deployed in the previous lecture. This command provides the state, how many pods are available, restarts, and the age. Let's run kubectl get pod on our local Minikube. You'll notice that our Tomcat deployment container, actually pod, is right there. Don't worry about the other two, those are images I had running for later examples. Let's cut and paste the name of that pod for use in the next command. Copy that to your clipboard. If we'd like to get more detailed information on a pod or pods, we can use the kubectl describe pod command. If you don't provide this command a pod name, it will provide detailed information on every pod in the namespace in the cluster. If you provide it optionally, the name of a pod, it'll only provide data on that specific pod. Let's use the kubectl describe pod command and the name of the pod that we've already copied to our clipboard to get detailed information about the Tomcat deployment. As you can see here, we have a wide variety of detailed data specifically and only about the deployment for our Tomcat. Hopefully you remember the kubectl expose port command. Remember, Docker containers can expose a specific port. We have to take that port and tell Kubernetes to expose it to the outside world. Using the expose port set of commands in kubectl, we're able to name a deployment, a pod, or a service, and expose it to the given world at a given port or a random port that kubectl chooses. We're also able to define what type of service this is. Is it an internal-only service, also known as cluster IP? Is it an externally available IP address, also known as node port? Or should we use a function of a load balancer? Those are more advanced usages we'll get into later in the lecture. However, using the type argument, we're able to specify what type of port we're trying to expose. Next, the kubectl port forward command provides you with the facility to forward a port from the local machine on which kubectl is running to the pod on the remote host that kubectl is connecting to. In our current case, since Minikube is already running on our system locally, this really doesn't seem to do much different from kubectl expose. However, when you're dealing with a remote cluster and simply need to map a local port on your machine to a remote port on a given pod or container, this can be quite useful. The kubectl attach command allows you to attach to a pod to view its output. It attaches to a process that is already running inside an existing container. That's important to note, especially as we go over the next few commands. kubectl exec will execute a command within a container. This is a very useful command for debugging and understanding what might be going on inside your containers, as it allows you bash access to containers that may not otherwise have interactive facilities. The -i and the -t options are relatively important. When running kubectl, you're able to interact directly with the process you run, for example, bash, if you specify the -i and the -t options. Look at the sample output. Understand what is happening here, because this is a command that you may use very frequently when debugging or creating complex deployments. kubectl exec -it followed by the name of the pod followed by the command you'd like to run. In this case, bash provides us with interactive shell access onto that container. Using interactive shell access, we can then introspect processes and other items available inside that container that we otherwise would have to use other methods, such as log analysis, to get after. Let's use the kubectl get pod command to copy the name of our existing Tomcat pod to the clipboard. Let's use that name to use the kubectl exec command with the -it options. That way we can interact with it using the standard in as a TTY to run the bash command. We now have a bash shell within our given pod that we specified, our Tomcat pod. Remember, bash isn't the only command you can run. You can run anything that's executable within that Docker image specified in that pod. However, it seems to be the most common and most useful way of using the kubectl exec command when debugging pods. Kubernetes also provides a similar set of facilities to label pods for classification either through automated processes or for manual bookkeeping. Using the kubectl label pods command, we're able to set key value pairs on any given pod. This command updates the labels on a given resource. For example, here we're labeling our Tomcat deployment pod healthy equals false. Finally, the kubectl run command provides us with a quick and easy way of running a given image on our cluster. You'll remember we had to define a deployment file that defined a pod that pointed to a Docker image to get our Tomcat deployment to run in our cluster. While that certainly is the preferred method of deploying production applications, in certain situations, you may want to run a particular image on a cluster relatively quickly and without having to do it in a replicable fashion. The kubectl run command can be particularly useful in that case. You can provide it with an image to run, a port to expose, and other options and more advanced usage are also available. Let's use the kubectl run command. In this case, we'll use the kubectl run command to run a copy of the popular Hazelcast server. Using kubectl run Hazelcast, giving it a name, Hazelcast, specifying the image, Hazelcast, and a port to expose, 5701, gives us the ability to create a deployment with one command. Let's use the kubectl describe pod command from earlier to describe the pods running on our minikube. If we scroll up through some of our other pods, for example our Tomcast pod that's already there, we can see that the Hazelcast pod has been deployed. We were able to do that with a single command instead of having to define a deployment simply by hand. This is a convenient tool for a quick administration. These commands are simply an example of a wide variety of powerful commands that are available to you through kubectl. We'll go into more in depth further in the lecture. However, it's good to keep these two references in your bookmarks as you explore Kubernetes. First, the kubectl reference for the latest version of Kubernetes. And second, a kubectl cheat sheet that provides shortcuts to commonly used patterns in the kubectl commands. Remember, kubectl exposes nearly every aspect of the Kubernetes API through that command line tool. It's powerful and will be your friend, and mastering it will make your journey into Kubernetes all that much easier. However, that's no need to fret about rote memorization. The more important aspect of kubectl, much like anything else, is to understand what it can do for you. The documentation and reference will always be there to provide you specific details on how to do it. At this point, simply understanding what is available to you within kubectl is going to be the most powerful tool and the most powerful area. In previous lectures, we've gone through deploying applications to our local Kubernetes cluster running on Minikube. We type a command or send a small configuration file, and the app is running. Seems pretty simple, right? Well, that's how it should be. Kubernetes is designed to keep you productive and your systems performant by abstracting a lot of complexity into higher level concepts which are very easy to work with. But if you're anything like me, the first time I saw the magic of Kubernetes in action, I was very curious as to what was going on under the covers that reduced all of this work to a single command. Understanding this is not only fun for curiosity's sake, but knowing what happens when you execute a command and deploy a workload to Kubernetes is critical to becoming an effective Kubernetes user, operator, architect, or developer. It can also help you troubleshoot things when the inevitable problem pops up. So, in this lecture, let's look at how Kubernetes is architected at a high level. Don't worry about the individual component details quite yet. We'll go into each later on. The key thing to understand is what each component does, not necessarily or exactly how it does it for now. In Kubernetes, the task of managing containers, where they run, the nodes upon which they run, and the like is handled by the Kubernetes runtime based on input from you in your deployment file. You've seen some simple deployments up to now, and we'll get into more sophisticated ones soon. In Kubernetes, the master or masters, you can have multiple masters for reliability and scale. We'll get into that later. The masters control any number of nodes. These nodes are individual machines that run pods. End users then, through services we declare, you may remember doing this in the previous example, access our application directly on the nodes. Don't worry about each individual component inside the masters and nodes for now. We'll go over each in turn later. Just take away from this that the masters control a variety of nodes and the pods running on them based on your deployment. Since containers and container orchestration technologies de-emphasize the role of the individual system, whether that's a server, a VM, or even a container, it can be difficult to get a starting point when exploring Kubernetes architecture. You'll remember the pod and deployment are relatively important concepts in Kubernetes from previous lectures and examples we've worked through. But let's think a little bit lower level for now and start with a familiar concept, the server or the virtual machine. In traditional architectures, it was usually the center of the universe. In Kubernetes, they're still quite important. They're called nodes. They used to be called minions, so you may see that in some older documentation, but now we refer to them as nodes. A node is a worker machine in Kubernetes. A node can be a VM or even a physical machine. Each node, regardless of what it is, has the services necessary to run pods and is managed by the master components. We'll discuss these later. Remember, masters just decide where to run your application. Kubernetes can consist of any number of nodes. It varies depending on your needs. We'll get into how you specify how many to run, what types to run, and how Kubernetes chooses what pods to run on what nodes and the like later. Don't worry about those details for now. But just remember, each node has a common set of services at the very least, regardless of what pods it may be running, that allow the master to send it work to do. These include Docker, a service called Kubelet, and a service called kubeproxy. Kubelet watches and manages processes on an individual node. You can think of it as the supervisor for that machine. It has one job. Given a set of pods to run from a master, make sure they're running. Kubelet runs pods. Kubeproxy is the glue on each node that makes sure the network services exposed by each pod on the node can be accessed as defined in the deployment. You may recall when we set up a Tomcat service, we created a node port service to allow the outside world to connect to it on port 8080. Kubeproxy was the glue that made that happen. Let's review how this all fits together. First, you deploy an application to Kubernetes. We've done this before. Initially and internally, the master will evaluate your deployment descriptor and decide where and how to run it. It will direct Kubelet on the appropriate node or nodes, depending on if the deployment asks for multiple replicas, to run the pods. Second, you define a service so users can access it. We've done this before too. The master will create connections between an external load balancer and external IP. For example, if you're running on a public cloud, it will direct the kubeproxy on each pod to connect to this given API or service, and the pods on each node. Finally, end users can access the services appropriately, as the load balancer will decide which pod to send it to based on the configuration created by the master during the deployment. Again, understanding this overall orchestra is more important than understanding individual instrument in it for now. In the previous lecture, we alluded to the fact you need not run only one instance of your pod. Whether it's for scale, to meet more demand, or for reliability, to have backup workers in case one or many die, replication is an important cornerstone of Kubernetes. Kubernetes supports scaling through replicating pods on the same or multiple nodes. But before we go into how this works, let's explore how applications should be designed to scale in Kubernetes. Many paradigms exist for effectively scaling an application. For our purposes here, we'll categorize them into stateful and stateless applications. Stateful applications store client data generated in one session for use in the next session with that client locally. The effect of this is to essentially lock a client session to a given thread or instance of an application on the server. If that server process dies, client state is lost. It is also the only one who knows what state that user's data is in. All subsequent requests must come to it. Stateless applications, on the other hand, update a centralized data store, such as a database with the result of a single operation, so the next client session or operation can be handled by any thread or instance of the application. Kubernetes supports both patterns. However, it is a best practice to create stateless applications whenever possible, and leverage replication without having to use stateful replication mechanisms. Architecting applications varies by programming language and framework, and it's beyond the scope of Kubernetes. Many great resources on software design exist that discuss the different approaches to designing stateful or stateless applications. For now, let's assume you're working with a stateless application so we can focus on how Kubernetes handles scaling through replication. Kubernetes gives you a variety of options to define how a pod should scale. By far the most robust, flexible, and frequently used is setting the replica options in your deployment. It's what we'll do today. Just for the record and for your knowledge, you can also define a replica set, deploy multiple bare pods, define a job. This is useful if you're doing a niche form of bash processing, or a daemon set if you're looking to replicate older software patterns like daemons. However, the dominant way of deploying a replica is to define the replica options in your deployment, and that's what we'll do today. We'll focus on the first as it's the most common, robust, and useful. Don't worry about the details of the others. We only mention them to be complete, as you may encounter them in documentation, discussions with others, or elsewhere as you explore Kubernetes and need to address more advanced niche use cases. Let's look at something familiar, our Tomcat server from previous lectures. Remember our Tomcat server deployment and when we said that we'd come revisit a few of the other parameters? Well, let's example the line that says replicas 1. At the most basic level, this is where we declare to Kubernetes how many copies of the pod we'd like to run. We can run as many as we have resources for on our cluster. There are various other properties we can set to define how these replicas are built, where they can run, and the like. But for now, let's keep it simple and simply tell Kubernetes we'd like to run 4 replicas, and leave the rest to Kubernetes itself. By setting replicas to 4, we have specified for this deployment that we'll have 4 replicas of the Tomcat pod running. This can provide redundancy and more capacity in a properly architected application. We could either create an entirely new deployment that looks like the above, or we could use a Kubernetes scale command to scale our existing deployment. Let's look at that. Issuing this command to our existing Kubernetes deployment modifies the deployment to have the exact same effect as if we were to make a new deployment, but it saved us from the headache of having to delete our old deployment and create a new one. It's also avoided any downtime for the application during that switchover. The kubectl scale command will set our existing Tomcat deployment to 4 replicas. Let's run this against our existing Kubernetes deployment and see what it does. If you had stopped Minikube the last time you'd used it, remember to start Minikube by issuing the minikube --start command. I already have it running, so I won't execute it. let's use the kubectl scale command. Let's type kubectl scale --replicas equals 4 deployment / tomcat -deployment. Let's execute the command to scale our Tomcat deployment to 4 replicas. At this point, you can trust that Kubernetes has scaled the Tomcat deployment given the output from the command. Or you could use a number of commands which you're already familiar with. For example, the kubectl get deployment command will get the information about the Tomcat deployment. You can see here we successfully have 4 up-to-date replicas. You could also use the kubectl describe deployments command to get more detailed information about the nature of these 4 replicas. You can see from the output of this command that Tomcat deployment was scaled to 4 of 4 replicas just a few seconds ago. So, now that Kubernetes is running 4 replicas, how does it decide which one gets to do the work? That's the second half of scaling. Now that we have 4 replicas running, we'll need to update our service definition connected to our deployment to take advantage of our replicas. You may recall from previous lectures that the only way pods can be exposed to the outside world is through defined services. We have used the kubectl expose command to create services to expose our previous Tomcat deployment to the outside world using the node port service. This command created an external port that connected to the port running on the pod that ran the Tomcat container. It mapped one port to one service on a node. That's what a node port service does. Now that we have multiple nodes running the same service, we need to graduate to something that can handle something more sophisticated than just exposing a single port on a single node. You may recall from the previous lecture that the load balancer service provides exactly this function. A load balancer is a type of service that exposes a single port, but uses a variety of internal logic, which we'll cover later, to decide which replica to send the request to. Let's look at what a load balancer service will look like for our Tomcat replicas. As you can see, it's not that different. We've added a few more options to set the newly created service's name to something predictable, and define the port we'd like to listen on and what port it's going to be on the pod. First, let's use the kubectl expose deployment command. Using this command, we will specify that our Tomcat deployment should have a load balancer exposed on port 8080, forwarding to port 8080 on its container and all its replicas, and we'll give it a name, something that we can easily refer to it by later. We'll see the command is successful when we can see that the service was properly exposed. Finally, we can use the kubectl describe services command to give us more information about the newly created service. Specifically, we can see what IP address was issued for the newly created load balancer. Let's issue the kubectl describe service tomcat-load balancer command. Remember, that's the name we gave it when we created it. As you can see, it's assigned an internal IP. Since we're running on Minikube, this will be an IP that we probably can't access. When running on a production cluster, it will be available as an external IP from whatever APIs your cloud provider may provide. For now, let's not worry about how we access the load balancer. We'll get into that when we talk about the DNS system and how names and network addresses are resolved in your Kubernetes cluster. For now, simply be confident that the load balancer was properly created, and since we're running on a Minikube, there's some things we're just not going to be able to get. Like an example, load balancing. We'll cover these items in later lectures. Hopefully, by this point, you're getting the feeling that deployments are pretty central to things in Kubernetes. We've used them to define a Tomcat service, scale it to multiple pods, and tell a service how to access the pods inside our deployment. As a foundation for diving deeper into Kubernetes, let's discuss more about deployments, their nature, and how to work with them. Deployments are a way to declare a desired state for your application. Kubernetes uses your deployment, usually defined in a file, to deploy your application according to how you describe it in your deployment configuration. You've already worked with a couple basic deployments to define a Tomcat container and then scale it. Deployments give us the advantage of letting us describe the semantics of our application and its needs in a central area, and let Kubernetes handle a fair amount of the details for us. They're not the only way of deploying applications to Kubernetes. In fact, in earlier versions, they didn't even exist. You had to work with the lower level objects, for example, the pods, the containers, the images, yourself, and create your deployment the way you wanted it. However, they have become the de facto standard and insulate you from having to handle otherwise quite complicated tasks on your own. With deployment objects, you can do a variety of things. You can create a deployment. You can update an existing deployment. You can apply rolling updates to pods running on your cluster. You can roll back to a previous version, or you can pause and resume a deployment. We've already done the first thing on the list. In fact, we've already done the second as well, when we set the existing deployment to a replication factor of 4 in the previous lecture. Applying rolling updates is very useful. We can use deployments to ease the pain of updating an application. By using rolling updates, we can use Kubernetes replication function to only update a subset of our replicas at any given time to a new version of our application, so the upgrade could occur without any noticeable downtime to the user in a properly architected application. We can also use a set of functions to roll back to a previous version of a deployment. If an update caused a problem, or for any other reason we'd like to go back to the previous version of an application, we can use the deployment rollback feature to go back to a previous version. And finally, you can pause or resume a deployment. And this is exactly what it sounds like. The application running as part of the deployment can be paused or resumed with some simple commands. Working with deployments is equally simple as many other things using kubectl. kubectl is your gateway to working with deployments. Here's the useful commands and what they do. First, you can list deployments using the kubectl get deployments command. Then, you can also view status of deployment rollouts using the kubectl rollout status command. You can also set the image of a deployment using the kubectl set image command. And finally, you can view the history of a rollout, including previous versions that you're able to roll back to using the kubectl rollout history command. Let's go through each one of these commands in detail, and you can follow along. We'll start off with one that you're already familiar with, kubectl get deployments. We've used the get deployments command to see what's been running on our minikube before. By typing kubectl get deployments, we're able to see what is running and a variety of information about it. In this case, Tomcat deployment has 4 replicas. We can use the rollout status command by typing kubectl rollout status deployment and the name of a deployment to see the status of a deployment and if it's been rolled out. Once the command is executed, it'll tell us if it's been successfully rolled out or not. Let's refresh our memory on what our Tomcat deployment looks like. Let's look at the deployment file. In this file, you'll notice we specified one container, named Tomcat, using the container image Tomcat:9.0. This deployment has one container, the name is Tomcat of that container, and it specifies the Tomcat:9.0 image from Docker Hub. We could use the kubectl set image command to change the image in any container, as long as we know its name and the new image that we'd like to set it to. Let's upgrade to the newest version of Tomcat, 9.0.1, using the kubectl set image command. To do so, we'll need to note the name of our container. With that information on our screen, let's use the kubectl set image command, specifying our deployment/tomcat-deployment. the name Tomcat for our container equals tomcat:9.0.1. That will set the image name on the Tomcat deployment. Let's execute the command. As you can see, the deployment was successfully updated. The kubectl rollout history command can give us information about the history of a rollout of a deployment. In this case, let's specify kubectl rollout history deployment / tomcat-deployment to get the history for our Tomcat deployment. As you can see, it'll note we've made 2 changes recently. We can get the information and the details of a given revision by typing the same command with the -- revision equals the revision we'd like to look more information about. Let's look at number 4. As you can see in this situation, it's given us the information about what the state of that deployment looked like. As your Kubernetes deployments grow, you'll have more and more objects available to you in the Kubernetes interface, both in the command line and on the web. Don't worry, we'll get into the web interface later. There are a variety of tools that are available to you to organize items within the Kubernetes interface. These are called labels and selectors. However, labels aren't useful just for organizing for the end user. Labels can be used to describe to Kubernetes how various objects and resources within the cluster work together. As your Kubernetes deployments grow, they'll invariably include multiple services, pods, and other resources. Keeping track of these can become cumbersome. Even more challenging can be describing to Kubernetes how these various resources interact, how you want them to be replicated, scaled, and serviced, and what to do and to what object when things might go wrong. That's where labels and selectors come in. Labels are key value pairs that let you set human-readable attributes on nearly any resource. Selectors are the criteria you can use to match labels. This way, using labels and selectors together, you can begin to describe to Kubernetes how your system is configured. Kubernetes also provides a few labels out of the box for common concepts. For example, things like host name, operating system type, architecture, and the like are defined on nodes. A complete list of the predefined labels is available in the Kubernetes documentation. Let's work with an example of how we use labels and selectors to accomplish a task in Kubernetes. For example, let's say we had a deployment, and we had a variety of nodes in our infrastructure. But only one of these nodes had an SSD. All the others were spinning disks. We have an application which requires an SSD for both speed and consistency. We can use labels and selectors to describe to Kubernetes the variety of traits about our nodes. We'd apply labels to each node, indicating whether they had an SSD or a spinning disk. Then, we could use selectors to tell Kubernetes that when it's deciding what nodes to run a given pod on, to only use nodes that had a label SSD. Labels and selectors together are not only good for organizing for a human in an interface like kubectl or the web. Labels and selectors allow Kubernetes to make decisions based on logic that you describe to it in the deployment to do real, actual tasks in scheduling and error recovery. You can label nearly anything in the Kubernetes world, whether it's deployment, services, nodes, or anything else that's addressable through the kubectl interface. Let's use labels to label a node that has SSD storage, and then use a selector to tell the deployment that our application should only ever go onto a node with SSD storage. For this example, we're going to use node selector. Node selector is a property on a deployment that uses labels and selectors to choose which nodes the master decides to run a given pod on. To accomplish our goal of running our deployment only on nodes with an SSD, we will first label a node as having an SSD. Then we'll define the node selector on our deployment to match only nodes having the label we just defined. The first order of business is to label our node. Let's use the kubectl get nodes command to find the names of our nodes. Since we're running on a minikube, there's only one, predictably named minikube. Let's type kubectl label space node space minikube to specify we'd like to label the minikube node. Then let's tell it we'd like to label the storage type equals SSD on that node. Once this is set, we can use the kubectl describe node command to look and make sure that our label was set. If we scroll up, we can see that the label was successfully applied. Now that our label has been applied to our node, we'll need to apply the node selector to our deployment. Let's go look at the deployment.yaml file. Remember, this is available in GitHub under the labels and selectors directory. The deployment.yaml file looks pretty much like we have throughout this course, except we've added node selector with storage type equaling SSD. This tells Kubernetes that when it's selecting nodes to deploy Tomcat onto, it should look for a label named storage type with the value SSD. Since we've made a change to our deployment.yaml file, we'll need to use the kubectl apply command to apply that change. Let's make sure that we're in the proper directory and look at the deployment YAML file to make sure it's the right file. Looks good to us. Now let's use the kubectl apply command with the -f flag and pointing to the deployment.yaml. This will apply the new updated deployment.yaml file onto our Kubernetes cluster. As you can see, the deployment was successfully configured. Using the kubectl apply command allows you to apply changes to the deployment that may not be possible using a variety of kubectl commands. For example, node selector must be done in the deployment file. Kubernetes is smart enough to understand what changes need to be applied and what is different from the new application of the deployment from the existing one. With this change applied, Kubernetes will only deploy Tomcat to nodes that have been labeled with a storage type equaling SSD. So far, we've assumed everything is going well in our software world. We've built a Tomcat service, scaled it, and even put it behind a load balancer. But what happens when one of these replicas has a problem? A bug in an application takes it down, or an issue with the runtime hangs it? How do we detect that? Kubernetes defines a variety of ways of doing this. They're called health checks or probes. They are what they sound like, a way of telling Kubernetes how to check the health of a given pod. Kubernetes has two types of health checks to ascertain two different things. First, Kubernetes uses readiness probes. Readiness probes are, well, what they sound like. Kubernetes uses them to determine when a pod is ready. After it has started the container, it can use a readiness check to see and ensure that that container is ready for work. Liveness probes determine when a pod is healthy or unhealthy after the pod has started and is ready to begin taking requests. Whether it's a readiness probe or a liveness probe, you can use a variety of methods to ascertain a container's status. You can create a probe, whether it's for liveness or readiness, that uses HTTP or TCP to send a request to the pod. If it succeeds, it's deemed healthy. If it fails, in the connection or an HTTP error code is sent, it's deemed as a failure. Or you can specify a command to run on the pod inside the container. If that command exits normally with a 0 exit code, it's deemed a success. Anything else is deemed a failure. These probes, whatever they are, whether they're HTTP, TCP, or execution of a command, are defined on the container in a deployment or a pod specification. Let's go back to our Tomcat deployment to define a readiness probe and a liveness probe. The first thing we'll do in our example is that we will use a readiness probe to check whether the pod has started and is ready to begin taking requests. Most basically, we're just checking to see if Tomcat has started up, since this might take a while on some machines. Finally, once the readiness probe has indicated that the container is now ready to do work and accept work, the liveness probe will begin on the Tomcat deployment. That will begin to check at a given interval if Tomcat is accepting requests or if it's hung. From the GitHub repository, let's look at the basic and core concepts /health checks directory. The deployment.yaml file located inside it is what we're looking at now. You can find this file, again, under basic and core concepts /health checks in the GitHub repository. Take a moment to open it if you need. You'll notice it looks pretty familiar. The file, up until about a little bit more than halfway down, looks exactly the same. We've added two stanzas, the liveness probe and the readiness probe. You'll notice that these two stanzas have a lot in common in themselves. In fact, the way you define a liveness probe and a readiness probe, the actual format, is exactly the same. You'll notice a few differences in a few of the properties within each one. That's because we need them to do different things. Remember, the readiness probe at the bottom of the file is our way of telling Kubernetes how to test to make sure that when it starts the pod, that it is ready for work. In this case, we'll tell it to access port 8080 every 3 seconds after an initial delay of 15 seconds on simply the / directory. Once this succeeds, Kubernetes will know that the pod is ready for business. After that, it'll go to the liveness probe. Every 30 seconds, after an initial delay of 30 seconds, it will use HTTP to access port 8080 on the / path. If the HTTP request fails, it will deem the pod to be unhealthy. We'll go over what happens later. If the HTTP request succeeds, it's deemed to be healthy. Let's begin by checking to make sure we have the right deployments file. From the health checks directory, let's look at the deployment.yaml file. A liveness probe and a readiness probe. Looks good. Let's use the kubectl apply-f command and pointing to our deployment.yaml file to apply the contents of it to our cluster. Once it's applied, let's use the kubectl describe command by specifying deployment, tomcat-deployment, to look at the details. You'll see this output looks pretty similar, except now we see a liveness and a readiness line. These are our indications that a liveness and a readiness check has been deployed as we thought. Up to this point, our primary point of contact with Kubernetes has been the kubectl command-line interface. kubectl continues to be the dominant tool and will be for the remainder of the lectures. However, in some situations, a web interface is equally useful. Kubernetes provides a web user interface called the dashboard that we can use to access the same information that kubectl can present in a friendly point-and-click web interface. It's called the dashboard UI. It runs on your Kubernetes masters and is accessible directly if you have a direct connection to your cluster or to your masters. This is unlikely in production situations. However, kubectl is your friend. kubectl can create a proxy or a tunnel for you from your local workstation to a Kubernetes cluster that you may not have direct network access to using the kubectl proxy command. The Kubernetes Web UI, or the dashboard, provides a variety of views for nearly anything in your Kubernetes cluster. It allows you to update, delete, and create nearly anything you may need to in your Kubernetes cluster as well. It accesses the same APIs as kubectl. It simply provides the interface and the data in a different form. Using the web interface is quite simple. On some Kubernetes clusters, the dashboard UI is pre-installed. Most cloud providers automatically install it when you provision a Kubernetes cluster on their managed services. However, if you're bringing one up from scratch, or are working with a provider that doesn't enable this by default, you can use the kubectl create command by installing the dashboard using the command shown. you can access the dashboard through a variety of ways. As we mentioned earlier, if you have direct network access to the IP address of your Kubernetes masters, you can simply go to the web browser and go to http:// the IP address or the host of your master, :8080/UI. However, the most foolproof way and the recommended way, even if you have direct access to the masters, is to use kubectl proxy to set up a proxy on your local machine that will access the API and the interface remotely through a tunnel. Type kubectl proxy and navigate the localhost :8001/UI in your web browser. Let's start the service by typing kubectl proxy. You'll know it's successful when it says starting to serve. Note the URL. We'll use that URL to access the web interface on our machine. Let's take this URL to our web browser to access the Kubernetes dashboard. You're welcomed by a variety of information: the overall status of your Kubernetes cluster, how many pods are running, what pods those are, what deployments they belong to, and the replica sets automatically created for us in those deployments. This should look familiar. This is largely the same information that we were able to access using the kubectl git deployments command. These are the details of our Tomcat deployment. You can access a large variety of information through the Kubernetes web interface. A number of objects are available, many of which we haven't discussed. Don't worry about the details of those yet. One of the objects we have discussed, however, are nodes. Everything we're looking at in the Kubernetes web interface runs on a node. So let's go check out our nodes in our minikube. Remember, since it's a minikube, there's only one node. Let's look at its details. We can browse through the various information that we would have gotten if we had used the kubectl describe node minikube command. It's also providing us with information about the resource, what pods are running on it, and a variety of other information. You'll even notice that the label set, storage type SSD, in a previous lecture is available and shown here, much like the output from kubectl. In fact, this data comes from the same source as all the data from kubectl, just another way of getting to it. Similarly, operations available to us in kubectl are also available to us in the web interface. By clicking the Create button, we can create a deployment. This offers us a graphical user interface to the same information as we would have defined in a deployment.yaml file. It's up to you whether you'd like to use a what you see is what you get WYSIWYG style editor as you can see here, or use the power of the command line and your own YAML text files. If you choose to use your own text files, you can still upload them with the web interface. This is the functional equivalent of using the kubectl apply command, which we have in previous lectures. To learn more about Kubernetes, we encourage you to come back to take the dashboard tour to learn more about each individual item and action you can take and view within the web interface. For now, simply knowing that kubectl and the web interface are available to you as two methods of getting at the same data and viewing or manipulating objects in your Kubernetes cluster is enough. Picking the right tool for the job is always a way to be most effective as possible. kubectl excels at certain things, and the web interface excels at many things. Now that you have both tools at your disposal, you're able to choose what is most effective and what you may prefer. Up to this point, we've largely discussed single-purpose deployments. For example, we've deployed containers as part of our deployments that just do one thing: a Tomcat app server and a MongoDB database. That's certainly interesting, but you're probably thinking by now, well, modern software systems are comprised of many different modules that need to work together. How do we accomplish that? That's a very good question. In Kubernetes, and in modern software systems in general, separation between the deployment, scaling, and configuration of individual modules is considered a best practice. But if each of these modules is an independent deployment, how do we get them to discover and communicate with each other to create a meaningful software system and do it in a maintainable way? There are many options This area is called service discovery and goes well beyond Kubernetes. Service discovery is a broad and diverse topic, but we'll just focus on how it relates to Kubernetes. Today, we'll focus on the main and most used method in Kubernetes for service discovery. That is using the built-in DNS system provided by Kubernetes to create predictable, maintainable, and reliable linkages between otherwise independent modules or services. DNS, or the Domain Name Service, is a cornerstone of the internet. It translates names into IP addresses. Kubernetes has a built-in DNS service that is launched and configured automatically. Kubernetes configures kubelets to tell individual containers to use its DNS service to resolve DNS names into IP addresses. It seamlessly resolves internet names, just like would normally happen on your web browser or a mobile phone, but also provides a predictable set of DNS names for services running within the cluster. This is how Kubernetes provides facilities for service discovery. Every service in your Kubernetes cluster gets a DNS name. Kubernetes has a very specific nomenclature for how these DNS names are created. You don't have to remember it. You can query it using kubectl tools, but it might be helpful. The name is quite simple. Just like www.google.com is comprised of 3 different names, www being the host name, Google being the domain name, and .com being the top-level domain name, Kubernetes provides you with a name for every service deployed automatically in its DNS. First, it starts with the service name. This is typically the name of your deployment. Followed by a dot comes the namespace. We'll talk about what this is in the next slide. Then it's followed by .svc, .cluster, .local. You can consider this the top-level domain to make sure that the name is unique and doesn't overlap or duplicate with any name on the broader internet. You can use this well-known pattern to design loosely coupled services, or at least set defaults in a reasonable manner. Software systems such as Ruby on Rails and even Node.js are moving towards a convention over configuration style of management. It's not that they won't allow you to configure parameters for the application, but the movement towards having sane defaults or predictable defaults that usually just work out of the box is one called convention over configuration. Kubernetes supports this by providing well-known predictable DNS names that you can later manually override if needed. However, the default should create a well-oiled system if designed properly from the beginning. Let's talk about namespaces. We'll discuss namespaces in depth soon in their own lecture, but for now, just know the following. Kubernetes allows you to define a namespace or namespaces. They allow you to separate your cluster into smaller logical clusters. It's still the same hardware, the same broader cluster you've always worked with, but it provides a logical separation between applications running on it. By default, everything you do is in the default namespace, and everything we've done so far has been, and that's okay. Kubernetes DNS names will include this namespace in the assigned DNS name. Namespaces are helpful mostly for large clusters with many users across many teams and projects. Using the default namespace is fine if this logical separation is not required. But take, for example, a large organization that has one Kubernetes cluster. MySQL for the HR department might be different from the MySQL instance for the development department. Using namespaces such as HR and development would provide a separation not just logically, but also in the DNS names created for both MySQL instances. This is what namespaces are for. Let's have a visual look as to how this works in a bit more detail. As we've mentioned before, service discovery helps us link 2 different pods. In this case, application 1's pod number 1, and application 2's pod number 2. These are separate deployments which exist without really knowing the details of each other. The way they can map to each other leverages the DNS service provided by Kubernetes. In this setup, the service, app1, which exposes the services of application 1, is given an IP address assigned by Kubernetes. You don't have to know what it is. However, you can always know that you'll be able to reach application 1 at service name app1. If we were to look at the DNS records of this theoretical situation, we could see that the host for app1-service has IP address 10.0.0.1. The same goes for app2. In this way, app1 and app2 can know simply to access each other by name, and the IP address will be resolved at runtime. By binding services to human-readable names, it not only makes things easier to configure, but removes us from having to tightly bind services to IP addresses that may change or we may not have control over. You may also be wondering, how does the DNS service itself work? It's a bit of internals of Kubernetes, but let's go over some of the high-level concepts. If we were to run a regular command on our Kubernetes cluster and look at the resolve.conf file, this is the file that controls what name servers our Linux instance will use, we'll see that it points to the internal DNS named KubeDNS that's provided by Kubernetes. This is a system which you don't have to configure and is automatically kept up to date by the Kubernetes master. So, when pod 1 or pod 2 needs to reach each other and simply use the name app1 or app2, KubeDNS is the one that's keeping track of what IP address was granted to that given pod at any given time and providing that IP address back to the DNS query made by the individual pod. This is accomplished by using the internal name server provided by KubeDNS, which is automatically available and provisioned for you when you're using Kubernetes. Let's explore a practical example of how we'd use service discovery to join together two otherwise completely different packages that need to work together. Let's set up a blog using a system called WordPress. WordPress is a very popular blog and website management system. WordPress is maintained by the company called Automatic. It's a completely independent software package available as open source and paid support. It's completely separate from a database called MySQL, which is a database management system, a relational database management system, maintained by a completely different organization than WordPress. These two independent software packages work together to serve the website and store the data required for that website. When you set up WordPress, it needs somewhere to store the data, the blog posts, the images, and the variety of content that you might host on any given website. WordPress handles serving that up to your customers, your clients, and your visitors, and gives you an interface with which you can add more content quite conveniently. MySQL is what's used to store that content persistently and in a way that can be organized and indexed for quick retrieval. What a database system does. Together, they'll work together to host the website. These two separate pieces of software is what we'll deploy as separate deployments and bind them by given names using the DNS system that we've described for service discovery. You can find out more about WordPress at wordpress.org and MySQL at mysql.org. Let's take this theory and move it into a practical example now. Let's consider deploying WordPress onto our Kubernetes cluster. As you may know, WordPress requires MySQL to function. WordPress and MySQL are created by two different organizations, are on two completely different release schedules, and are largely administered in two very different ways. For this example, and in reality, it's probably a good idea to have separate deployments of the WordPress software and the MySQL software. That way, they can be patched and maintained on their own release tracks, and they might even be maintained by two different people with two very different skill sets. However, for WordPress to function, it needs to know about MySQL and how to interface with it. So there must be some sort of linkage between these otherwise two separate deployments. Specifically, WordPress needs to know a TCP/IP hostname where it can connect to MySQL. We'll use DNS to create a WordPress deployment that expects MySQL to be running on the WordPress-MySQL hostname in the same namespace. Now you can see how Kubernetes' default behavior of creating a DNS name for a given service will allow us to connect two services together that otherwise may not know anything about each other. Let's talk about MySQL first. We'll deploy it first in a deployment named WordPress-MySQL. Since MySQL exists at the so-called bottom of the stack, it's where the data gets stored, and WordPress expects it to be operational when it comes online. Let's just deal with it first. Once it's deployed, it will run MySQL 5.6 on port 3306, which is the default port that MySQL runs on the WordPress-MySQL hostname. This is the name of the deployment. Remember, we're using this well-known name to allow Kubernetes to wire the IP addresses together using DNS. We can reference WordPress-MySQL in other deployments, and it will automatically resolve to the IP address that happens to be active for the MySQL service. Once MySQL is running, we'll bring WordPress online in a deployment named WordPress. Since we'll already have configured MySQL to be available on the WordPress-MySQL hostname, when WordPress starts, it will be able to obtain the IP address of the running MySQL deployment without knowing any of the details as to how MySQL was set up, how it's being run, or the health of the service. The only thing it needs to do at runtime is use the regular TCP/IP communications channels and resolve the WordPress-MySQL hostname, and it will connect to the MySQL instance. So let's get started. First, let's deploy MySQL. Remember, you can access any of the files which we're looking at in this lecture in the Advanced Kubernetes Usage folder under the DNS and Service Discovery subfolder in the GitHub repo for this lecture series. First, we'll use the mysql-deployment.yaml file to establish two objects. First, we'll declare a service named WordPress-MySQL that exposes a service on port 3306. This is the default MySQL port. Secondly, we'll define a pod. In this deployment, also called WordPress-MySQL, we will use the MySQL Docker container version 5.6. This is maintained by the MySQL open source project. We'll use their default configuration, and we'll specify the MySQL root password. This environment variable is defined by the MySQL Docker container, and we'll set the password to be passwords in plain text are bad. We will show something more secure later. You'll also notice that we've defined the container port of 3306. The Docker container is listening on port 3306 for the running MySQL instance. This, as we mentioned, is the default behavior of MySQL. Since we've defined a service above, this will be exposed to anyone connecting to the WordPress-MySQL service into the container running MySQL. Now, let's use the kubectl create-f command to point to the mysql-deployment-yaml file. This will create the MySQL deployment and the service on our server. We can use the kubectl get pods command to make sure that that was successful. Now that MySQL is running, let's deploy WordPress. Now, let's have a look at the WordPress-deployment.yaml file. Similar to MySQL, it declares two objects, a load balancer and a deployment with a pod. Let's have a look at the service it deploys first. You'll notice this service is named WordPress, runs on port 80, as you may know, the default port of HTTP, the language of the web. However, it deploys a type load balancer. This is important to know. This buys us two important differences over a regular service. If you don't specify load balancer, the service is only available inside the Kubernetes cluster by default. The IP address is chosen largely at random in the available IP space. When you specify load balancer, however, Kubernetes uses an external load balancing service. For example, on Amazon AWS, Amazon Web Services, it will connect an elastic load balancing service, a service provided by Amazon, with an external IP address, which is monitored, and connect that to your service. Similar services exist on nearly every cloud provider, such as Google Cloud Platform, Microsoft Azure, and other cloud providers. The important aspect to note is that a load balancer uses an external load balancing service with a public and usually static IP address, although that varies by provider, and connects it to the service on your deployment. Let's look at that now. We'll use the WordPress 4.8 image, again, maintained by the WordPress open source project run by Automatic. A couple of variables are defined, like the database host, WordPress_DB host. This is where the magic of DNS allows us to loosely couple services and provide service discovery. The value is WordPress-MySQL. We'll also define the WordPress DB password. This was the password which we set in the MySQL configuration. Finally, you'll notice that it exposes port 80. Port 80 is what the WordPress process inside the container is running on. Again, this is the default behavior defined by the creators and maintainers of the WordPress project. This will be wired up to port 80 on the load balancer, so we can access our WordPress service externally from outside our Kubernetes cluster. Let's use the kubectl create-f command and point it at the WordPress-deployment.yaml file we just looked at. Much like we have in the past, this will create the service and the deployment. We can use kubectl get services WordPress to only look at the WordPress services to see that indeed a load balancer has been created. Remember, since we're running on a minikube and not on an actual Kubernetes cluster on a cloud provider which provides services like load balancers, we don't actually have a load balancer. This is because minikube doesn't provide those facilities. Instead, minikube, for testing purposes, simply makes your load balancer function on a random port on your machine. You can use minikube to retrieve the URL at which this load balancer is listening. The minikube space service space WordPress, the name of the service, --URL command will provide us with the URL at which the service is available. Because minikube doesn't provide a load balancer, this just connects you directly to the open port on the container. Let's copy this URL to our clipboard, select it, and do Control-C or Command-C or Edit Copy. Going into a web browser, let's navigate to this URL. You'll notice WordPress is ready for us to continue our installation through its GUI interface. At this point, WordPress has connected to MySQL and is properly running on our Kubernetes cluster. You can walk through the installation process as you would any other WordPress installation. We've used DNS to connect two different services, developed, maintained, and deployed completely separately, to connect them in a maintainable and understandable way. Using the DNS service discovery, these services have now created a software stack that allows WordPress to run on top of MySQL and provide content management and deployment services. We'll explore some nuances of how to better secure our secrets and how to persistently store our data in the upcoming lectures. In the previous lecture, we set up WordPress and MySQL. You could imagine that a WordPress site or an SQL database would really like to have long-term reliable and persistent storage for the data entrusted to it. You may know that files created or modified in the file system in a Docker container are ephemeral, meaning they only exist for as long as that container is running. Once it is shut down or the host running that container is stopped, those changes are lost. When the container restarts, it is back to its original state from the original image. This is great for scaling and reliability. Containers being stateless and starting with a clean state is a cornerstone of what makes Kubernetes and stateless application frameworks work. But on the other hand, we need some mechanism other than local storage to provide us with persistence. To accomplish this, computer systems have long used block storage. Whether it's a spinning disk or a solid-state drive, persistent storage promises to retain data across restarts, scale to relatively large sizes, and be somewhat portable between machines. We can't attach a physical disk to a logical container. That functionality is provided by Kubernetes volumes. Since containers exist in the logical world and physical disks exist in the physical world, there must be some kind of bridge to define how those two resources can interact with each other like they do in an actual hardware computer system. Kubernetes provides the logical concept of the persistent volume to connect containers to volumes that Kubernetes then maps to some form of physical storage as it's defined by you, the Kubernetes user, administrator, or developer. Much like you have many choices in choosing a type of disk for your hardware server or virtual machine in terms of size, speed, how and where it is mounted, etc., you have those same options in Kubernetes volumes and persistent volumes, as well as a few other options that define how these volumes are mounted to pods. When we set up WordPress and MySQL, we promised we'd go deeper into volumes, and this is where we'll do it. Volumes are like disks, but with a little bit more. At its core, a volume is just a directory, possibly with some data in it, or maybe ready for data to be written to it, which is accessible to the containers in a pod. How that directory comes to be, the medium that backs it, and the contents of it are determined by the particular volume type being used. Kubernetes has a wide variety of types of volumes. This is an incomplete and non-comprehensive list. The Kubernetes documentation provides a full list of officially supported volumes. In terms of cloud providers, volumes can range from Azure disks and Azure files to Amazon Web Services' Elastic Block Store and Google Compute Engine's persistent disks. On the hardware side, whether it's a storage area network, a file system, or actual hardware, a variety of file systems, interconnects, and even local storage types are supported. It's important to note that local is only supported in Minikube and for local development purposes. This stores an actual directory on the node itself. This is not supported in production and in fact cannot even be used in production. However, is very useful for Minikube so you don't have to attach an entire fiber channel storage device to your laptop for simple testing. Similar to if you were creating the specification for a computer system that you would purchase as hardware, you can specify to Kubernetes what volumes and what persistent storage you'd like your containers to have. As long as you have the resources on the machines running your Kubernetes systems, you're able to provide that storage to containers by using volumes. Let's look a little bit more into what volumes are and how they work. First, pods can specify what volumes they need and where to mount them. They use two different areas to do this, and we'll look at some specific examples in a moment. They use the spec.volumes field in the specification of the deployment to say what volumes they need. And they can use the spec.volumes.containers.volume mounts field to say where to mount them. Processes in the container can then see a file system view of the data in that volume. What's important to note here is that volumes let us separate stateless portions of our application, the code that needs to run, from the stateful data, which is the data that the code runs over. This allows our infrastructure to be scaled and maintained and live separately from the data that it works on. It also may allow us more portability, more backup and recovery options, and ease other management tasks when we have a well-architected system. We need not back up the Docker containers because those live in a repository. However, we need to back up and recover user data in the event of a failure. By separating these two out, we've eased the management tasks for both types of data because they're markedly different in some systems. Persistent volumes are a type of volume designed to provide persistent disk-like functionality. They are the ones that are most commonly used in Kubernetes and that we'll use in our demonstrations. Using them involves a couple of easy steps. Don't worry about the exact syntax, we'll go over that later. First, you can provision a persistent volume itself. This is akin to creating a virtual disk on your cloud provider or installing a physical disk in your hardware server or computer. Then, once that disk is created, you establish a persistent volume claim on your deployment. The persistent volume claim is a request for storage by a user in a pod. That is what maps a given claim or pod to a volume that was created. In the next lecture, we'll get into the possibility of automatically provisioning persistent volumes where it's possible. But for now, go ahead and know that you will have to, or someone or something will have to create a persistent volume in order to service a persistent volume claim. The Kubernetes master takes care of examining the available persistent volumes and matching them against demands from the running pods in their persistent volume claims. This might seem like a lot to take in. Let's look at it visually. First, an administrator, whether that's you or someone else, defines volumes on your Kubernetes cluster. These volumes can be cloud-backed disks or actual physical disks in a physical server. It varies by implementation. In Minikube, it's just directories on your laptop or your computer system. The developer or the Kubernetes users define claims for volumes. They don't necessarily know, and nor really should they care, where that data is actually being stored. They simply care that it is persistently stored at some point. They can provide a variety of criteria, such as storage class, size, and the like. And then at runtime, when the deployment is made to the Kubernetes cluster, the Kubernetes master looks at the claims or the asks for volumes, matches them with available volumes, and attaches those volumes to the newly created pods. In certain situations where there are not enough volumes, an error may occur, or if auto provisioning or dynamic provisioning, as it is called now, is enabled and possible, the master may create new volumes in available space on the cloud provider or the physical disks attached to the cluster. We'll go into dynamic provisioning later. For now, just know that the Kubernetes master matches claims with volumes and attaches them to pods at runtime. How this happens doesn't have to be the worry of the administrator or the developer. Now that we know how all the pieces interact together, let's look at how we define them and the syntax in detail. First, let's look at how we create a volume. To create a volume, you use the persistent volume object. This definition specifies the type, size, and how a volume can be accessed. The type and access type is highly dependent on the underlying media. Whether it's a local disk, a network mount, a cloud block storage service, or just a directory on the host, can dictate the minimum and maximum sizes and whether they're read-only, read-write, and whether many people and many containers can read and write them at the same time. This is largely a limitation of the underlying media and not something imposed by Kubernetes. Let's go look at how this is defined. In the data on the right-hand side of the screen, you can see a persistent volume that is named task-pv-volume. This follows the same metadata naming convention that you see elsewhere in Kubernetes in your deployments and services. Next, in the actual specification, under the spec property, you can see the storage class name. This can be used to define multiple types of storage classes. They're up to you, whether it's SSD, spinning disk, SAN. This allows you to create different classes of storage that your end users and your application might need to define in their given claims. Further, you can define the capacity. How much storage do you want to allocate to this volume? Next, you define the access mode. This is largely dependent on the underlying media. Is it a spinning disk? Is it a network storage volume which can be shared across multiple containers? Can multiple people read it and can multiple people write it? This is highly dependent on the underlying storage media, and you probably should consult your hardware documentation or your network administrator or your cloud storage provider what mode needs to be specified here. The Kubernetes documentation can help you understand what mode is appropriate for a given cloud provider or a given type of hardware. This varies based on what is providing the actual persistent storage. In this example, there's a further property, host path. Since this is a local volume, it simply provides access to a directory on the host for testing purposes. It doesn't actually create a disk on a cloud provider. This simply says where that data will reside. This is only provided or needed if you're using the directory on the host for testing purposes and not actually creating a volume on a storage device. In this case, since we're using a host path, the configuration items for that particular type of underlying storage are enumerated here, like the directory on our local host, where the data for that volume will be stored. If you are using a different type of storage, such as a SAN, NFS, or a other type of backing volume, the configuration would look differently. Consult the individual storage provider's documentation and the Kubernetes persistent volume documentation for what that might look like, as this varies provider by provider. Now that we have volumes created, we have to claim the volume to attach it onto a pod. Pods use persistent volume claims to request physical storage defined by persistent volumes. Kubernetes uses the information in a claim to look for a persistent volume that satisfies the claim's requirements. If it finds a match, it binds the claim to the volume. If it cannot find a match and automatic provisioning isn't enabled, we'll go over that feature later, it results in an error. Let's look at the syntax for claiming a volume. It's defined by a persistent volume claim. The claim has a metadata section with a name, just like any other Kubernetes object. In the spec, the claim specifies what it is requesting. In this situation, this claim is requesting a manual storage class with read, write once accessibility, and it requests 3 GB of storage. The Kubernetes control plane will use that information to try and find, or if enabled, automatically provision a volume that matches those criteria. Once those criteria are met, it will bind it in the runtime configuration in Kubernetes, and that will be accessible to the pod at the given mount point. We'll talk about that and specifying mount points in a moment. To make this real, let's look at adding volumes and volume claims to our MySQL and WordPress deployments so that any changes and posts we make in WordPress are persisted not just across container restarts, but across other events such as moving them between servers, etc. First, let's take a look at the local-volumes.yaml file. Remember, these are available in the GitHub repo under Advanced Kubernetes Usage, Volumes. In the local-volumes.yaml file, you can see two separate volumes are being declared. This makes sense because we need a volume for both MySQL and WordPress. In this case, we're making one each. They're defined relatively similarly. They follow the same format of the persistent volume that we just spoke about. In this case, we're giving them the names local-pv-1 and local-pv-2. They're 20 gigabyte volumes that you can read-write once. That means one person or one container can read and write to them at a time. They're host path disks, meaning they're not backed by an actual magnetic disk, they're not backed by a SAN storage device or a cloud block storage device. Instead, on your Minikube, it will simply store data somewhere on the Minikube host in a directory that we specify. In this case, it's /tmp/data/pv1 and /tmp/data/pv2. This creates two empty disks that Kubernetes can use to fulfill persistent volume claims made by each deployment. Let's go look at each respectively. Let's consider the MySQL deployment. It looked relatively familiar to the last one that we used. First, the service is declared. Now the persistent volume claim is something new. Looking at this persistent volume claim, you can see where it's named MySQL-PV-claim. We're asking for a disk which is capable of read-write once, meaning that one container can read and write to it, and has 20 gigabytes of storage. You'll remember in local-volumes.yaml, we actually declared two disks that would meet the criteria. That gives Kubernetes the ability to bind that disk to this claim. Let's scroll down a little bit more and examine something that we had mentioned earlier. Once this disk has been bound to this container, how do we know where it will be mounted? In normal Linux file systems, you can mount a disk at any point in the directory structure. This is exactly the same. If you notice the volumes and volume mount stanzas under the specification or spec property, you will notice that the persistent storage claim and the persistent volume is declared, and a mount path is specified. The name of the volume is MySQL-persistent storage, and it references the claim that we just looked at above. That claim, when fulfilled and when bound, will be mounted on the mount path at /var/lib/mysql, where the Docker container expects it. The Docker container and the MySQL process running the Docker container will write data to that directory. Since that directory is mounting a persistent disk, that data will now be available across restarts. Let's go check out the WordPress deployment. This should be similar. The persistent volume claim looks pretty much the same as the MySQL deployment persistent volume claim. In this case, the only difference really is the name, WP-PV-claim. Let's scroll down and have a look at the volume mounts and the volumes. In this case, we'll notice a WordPress-persistent-storage volume that's bound to the persistent volume claim. We can see that it's being mounted on /var/www/html. Again, WordPress will write to the /var/www/html directory a variety of files such as images and static data that it's going to need to present your website properly. Now that that directory is actually mounting a volume brought through a persistent volume claim, that data will be available across container restarts, across movements between nodes, or other events that may cause the container to restart that would otherwise result in data loss. Now, let's actually apply these changes to our minikube. Let's use the kubectl create-f command and specify the local-volumes.yaml file. This will create the two local persistent volumes on our machine. We can use the kubectl get persistent volumes command to see that they were successfully created. Now that we've created the local volumes, let's apply the changes which we've looked over in MySQL and WordPress. We'll use the kubectl apply command. First, let's type kubectl apply -f and specifying our MySQL deployment YAML. You'll notice the service went unchanged and it configured the deployment for a new persistent volume claim. Let's do the same for our WordPress deployment. You can ignore for now any error messages or warning messages that indicate about kubectl apply should only be used on certain resources. You may or may not receive this error message based on your configuration. This error message has more to do with how the resource was created than any error going on right now. It is typically a best practice to use kubectl apply. At this point, both MySQL and WordPress deployments will have been restarted to reflect our changes. But just to be sure, let's issue a minikube stop and a minikube start. This will ensure that we've stopped our cluster and restarted it with new disks mounted. Based on the speed of your machine, this may take a few moments. Take as much time as you need. And once minikube is started, come back and start a web browser. With our web browser started, let's go to our minikube and get the URL for our WordPress instance. If you already have it, saved on your clipboard or in your terminal, copy it. Remember, you can issue the minikube space service space WordPress space -- URL command to get the URL at which the service is available on your machine. Let's copy this URL to the clipboard. And let's navigate there in a web browser. Let's continue to set up WordPress. We'll pick US English for our setup language and just give it some information. Let's choose Master Kubernetes as a site name. You're free to give it whatever you'd like. Let's create a user. Let's call it Kubernetes. Again, you can free to use whatever you'd like. Create a password that you know you'll remember. In this case, we're going to pick something very insecure, but this is just local and we'll get rid of it soon. Enter in our email. And let's install WordPress. Based on the speed of your machine, this may return quite quickly or may take a few moments. Once it's completed, you should see a screen similar to this. Let's log in. If you've never used WordPress, it's actually quite simple. Once we're logged in, let's go to the Posts menu and click Add New. Let's give the post a title. Something simple like, this post should live on. This is getting sent to persistent storage. Let's publish the post. Let's visit the site by going to the upper left-hand corner, Master Kubernetes, and click Visit Site. As you're able to see, we have a post. Now that we have some data in both our WordPress and our MySQL instances, let's go and delete the pod for WordPress and see what happens. Let's return to a terminal window and prepare to delete the pod so we can see what happens and the advantage of using persistent disks. Let's delete the WordPress deployment by using the kubectl delete deployment WordPress command. The deployment was successfully deleted. Let's ensure that's the case by trying to reload the page. You can see it's unable to connect. Indeed, the deployment is no longer there. We can verify this with kubectl git deployments. While SQL is still there, our WordPress instance is not. Let's recreate the deployment using the kubectl create -f command and pointing it to the existing file, the file that we used to create the deployment. We may see some errors because remember, this file defined 3 different things: a service, a persistent volume claim, and a deployment. The first 2 still exist, the third does not. As you can notice, the deployment WordPress was created and the 2 other resources already exist. That's fine. Let's ask Minikube once again for the URL to the new service, although that shouldn't have changed. We can use the Minikube space service space WordPress space -- URL command to do this as we have before. This URL hasn't changed, but let's use it anyway. As you can see, even though we recreated the WordPress pod and deployment, our work is saved. We weren't prompted to create a new blog or a new WordPress instance like we were the first time we did it. Instead, the persistent volume and the persistent volume claim were assigned to the new pod that we created. Indeed, our post lived on. While this may seem simple and nothing really to write home about, when you consider the power of segregating the stateful parts of your application from the stateless parts of the application and allowing them to be managed separately, where persistent state is no longer tied to the image and the code required to execute logic in your application, you can see the power that Kubernetes provides in terms of providing scalable, self-healing architectures. This is merely a simple example of how to use volumes. When you consider cloud-based storage systems and how volumes are provisioned and deprovisioned and backed up, you can see at scale, this indeed can provide a significant benefit in a properly architected application in a variety of management and also deployment needs. Faster applications, which can be managed in a more resilient fashion with less resources, and even in an automated fashion are possible with Kubernetes. This is simply the basis. Most systems in modern computing require some sort of credentials to secure access to their services, access other services securely, and connects to external systems. Typically, these credentials are designed predicated on the fact and the assumption that some sort of data can and will be kept secret amongst those entitled to know. Common examples of this include a user and password combination, a private key certificate, or an API key. Whatever they are, their magic lies in the fact that they're kept a secret amongst those who are entitled to know them. If you know them or have them, you can get access to the service. As software systems grow and more developers work collaboratively on them, more system administrators from both inside and outside the organization may work on the system, and source code for the application is shared, perhaps even publicly on the internet. The need to secure these secrets through separation from those with a need to know and those without a need to know continues to grow. Soon, setting passwords and configuration files on small post-it notes next to the server or other ad hoc methods just isn't enough for both security or convenience. In many situations, legal or other certification compliance needs a built-in method for separating these secret items from non-sensitive information. Kubernetes Secrets provides this functionality to hold sensitive information such as passwords, tokens, and SSH keys separately from plain text non-sensitive configuration items. Putting this information in a secret is safer and more flexible than putting it verbatim in a pod definition. You may recall how we use a single secret to set and share the password for our MySQL database when we were setting up WordPress. This was not only convenient, we only had to set the password once in one place for 2 different services, but it also removed the password from the plain text configuration files. We could have shared those files with any number of users, contractors, or even published them on the open source web, and our secrets would have remained safe. A secret is an object that contains a small amount of sensitive data, such as a password, a token, or a key. Such information might otherwise be put in a pod specification or in an image. Putting it in a secret object allows for more control over how it is used and reduces the risk of accidental disclosure. Users can create secrets, and the system also creates some secrets. To use a secret, a pod needs to reference the secret once it's created. A secret can be used within a pod within 2 ways. 1, as files in a volume mounted on one or more of its containers, or used by the kubelet when pulling images for the pod and setting it as an environment variable in the running container. Secrets are stored in a couple of ways. Kubernetes provides separation for secrets, but it does not provide strong encryption. Secrets are typically base64 encoded strings stored separately configuration and injected at runtime. You can encode the string manually, or you can use Kubernetes tools to do it for you. The latter is highly recommended. Remember, secrets don't provide strong encryption. Secrets assume that you've already taken appropriate access control methods to your cloud provider and simply provide separation of the data. Secrets are key value pairs. Both the key and the value are arbitrary strings. When you define a secret, you're not just defining one string, you're actually defining a set of key value pairs. This data structure is called a map in some vernacular or a hash table in others. Basically, consider it a set of key value pairs that you can set and retrieve. Now you may be wondering, what is the method that Kubernetes uses to turn arbitrary data into a string? For items like passwords, which are already strings, they're already human-readable strings you can store in environment variables without a problem and put into a configuration text file. That shouldn't be a problem. But what happens if we have other data, like a binary certificate or something else that we'd like to keep safe and secure in secrets? We mentioned base64. That is the method that Kubernetes uses to encode arbitrary data into text. It's an industry standard which is used widely across the web. In case you're unfamiliar with it, you can think of base64 as a well-accepted method to turn any data, whether it's human-readable text or binary data that could be an image, a digital certificate, or any other information, into a text string which you can manipulate and put into a configuration file, etc., without any large problem. It has a variety of implications. Number 1, it removes special characters and it turns everything into Unicode or actually ASCII text to text standards. Number 2, it has the side effect of increasing the length of strings, so it's best used with small pieces of data. Remember, secrets is not designed as a large object store, so this is fine. Base64 is a standard which has been in use quite a bit, and most tools and most systems have facilities for accessing them. If you need more information, you can consult a number of articles on base64, including Wikipedia or other resources, simply by Googling base64 encoding. Let's talk about creating a secret. You can imagine, given the pattern of things that we've done up to this point, kubectl will likely help you here. There are 2 methods you can use to create a secret for further use in other areas such as deployments. First, you can create it from a file, or you can create it from a string using kubectl on the command line. You can pull a secret from a file. The kubectl creates secret, then providing the name of the secret you'd like to create, and specifying the --from-file command allows you to create a secret from a file. The contents of that file follow the same format that you would need if you were creating a literal on the command line. Using the kubectl create secret generic space the name mysql-pass --from-literal equals the value. In this case, you can see the value, the key password equals the value of your password. Remember, secrets are a set of key value pairs. That's why the literal here says password equals your password. We could set the key to whatever we'd like. It doesn't have to be password. It could be username equals your username, or API token equals our API token. Once you've created the secret, the second half is using the secret. You can use a secret as an environment variable. If you look at this configuration, it might look similar. This is the deployment or a snippet of the top of the deployment file from our WordPress MySQL container. If you notice at the bottom, we're defining an environment variable on the MySQL container. The mysql_root_password environment variable will be set when the container is started or restarted. You'll note that the value comes from a secret key reference, the name being mysql-pass, which if you notice in the previous slide we created using the command line, pulling the key password. Remember, we set password equal to our password value. This will pull the key password from the mysql-pass secret and inject it into the mysql_root_password environment variable for use by the container. The developers of that container image expect that environment variable to be set, and this is how we can hand it off to them in a secure, separated fashion. We could also place that secret on the file system as a file. This is further down in the same configuration file. I've truncated the top so it all fits on the screen, but if you look, the spec should be familiar. You can see we've added a volume mount under /etc/secret store. We've named it secret-storage. This will create a mount point on our container at /etc/secret store. Then, below in our volume stanza, we've indicated what that volume is to be. Instead of pulling a persistent volume claim and looking for a disk, Kubernetes will attach a file from the secret mysql-pass. It will mount that file at /etc/secret store, and any process on the system or in the container will be able to access that file using normal file open and viewing methodologies. These are two methods of achieving largely the same thing, of taking a secret and getting it into a running container, whether it's set as an environment variable or as a file. You can choose which one works best for you in your given circumstance. Let's do what we've talked about in a practical example. Earlier, we called out a weak point in our WordPress and MySQL stack. When we were first creating it in the DNS lecture, we noticed that the hard-coded plain text password may not have been the best idea for production-grade systems. This is true and a best practice across the industry. So, let's take our newly found secrets knowledge and replace the plain text value in both of our MySQL and WordPress deployments with a secret in both of these deployments. Let's have a look at the correct part of the mysql-deployment.yaml file that we used to set up MySQL. This should look familiar. Remember, we're defining an environment variable named mysql_root_password. This is expected by the MySQL container because that's the way the maintainers of that image have defined it. It's defined in the documentation and we're expected to provide it. In this case, we're providing the text value directly under declaring that variable. That's how you define variables in Kubernetes. We've been over this before. If you look at the right-hand part of the screen, the new mysql-deployment.yaml, which, by the way, as always, is available in the GitHub repository for this lecture series in the Advanced Kubernetes Usage folder under the Secrets subfolder, has a very slight change. You will notice it says the same name, mysql_root_password, as we don't want to change the name of the environment variable, but we've changed from value to value from. And we have provided a secret key ref, which is a secret key reference, referencing the name of the secret and the key inside the secret where that password can be found. This references a secret, which we will then have to go create where the actual password is stored. We've shown how to do this earlier in this lecture, and we'll walk through this in a real example later. We'll make the exact same changes to the wordpress-deployment.yaml file. We'll change the plain text password value declaration to a value from the exact same secret and exact same key. You'll notice, in this case, we're referencing the same secret name and the same key. This way, the password is maintained more securely, but also in a central location. An unlimited number of deployments and containers can reference one secret, making changing passwords across multiple systems very easily. In this case, MySQL protects the database with the given password, and anyone accessing it needs to know it. So providing it in one place allows MySQL, the person who's enforcing the password, and WordPress, the instance that is using the password or that credential to access it through another service, to simply reference one object. This makes administration easy, so when it comes time to change the password, multiple configuration files don't have to have the same value. As long as they're referencing the same secret and that secret is updated, it's updated across all containers. With these newly modified configuration files, we can now migrate our existing deployment of MySQL and WordPress with hard-coded passwords to secrets relatively easily. You've already seen the updated files, which we'll apply to our existing instances. The only other remaining step is to ensure that we create the secret before we apply the modifications. We've already shown how to use kubectl to create secrets from two different sources. In this case, since we only have to set one password, we'll elect to use kubectl's command line interface to create a password as an environment variable. That'll be step number one. Then we'll apply both the new MySQL and the new WordPress deployments with the change referencing that password instead of the hard-coded variable. Now that we have all the pieces in place, let's actually go and do it. We'll use the kubectl create secret space generic space the name mysql-pass command to create the password --from-literal, and then we'll define the key value pair. Let's set the password to something sane, like a much better way to store a password, for example. This will set the secret in Kubernetes. We can use the kubectl getSecret command to see the secret. It was created. It won't give us the value because it's opaque. That's good. Now let's apply the MySQL deployment. The changes have been applied. Let's do the same for WordPress using the kubectl apply command. The changes to WordPress have been also applied. Let's also verify that the changes were made on the deployments. We'll use the kubectl describe deployment command to look at the WordPress deployment. Sure enough, we can see that the environment variable here is set to the secret. Let's do the same for MySQL. Here, we can also verify that the environment variable was set to reference the key password in the given secret. Everything looks good. Now, just as proof that everything's working properly, let's use the minikube service WordPress --URL command to get the URL to our WordPress service. Let's copy this to the clipboard, open up a web browser, navigate there to make sure that everything is working properly. Sure enough, our blog and our WordPress site works properly. It's there and able to access the database. If not, there would have been an error because it couldn't get to the database containing the information required to generate this page. We've examined secrets, 2 ways of storing information which otherwise should be kept in a controlled environment. It's a best practice to separate this from configuration, as configuration files might be saved and shared with and worked on by people who shouldn't have access to more sensitive information such as API keys. Remember, there are 2 ways you can create secrets, either as command line literals or files. You can inject them into your containers as environment variables, or you can inject them as volumes mounted at a specific point. This gives you flexibility and options in inserting this information into a running container and choose the best tool for the given application. Now that we've mastered creating usable systems that can persist themselves, let's start to think about how our application lives in the wild. It's not enough to just run an application, but we want to be able to run it performantly, reliably, and perhaps even react to changes in usage or various situations. But before we can act on something, we have to know about the health of our system. We've discussed health checks in the past. These tell us if something is working or isn't, but that's relatively binary. Systems are more than just up or down in the real world. They're busy and slow, or fast and have room to grow. Metrics and resource monitoring can help you gain these insights into your system to better inform how you can act, or perhaps how even one day an automated system might be able to act on your behalf. Usage and performance monitoring is a large field. It's been around since the advent of computing. There are many free and paid packages and services, both for Kubernetes and beyond, that you can explore that promise to give you all kinds of insights into your system. We'll explore Kubernetes' native stack with a few open source additions. This consists of Heapster, backed by InfluxDB, and visualized by Grafana. Heapster is a CNCF project, which is maintained by the same organization that maintains Kubernetes. Heapster is installed as a cluster-wide pod. It gathers monitoring and events data for all pods on each node by talking to each kubelet. The kubelet itself fetches this data from cAdvisor, an internal Kubernetes system. Heapster will send this data to InfluxDB, and we can visualize it using Grafana. These are Kubernetes add-ons that are sometimes enabled by default if you are running on certain cloud providers like AWS or Google Cloud. You really don't have to do anything more to get this functionality, as it's enabled by default. On Minikube, however, we will need to explicitly enable them, and we'll walk through doing that in this lecture. As we mentioned, Heapster collects and interprets various signals like compute resource usage, lifecycle events, and the like. Heapster supports pluggable storage backends. We'll use InfluxDB. It's the most common and what comes out of the box in the Heapster add-on. Heapster stores a wide variety of data points related to usage and performance from a variety of internal sources, namely cAdvisor. By default, it collects data from Kubernetes' internal processes. The Heapster documentation can provide more information into how to plug into other sources as well, but the out-of-the-box information should be more than enough for most purposes. This data can then be accessed by user interfaces and other processes to provide visualizations and other actions when pulled from InfluxDB, where Heapster stores it. Before we actually look at the dashboards, let's enable Heapster on our Minikube. To do this, we'll launch Minikube. If you already have it running, you don't need to do this. On Minikube, we'll have to enable the add-on first. First, we'll run the Minikube add-ons enable Heapster command. This will take a while. Grab a snack, a drink, or a beer. It may take a few minutes or longer. On my machine, it took up to 5 minutes. You can use the kubectl get pods space dash dash namespace equals kuba dash system command to check the pod status for both Heapster and InfluxDB. If you see container creating and not a full amount of pods ready, then you'll know your system is still working. Don't be worried if this takes up to 5 or 10 minutes. Once the pods are up, you can access the Grafana dashboard by typing the minikube space add-ons space open space heapster command. This will open a web browser to the appropriate URL running on minikube that allows you to log into Grafana and access information about a variety of metrics collected by heapster. Let's get started. We'll use the minikube add-ons enable heapster command to enable heapster. This will take a while. The minikube add-ons open heapster command will open Grafana UI. If you get an error message like this, that simply means things aren't ready yet. Don't worry, give it some time. If you come back and you see this message, it's pretty self-explanatory. The endpoint for the service is not quite ready yet. Keep waiting. You can use the kubectl get pods -- namespace equals kuba - system command to look at the available pods. If all of them are running, then it's ready. You can issue the minikube add-ons open heapster command, and it will open Grafana in a web browser. Let's have a look. From the home page, first log in. Go to the upper left-hand corner and click Sign In. On minikube, the username is admin and the password is admin. Once you're logged in, you can navigate to a variety of dashboards. Under the home menu, let's look at our cluster and pod statistics. By clicking on pods, we're able to view a variety of dashboards. Let's change to the default namespace. This is giving us information about our Mongo cluster from the Mongo exercise. A variety of data, including file system usage, memory, and CPU usage is available. Let's go look at WordPress MySQL. The same information is available. File system usage, networks, memory, and other information is all available, including CPU usage, by pod. We can also choose what time range to look at. Since you just started your monitoring system, your data may not be available quite yet, or you may only see lines at the right side of your screen. This is normal. The system needs to be running for a few minutes to be able to collect information. Remember, you just started the monitoring system, and it may take a few moments for your particular system to populate with information. You can explore the user interface once it's populated with information, look at different timing areas, or look at different metrics ranging from CPU, file system, and network use by pod or by your cluster. As you've probably noticed at this point, Kubernetes allows you to name objects of nearly any type. You can give your deployments easy to remember names, like WordPress-MySQL for the MySQL database for your WordPress instance, or give its secret object for the database password the MySQL-pass name. This all makes sense if your Kubernetes cluster is only being used by a single user, team, or project. But what would happen if you had multiple teams, each running their own WordPress instances on your cluster? They'd have to fight for who claimed the name WordPress-MySQL first, and those that came afterward would have to append some sort of unique modifier. This would create a mess, not just in name uniqueness, but in manageability for you and the system administrators. This is why Kubernetes introduces namespaces. Namespaces are intended for use in environments with many users spread across multiple teams or projects. For clusters with a few or maybe tens of users, you shouldn't need to create or think about namespaces at all. You can use the default namespaces and only start using namespaces when you need the features that namespaces provide. Namespaces provide a scope and separation for names. Names of resources have to be unique within a namespace, but not across namespaces. Namespaces are a way to divide cluster resources amongst multiple users or teams. You can use resource quotas to assign how many resources each namespace can use. We'll go over this later. It is not necessary to use multiple namespaces to separate slightly different resources, such as different versions of the same software. Use namespaces for different logical organizations, projects, and the like. For example, a namespace for software development, hardware development, and human resources might make sense in a company dedicated to hardware and software development. When several users or teams share a cluster with a fixed number of nodes or resources, there may be a concern that one team or one namespace could use more than its fair share of resources, adversely affecting other users on the system. Resource quotas are a tool that you can use to address this concern. A resource quota, which is defined by creating a resource quota object, provides constraints that limit resource consumption per namespace. It can limit the quantity of objects that can be created in a namespace by type, as well as the total amount of compute resources that may be consumed by resources in that project. Resource quota is enforced on a particular namespace when there is a resource quota object created for that namespace. It's not required, but if you're going to set a resource quota, there should only be one resource quota per namespace. Let's look at an example. This resource quota is defined in a file that you can apply using the kubectl create or the kubectl apply command against a given namespace. This provides a resource quota that only allows 4 pods. Requests for CPU can only request 1 CPU at a time. Requests for memory cannot exceed 1 gigabyte. And the total usage of CPU within the namespace cannot exceed 2. And the total usage of memory in the namespace cannot exceed 2 gigabytes. Further information about the variety of limits, the types of limits that you can set, etc., is available in the Kubernetes documentation. Namespaces provide the basis for a large variety of controls which are coming in future versions of Kubernetes. For example, on the roadmap for Kubernetes development is providing access control to objects based on namespaces. That way, members of the HR team may not be able to access items in other development organizations and vice versa. Remember, namespaces aren't required. Working in the default namespace may be suitable for your needs for quite some time. However, they provide you a mechanism to think about how you can scale and grow access to your Kubernetes cluster and maintain control and reliability. Before we get started on a practical example, let's look at some useful commands for namespaces. By now, you should be able to guess what these commands might look like. Namespaces follow the same pattern for many other types of Kubernetes objects. When you create a service, a deployment, or even a persistent volume, you use a set of commands: create, get, and describe. These are the same. To create a namespace, you can use the kubectl create namespace command, specifying the namespace. After that, we'll create that namespace. You can list namespaces using the kubectl get namespace command. More information on more detailed commands to use with namespaces are available in the Kubernetes documentation. To practice with these concepts, let's examine a deployment that requests a certain amount of CPU. Let's say 20% of a CPU for each container with 3 replicas. It'll take a total of 60% of a CPU. But let's do this in a namespace that only has 40% of a CPU allocated using resource limits. You will note that we're expressing CPU usage in a unit of Ms. 200, for example, corresponds to 20% of an average defined Kubernetes CPU. 600 corresponds to 60%, and 400 corresponds to 40%. The M is what is used to denote this nomenclature. Let's see how Kubernetes will handle this situation. Going into this, if you haven't already noticed, remember and consider that across 3 replicas, we're asking for more CPU than that namespace has allocated. Consider and think about what might happen, and then watch and see if that's what actually happens. Our steps will include first, creating the namespace, which we've already discussed how to do. Number 2, assigning the namespace a 400M CPU limit. 3, deploying Tomcat as we have in the past, but with a twist that in this new namespace, and we'll deploy it into this new namespace, we'll deploy it with 3 replicas, each requesting 20% of a CPU. Then we'll use kubectl to see exactly what the deployment status was and what happened and how Kubernetes managed this. Our first step will be to create the namespace. We'll use the kubectl create namespace command, and we'll provide it the name CPU-limited-tomcat. Next, we'll assign a resource quota to this namespace. Remember, much like every other lecture, in the GitHub repository for this lecture series, under the Advanced Kubernetes Usage directory, inside the Resources and Namespace directory, you'll find all files referenced here. In this case, we'll use the kubectl create-f command to create the CPU limits defined in this file as shown here. A hard limit on CPU of 400M, which is 40% of a CPU. Remember, the new thing in this command will be the --namespace parameter. In the past, we've only created things in the default namespace. Specifying --namespace equals the name of the namespace, we'll run that command against the specified namespace. This is nomenclature used across nearly every kubectl command. Next, we'll deploy Tomcat into the same namespace. We'll use the kubectl apply command that we've used before, with the addition of the namespace flag that we just discussed. We'll also make a few changes to the Tomcat deployment from earlier in this lecture series. Let's look at them in turn. First, we specified 3 replicas. Next, in the container specification, we made sure to request 20% of a CPU for each container. Remember, this applies to each container in the pod and not overall for the pod. So in this case, given 3 replicas, ergo 3 containers, each will be requesting 200M or 20% of a CPU. Doing the math as we discussed earlier, this will create a requirement for 600M or 60% of a CPU for this deployment to be fully provisioned. Remember, we just in the last step had created a resource limitation on the namespace of 400M of CPU or 40%. Think about how the failure might occur and what it'll look like. Finally, once we've done the aforementioned steps, we'll use the kubectl describe deployment command to see what the status of the deployment is. Remember, we're applying the --namespace equals CPU-limited-tomcat command flag to our execution to ensure that we're looking at the Tomcat deployment in the proper namespace. If we had left that off, we'd be looking at the Tomcat deployment in the default namespace. This is important to understand because you can have the same name in multiple namespaces and be looking at something entirely different. Remember, we're operating in the CPU-limited-tomcat namespace, and we have to specify that to kubectl so it knows the appropriate place to look. Let's get started with the actual steps we've reviewed. We'll use the kubectl create namespace command, as we discussed, to create the CPU-limited-tomcat namespace. We'll see the namespace was created. Remember, as we mentioned before, the CPU-limits file will provide the limits for quota for this namespace. This file is available in the namespaces and resource limits subdirectory of the Advanced Kubernetes Usage directory in the GitHub repository for this lecture series. From this directory, we'll run the kubectl create-f command specifying this file. We've done this before, But now the twist is we'll add the CPU-limited-tomcat namespace flag to ensure this limitation gets applied to the proper namespace. If we neglect to do this, the command will run in the default namespace. You'll notice that the resource quota was appropriately created. We can use the kubectl get resource quota command, again applying the -- namespace flag equals CPU-limited-tomcat to see if that was applied. In this case, you can see it was created 15 seconds ago with the name compute-resources. Looks good to me. Now, let's apply the Tomcat deployment. This is the same Tomcat deployment that we've used before with a twist. Remember, it creates 3 replicas and it puts a CPU request for each of those replicas. Remember, we'll want to make sure that we don't deploy it in the default namespace. So we'll again do the CPU-limited-tomcat namespace. We'll see the deployment was created. What's important to note is that while the deployment was created, it takes a while for the containers to start. So if there was an error during deployment creation, it may not be reflected here. The only thing that might be reflected is there was a syntax error in your deployment file. If Kubernetes has a problem provisioning the nodes for whatever reason, it may not show immediately. Instead, we'll use the kubectl describe deployment command, providing the name of our deployment, and of course the namespace, because we want to be looking, again, in the right place. To see what the status of our deployment is. In this case, you can see that the deployment has failed. First, the new replica set was created, and that worked. The next check, if the minimum number of replicas are available, failed. Looking down a little bit more in the event section, you can see that it's tried to scale the replica set to 3, but it didn't create successfully. An important failure aspect to notice is that the reason it failed was minimum replicas unavailable. Instead of creating 2 out of the 3 replicas, Kubernetes failed it in an all or nothing fashion. This is important to note. We specified 3 minimum replicas in our deployment, and since Kubernetes was not able to fulfill that due to a quota that we imposed, it simply didn't create anything. Had this been a situation where we had a horizontal pod autoscaler with a minimum of 1 replica and a maximum of 5, Kubernetes would have created as many as it could up to the maximum because we had specified a minimum below what was available. This is an important aspect to note when troubleshooting Kubernetes deployments. Looking at the conditions area and the events area of the deployment can help provide you clues in troubleshooting as to what might be going on. Minimum replicas unavailable is an error code which typically points to the replicas being unavailable for some reason. One of these reasons is unavailable resources to allocate. Further information about these error codes is available in the Kubernetes documentation. This is only one example of how namespaces and resource limits can be put together to create a system that respects and enforces proper scaling and proper service availability. If you were to allow a system or a process unlimited reign of the system, it could create what's called the noisy neighbor problem. one process hogging all the resources on a system, bringing other things to a grinding halt. This is a complex area of service management well beyond the practice of Kubernetes, and it's a generic practice in the DevOps and service delivery areas of computing. We've only looked at a few methods as to how you can enforce rules in Kubernetes, consult the documentation for more advanced tools, and think about how you can apply resource limits when you're architecting your application. Using the facilities provided by namespaces, resource limits, and requests, as we've done in the example in this lecture, you will be able to create the most valuable and most relevant set of restrictions and permissions and requests to create a performant, scalable application using the tools Kubernetes provides. We've examined at how to manually evaluate usage, resources, and performance in your Kubernetes cluster. You may recall now that Heapster is monitoring our cluster. Metrics like CPU usage, memory, network, and storage by pod are being tracked. That can provide you with valuable insights into the status of your application, but that data can also be used by Kubernetes to automatically provide scaling for your application to keep it performant when resource usages spike without any intervention from you. This process and system is called auto-scaling, and Kubernetes provides a facility called the horizontal pod autoscaler to scale the number of pods in your deployment to match usage needs. So what is this highly multisyllabic thing anyway? The horizontal pod autoscaler automatically scales the number of pods in a replication controller, deployment, or replica set based on observed CPU utilization. In custom situations and scenarios, custom metrics can be provided to go beyond CPU utilization if you're willing to do a little bit of work to build a manual API. In plain English, it means that Kubernetes will scale your pod and create more pods to meet demand within certain parameters. You can either specify those parameters or until you hit the physical limit of your cluster. There are a variety of configurable options, quite a few, and you should consult the documentation for every last one. The key takeaway here is to know that HPA will create new pods or remove pods from a replica to maintain an average CPU utilization across all the pods in your application to a specified level when you create your HPA. So how do you create an HPA? Much like anything else in the world of Kubernetes, you can use kubectl using the autoscale command to provide and access the needed functions to create an HPA. For example, to create an autoscaler on our WordPress deployment that targets CPU utilization to be an average of 50% per pod or lower within the parameters of a minimum of 1 pod and up to a maximum of 10 pods, we'd use the command kubectl space autoscale space deployment space the name of the deployment, in this case WordPress, --CPU %% equals 50, --min equals 1, --max equals 10. The options should be relatively self-explanatory here. Let's consider a practical example. We'll add an HPA to enable autoscaling on our WordPress installation that we already have on our Minikube. We want to keep the CPU at 50% average or lower with a minimum of 1 pod and a maximum of 5. We'll simulate load using an infinite HTTP request loop to WordPress to spike our CPU and see how the HPA responds. Let's dive in. Before we get started on the actual parts of the practical example, let's rig the system a little bit. Because most modern CPUs and most modern laptops even possess the power to be able to serve a high amount of simultaneous requests via HTTP, we need some way to artificially limit our WordPress pod so we can stress it easily. This is also a good learning opportunity. What we will do is set a resource limit on our WordPress pod to artificially limit how much CPU each pod can consume. That will allow us to stress each pod to the point that the system artificially has to scale the CPU and scale the amount of pods to meet the compute demand. Let's examine how we'll do that first. In the lecture series' GitHub repo, in the Advanced Kubernetes Usage /autoscaling directory, you will notice a slightly modified wordpress.yml file. Let's examine it. This file should look relatively familiar to you. However, towards the end of the container specification, you'll notice a resources stanza. Under resources, it says requests CPU of only 100 M. That means 10% of a single core CPU. By severely hampering the CPU, we're able to make it such that any one pod will hit a limit quite quickly, and the horizontal autoscaler will find a need to intervene much sooner. We'll apply the slightly modified configuration using the kubectl apply -f command and specifying the WordPress deployment YAML in the autoscaling directory. We'll notice that the deployment has been configured. From here, we can move on to add an HPA to our WordPress installation. We'll use the kubectl autoscale deployment, and we'll name our deployment WordPress. Specify the CPU % target to be 50. We'll specify the minimum amount of pods to be 1, and the max to be 5. We'll notice when we see deployment WordPress autoscaled that we've successfully autoscaled our deployment. Now, let's open a new terminal window or a new terminal tab. In this tab, we'll run the process which will simulate the load. It's important to run it in a new tab so we can move in and run commands in another tab, in our existing tab and session with Kubernetes. First, let's run a basic BusyBox image. BusyBox is a utility image that will allow us to run an interactive shell. We'll use the kubectl run command with the -i and -tty flags to indicate we'd like an interactive TTY session to our new container that's running. Let's name it load generator and specify the BusyBox image. We'll specify the command to be run, and in this case, a simple shell will suffice. We're greeted with a command prompt, and we're ready to create an infinite loop to stress our WordPress instance. Let's write a simple bash script. While true, condition that should always be true. Let's use the wget command, which simply issues an HTTP GET to the URL of our WordPress instance on our local Kubernetes cluster using the well-known DNS name that we've spoken about earlier. Executing this command should start putting load in our instance. Let's go back to our other command window and use the kubectl get HPA command to see the status of our current WordPress HPA. At the moment, it has a minimum of 1 pod and a maximum of 5 with 1 replica. It might take about a minute or two for load to start increasing on our server and for HPA to have to respond. Let's give it a little bit. After a moment or two, we'll notice that the CPU usage has spiked quite a bit. You can see replicas has gone up to 2. The horizontal pod autoscaler has responded to increased CPU usage by horizontally scaling our pods. If your machine happens to be quite fast or quite efficient, you may need to run more than 1 load generator. You'll notice I've started 2 extra ones to simulate enough load to actually spike the CPU usage. This will vary machine by machine. The horizontal pod autoscaler in Kubernetes provides you with sophisticated facilities to do a variety of things to keep your applications performant and serviceable. Since it leverages existing metrics and systems within Kubernetes and builds upon previous functionality, this is actually relatively simple to do. You'll notice we were able to accomplish it using a few simple commands. The most complicated part of the example was arguably the fact of having to artificially hamper the CPU usage of a given pod just to be able to demonstrate the capability. Otherwise, attaching an autoscaler was relatively easy. When you think about architecting and deploying applications, consider how you can scale horizontally to meet the need, instead of throwing more hardware or more expensive hardware at a scale problem. Kubernetes makes this possible quite easily. In nearly any production computer system, an important aspect of operations is security and auditing. Auditing in the context of computer systems in production use typically refers to understanding what has gone on, how it happened, where it happened, and who or what caused an event to happen. An important aspect of auditing is that the auditing process be safe from either unintentional or intentional interference by individuals who aren't authorized to look at or change the records that the auditing process keeps. Outside the computing world, auditing in a bank, for example, looks to make sure that the bank employees did what they were supposed to do. And if there's ever a question, there is a record which can be relied upon and trusted to reflect what actually happened, to either investigate malfeasance, intentional malicious behavior, or simple mistakes. Kubernetes is the same. Since Kubernetes provides a framework for running all kinds of workloads, which may require the same level of audit capability, Kubernetes provides an auditing facility. There are two types of auditing in Kubernetes: legacy auditing, which was sunset in Kubernetes version 1.7, and advanced auditing, introduced in 1.8, and the standard audit and default audit system in 1.8 and beyond. We'll only consider advanced auditing, and we'll only refer to it as auditing as that is how it will be in future versions of Kubernetes. So what is Kubernetes auditing? As we mentioned, Kubernetes provides security-relevant, chronological sets of records documenting the sequence of activities to help answer a variety of questions. The Kuba API service process performs the auditing and accounting. This is a little different from everything we've discussed to date. Most of the actions we've taken, like creating a service, creating a deployment, creating a horizontal pod autoscaler, or any other number of activities, have been done inside the Kubernetes framework in your cluster. They've been executed as processes running inside Kubernetes. However, auditing is important from a security perspective and needs to remain secure. So the auditing process happens at a lower level that cannot be accessed by the kubectl runtime or pods running inside Kubernetes. This is important to understand when we actually go to set up auditing. The Kuba API server is what provides the auditing functionality, and it's configured from outside the cluster. Remember, much like you wouldn't want an internal auditor in a bank to be the only source of data and trust, because they might be easily corrupted. An external audit process or an external auditor is used to ensure that there's the appropriate controls in place, that the audit record is not altered. Same thing here. Kubernetes auditing can be broken down into two large areas of concern. The first is the audit policy. The audit policy defines what should be logged. Should we keep a record of every last thing that happens on the system, or are we only interested in logging a few items? Where you fall on the spectrum likely is influenced by what your compliance needs are, either legally or from a business perspective, or what you'd like to log. The audit policy is defined in a .yaml file like any other Kubernetes object, But as we mentioned earlier, since this is auditing, it needs to happen outside the framework of the normal Kubernetes tools so that normal administrators and system users without access to certain parts of the system cannot alter the audit process, either inadvertently or intentionally. Auditing is defined in the Kube API server, as we mentioned, and it's an option that's passed to the API server when it starts. So the commands that start up your kubectl and your Kubernetes cluster is where we need to specify the audit policy. We can't do it once it's already started for reasons of security and integrity. This varies by various cloud providers and how you set up your production Kube cluster. We won't really go into that right now since we're using Minikube. Luckily, we'll just pass a few options when we start Minikube, the same options that we might pass to our provider in a production environment to enable and see how auditing works on our local machines. Nearly anything you can create or do can be audited in Kubernetes. Setting the policy restricts what is audited and how. The second part of auditing is the audit backend. Once you define what you would like to audit, the backend handles where that audit information is stored. Audit backends can range in sophistication, and you can have custom backends to send information to nearly any system. A variety of external compliance systems exist, and Kubernetes can send events to these external compliance systems. But out of the box, Kube API server, the process in Kubernetes that enforces auditing, provides two backends. First, logs, essentially writes events to disk, or in the case of Minikube, you can even write it to your screen. Or webhooks. Webhooks send events to an external API or system for storage. This provides a gateway and a pathway for compatibility with a wide variety of external systems that save logs, audit logs, or send them to other systems for compliance. Let's look at a practical example. First, we'll set up a simple audit policy to log all requests regarding metadata. That meaning data about systems and processes running in Kubernetes. This will let us see what audit data looks like without having overload. Since you can audit any number of events, and hundreds of thousands of events might occur per second in a production Kubernetes cluster, we won't want to necessarily be drinking out of a fire hose. So let's just look at something modest like metadata. We'll configure Minikube to log it to a file on our system or the screen in our laptop. Our steps to do this is, number one, we'll stop Minikube if it's already running because we need to affect changes to how Minikube starts up. We'll define our audit policy, and then we'll start Minikube pointed to the audit policy and the appropriate options to make sure that it deploys a audit backend to save the data to a file or to our screen. Let's get started. Remember, just like in previous lectures, all the files that we reference are available in the GitHub repository for this lecture series. In the Advanced Kubernetes Usage /auditing directory, you can find the files that we'll reference in this demonstration. If you haven't already, or if it's not running, make sure you stop Minikube using the Minikube stop command. On my system, Minikube is already stopped, so it happened relatively quickly. It may take a little bit longer on your system. Pause and come back once it's stopped. It's important to stop Minikube because we need to change how Minikube starts. We need to set a variety of options at runtime to enable auditing. In a production system, this is going to vary based on what operating system your cluster is running on or what cloud provider it's running on. Since it has to do with how the Kubernetes cluster is started, this varies configuration by configuration. In a production system, consult your design documentation or your cloud service provider's documentation as to how you'd set these options. With Minikube, we simply pass a variety of command line options to the Minikube process when we do Minikube start in order to pass the options to enable auditing and specify what we would like to audit, the audit policy, and where we would like the audit information to go, the audit backend. First, it's important that we copy the audit policy file to a place that Minikube has access to it. The audit policy.yaml file specifies a very simple audit policy to audit metadata actions. metadata actions, meaning anything that has to do with information in the kubectl command set. Anything against the API server which is accessing metadata. For example, information about pods. You can audit any variety of information in Kubernetes, and you can consult the Kubernetes documentation for a full list of things you can audit. Let's have a look at the auditpolicy.yaml file. You can see that it's relatively simple. It defines a type of object, policy, with one rule: to audit anything at the metadata level. Remember, you can audit a blindingly large amount of data points in Kubernetes. We chose only auditing metadata to keep the amount of data low and useful. Let's copy this audit policy file to an appropriate place where Minikube can access it. Minikube stores its configuration in the user's home directory, the tilde. That stands for the user's home directory, .minikube /addons directory. This directory is mounted to the virtual machine that's running Minikube on your system. Any files here will be accessible by the Kubernetes processes running in the virtual machine, which are your Minikube. So let's copy the audit policy here, so that way we can tell Minikube when it starts up to expect the audit policy file in that area, which is accessible to all processes running inside our Minikube. Don't quite start the Minikube command yet, because we need to use a special Minikube start command that's specifying a variety of command line options, so Minikube understands to turn on auditing, what to audit, and where to audit it to. This command is a little verbose to say the least, meaning it's a little long. So I've provided a shell script that you can run that will do it for you. Instead of just trusting that the shell script has it right, let's actually look at the shell script and run the command manually. Let's use the cat command to look at the Minikube start with audit.sh shell script. You'll see that it starts off relatively predictably, Minikube start. But we're providing 3 specific command line options to Minikube using the --extra--config parameter to tell Minikube a few things to communicate to the API server. First, we're telling it to turn on an authorization mode called RBAC. You don't need to worry about this right now. Just consider and know that that's a requirement and a prerequisite of auditing functioning properly. Secondly, we're telling the API server a log option path. That's basically where do you want the log to be stored on the system and the virtual machine running Minikube. /var/logs/audit.log is what we've chosen. The final option is important. It tells Kubernetes and Minikube where it can access any extra configurations, items such as our audit policy. In this case, /etc/kubernetes/addons/audit-policy.yaml is the policy file that we just copied into the addons directory in the Minikube configuration file. This is mounted in the Minikube virtual machine at /etc/kubernetes. Running this command will start Kubernetes in Minikube with auditing enabled, logging items that match the audit policy that we defined, and saving it to /var/logs/audit.log on the machine running Kubernetes. Let's issue this command. Since you have to get it right the first time, I recommend cutting and pasting it. It may take a moment for Minikube to start up, so let's wait until Minikube has successfully started up and we have control of our shell yet again. Now that Minikube is running, let's use kubectl to get some kind of information that will trigger an event which requires auditing. kubectl get pods will do exactly that. Because we're getting information about something on the system, it'll generate a metadata event. This gave us information about the pods running on our Minikube. Now, how do we actually look at this log data? We'll have to use the Minikube SSH command to SSH, or create a secure shell connection, into the machine running Minikube. This is a virtual machine that's running on the machine that we're logged into right now. This connects us into Minikube, and you'll remember the parameter that we passed into Minikube when we started it told Minikube to store the data in /var/logs/audit.log. Let's assume super user command and authority using sudo space bash, so we have permissions to read this file. Now, let's navigate to /var/logs. Let's use the cat command to look at audit.log. As you can see, there are a variety of messages in JSON format, which is a format that's used through a variety of web services and systems, logging a whole variety of data that has happened to this point relating to metadata. We can scroll through this data and begin to see that there are events which are talking about any number of actions against metadata. This information logs anything against metadata that has happened since we enabled auditing. Of course, this isn't very useful for human consumption, but that typically isn't the use case. Usually auditing data needs to be sent to an entirely separate compliance system, which will actually enjoy this highly structured data that you see here. So we can look at it in a little cleaner fashion. Let's use the JQ command, which formats JSON data. This is available on nearly any Linux or Mac system and is installed by default on the Minikube system. So let's use the cat audit.log and let's pipe it to JQ, telling it to format each line. The period will do that. Don't worry about this format. This is a command which is outside the scope of Kubernetes, a utility for manipulating JSON data that you don't really need to know about. It's a convenience so we can understand the data put to us in better formatting. You can see it's putting the log on our console with a whole lot more formatting and coloring in a human, readable, and friendly fashion. Scrolling through this data, you can see that a variety of actions have been taken in just the last few minutes. The variety of Kubernetes processes running in Minikube are accessing data and listing data to start all the pods when we started Minikube. There's a lot of data here, but if we scroll through it, we'll notice a few events of interest. For example, if we scroll through, we'll notice that the system made a request to examine persistent volumes. This happened as we were starting Minikube. Kubernetes needed to know what persistent volumes were available to fulfill a persistent volume claim. You'll notice in this case, the request was received at a given time. In this case, you'll have to trust me that that was a few minutes ago. And what object it worked against. A persistent volume claim with this identifier. If we'd like to know more about it, we could copy this identifier and use the kubectl command to list information about that. If we continue to scroll down, you'll see the response was completed and sent back to the source IP 127.0.0.1. In that case, we know that the response originated and ended on our local system. It was the Kubernetes processes running in Minikube that wanted information about this given resource. That's the purpose of auditing, to answer and know conclusively what's happening on your system, by who, and when. In this case, we're able to see that a given process asked for data and introspected data at a given time. Think of it as an incredibly detailed access log. Let's log out of our superuser shell using the exit command. Let's log out of our minikube SSH session using the exit command. This is just the beginning of auditing and logging. You can audit many more points by looking through the Kubernetes documentation and seeing specifically what options are available to log. You can log much more than metadata. You can log actions, etc., and create sophisticated rules to only log certain namespaces or certain pods or certain actions to get only the data that you like and nothing more and nothing less. Secondly, there's a variety of ways that you can send the log data to systems which can process it in an automated fashion or present it for your consumption or your auditor's consumption or store it in a compliant manner however you would need according to data retention policies. Examine the documentation for Kubernetes and whatever third-party systems you might be using to store and analyze log data as to how you can integrate them. You'll still use the same framework of audit policies and audit backends to achieve a variety of system configurations to meet your needs or the needs of the applications you might run. You've probably heard the adage that any chain is only as strong as its weakest link. And perhaps you've even experienced this in technology, that no matter how robust and well-written your application, if the systems upon which your applications are running are unreliable, or perhaps even deeper down, the power, cooling, or the buildings hosting them are unreliable, the full stack simply doesn't work or doesn't work properly. Similarly, deployments running on Kubernetes are no different. They're only as reliable as Kubernetes itself. The same applies to the various components that make up Kubernetes. We've talked about masters, nodes, Kupa API, and the like. These are some of the components that make up Kubernetes and its internal control plane. Without them, or without them functioning properly, applications running on Kubernetes simply won't function properly, or won't perform to the standards that we expect them to. Just like any other software system, Kubernetes components can fail, either because the underlying hardware, network, or software they are running upon experience an issue, or the process itself has some sort of fault or bug. In order to create a system that is resilient in light of failure of any one component, or depending on the configuration, perhaps even multiple failures of multiple components, Kubernetes is architected and provides facilities for redundancy, replication, and graceful handling of faults within its system. These together are considered the high availability portions of Kubernetes. We'll discuss a few aspects of this in this lecture, and we'll look at actually implementing them in future lectures. Keep in mind, this is an area of increasing development and focus in Kubernetes. It's not 100% complete, but it's quite mature. The high availability features are continually being added upon, but the core feature set is complete and focuses on replicating Kubernetes' key infrastructure components to provide a scalable, resilient, and robust system for almost any use case. Kubernetes itself is comprised of many components, and many of them you don't even need to know about, even if you were a Kubernetes system developer. For the purposes of understanding high availability, however, let's review a few of the key components that relate to creating highly available Kubernetes clusters. First, the Kubernetes master is a machine running 3 processes on a node in the cluster, or at least 3 processes. These processes are the Kuba API server, the Kuba controller manager, and the Kuba scheduler. Second, etcd is a consistent and highly available distributed key store that stores all cluster data. etcd itself actually isn't provided or even maintained by the Kubernetes project. It's a separate data store, a separate key value database that Kubernetes uses to store its data, because it has solved the problem of having a fast, scalable, distributed data store, and Kubernetes didn't want to reinvent the wheel. Much like WordPress uses MySQL as a database, Kubernetes uses etcd as the database for master data. etcd can run on its own machines or on the master machines. However, it's important to run etcd on its own, and it's not recommended to run it on the same machines that are running the master. Many things can go wrong in any system. No system is completely infallible, but the design of Kubernetes is laid out with the intention to provide resiliency and redundancy at most points, and it is continuing to evolve. Currently, highly available masters in Kubernetes are accomplished by 4 key things for the master and Kubernetes control plane side of things, and then ensuring we have multiple worker nodes as well. We'll walk through each step 1 through 4, and in a later lecture, we'll use Kubernetes tooling to set up a highly available cluster, and then we'll look at step 5 to set up multiple worker nodes as well. But for now, we'll just discuss each step at a high level to lay the foundation of an understanding for demos in further lectures. First, creating reliable nodes that together can form a highly available master implementation is where we start. These are the actual Linux machines upon which our masters or etcd will actually run. Second, we'll set up a redundant, reliable storage layer with a clustered etcd implementation. Third, we'll start replicated, load-balanced API servers. Fourth, we'll set up master-elected Kuba scheduler and Kuba controller manager daemons. Each of these steps sounds really daunting, I'm sure, and probably has things you don't understand. We'll go over each one of them in a moment and what it means. And rest assured that Kubernetes provides us with a set of tools called KOPS, K-O-P-S, that will provide a level of automation in setting up and managing each one of these, while you could manually go and create the configuration files needed for each one of these. Kubernetes provides a suite of tools called KOPS, K-O-P-S, that provides a higher level command line interface to a lot of the tasks required to write configuration files and maintain them. This provides an interface which reduces errors and can make you more efficient and automated if you choose to use them. But understanding what steps the tools are taking is an important part of learning, so we'll go over each one. First, let's look at setting up a reliable system. Up to this point, we've worked with a minikube, where the master processes and node workers all work on the same machine. If that machine lost power, restarts, or is thrown out of a window into a pool, everything fails. In simple Kubernetes clusters, while there is a master and some nodes, if the master fails, e.g. the data center it's in goes down or it loses power or connectivity, the cluster will cease to function no matter how many worker nodes there are. In highly available systems, depending on the number of masters, even if individual masters and the machines running those masters fail, other masters can take over and provide the services of processes running on the master. One can build highly available systems with any degree of resiliency. Depending on how many masters and instances of etcd are created, a certain number of failures can be tolerated. For example, ensuring these systems are as physically separated and independent as possible is important. It is of little use if all of these machines are flooded in the same storm, are burned in the same fire, or lose connectivity because of the same fiber cut in a fiber optic line leaving town. Understanding what the variety of failures can be and choosing which ones you'd like to design and hedge against is important in understanding what architecture you should create. In this diagram, we can see the variety of facilities available to us in creating a redundant system. Multiple worker nodes and multiple master nodes which live behind a load balancer are what creates a variety of the high availability systems in Kubernetes. You can create multiple master nodes in different parts of the country so that if an internet line is cut, a fiber optic line is compromised, and a given city might have connectivity issues, only the master in that city is affected, and other masters in other parts of the country might be able to take over. Similarly, a natural disaster in one area that might knock a data center offline doesn't have to affect your worker nodes or your client applications because the load balancer detects that master node being gone and begins to send requests to other ones. Let's look at how that gets created. Remember the 4 steps. The first being reliable nodes for our masters. Each machine should be separated and single points of failure removed as much as is reasonable for your needs. You may not need to have masters located in every major metro area in every country where you want to run your application, or you may decide that that's important. That's a choice that you have to make based on the needs of your application or your business. This will vary based on the amount of redundancy you really need or are trying to accomplish. For example, it may be okay for you to have each machine in the same city if surviving a catastrophe that isolates your entire city isn't important or considered so low probability, it isn't worth protecting against. Remember, everything we do when it relates to machines and technology might have a cost associated with operating it. Running 10 masters usually costs 10 times as much as running one. And distributing them across multiple geographic data centers usually incurs some sort of cost of bandwidth for them to all communicate. Understanding your needs and mating this up against complexity and cost is an important exercise of design and architecture of high availability. For now, just know that creating reliable nodes is an important basis point for everything we'll do here on out. Secondly, we need to create a reliable data storage layer. etcd is a system that is a study in and of itself. It's something built entirely separate from Kubernetes and maintained separately. Kubernetes uses it much like WordPress uses MySQL as a data store that is built and managed by an entirely different development organization. etcd itself has redundancy options well beyond the defaults that are typically used by the Kubernetes deployment tools that we'll use. If you need this, explore the etcd documentation or consult an etcd expert on how to further tune your etcd deployment that is created for you by the Kubernetes tools. It's completely outside the scope of Kubernetes as it's a different software system and could be an area that it provides months of work and study on its own. Examine these options if you need them, but for most applications you won't. The next step is having replicated API servers. Kuba API is a key process on the master, and as such it should run on all masters. Since clients need access to the Kuba API processes, for example, kubectl, the command line tool that you've been using to access information about your cluster, modify deployments, create deployments, accesses the Kuba API process on the master. A load balancer in front of the machines that are making up the masters is critical to ensure this process is exposed properly, and requests from applications like kubectl are routed to an available master. Setting up load balancers varies. It exists outside the scope of Kubernetes. And Kubernetes doesn't provide a load balancer facility in and of itself, although it does provide facilities for managing them. We'll use a load balancer provided by Amazon Web Services called the Elastic Load Balancer Service in further lectures to create replicated API servers. This varies depending on where your chosen deployment is. Next, and finally, we'll need to make sure that the masters which you set up can speak to one another and elect who's going to be the active master. Now that items are actually set up on reliable nodes, we have the pieces in place, but they actually aren't running. We need to ensure that only one actor works in the data at a given time. This is the too many cooks in the kitchen who aren't talking to each other problem you might have if you, for example, were trying to cook a meal with multiple cooks. There would have to be some level of coordination between who's doing what. Each scheduler and controller manager will be started with a leader elect flag. That will use something called a lease lock API between themselves to ensure only one instance of each is running or active at a given time. In plain terms, that means the masters which are up and running and healthy will communicate with each other and decide who's going to speak for the cluster. They'll use a specific algorithm and a specific protocol to do it amongst each other, and when one goes away, the process will be repeated. There's specific documentation available on how this works and the details of the process. If you'd like to understand more about it, consult the Kubernetes design documentation available in the Kubernetes GitHub repository. For now, and for most purposes, simply understand that there is some level of communication between the masters which is handled through etcd. All this comes together to create a robust, high available architecture to ensure that we have multiple worker nodes in a variety of availability zones to create a system that can withstand the kinds of failures that you decide might disrupt your application. In further lectures, we'll go through the process of setting these up. For now, even if you don't understand the exact details of how this happens, and it's not expected that you should, understand and be comfortable with what happens in this diagram when one master might go away. For example, if master node number 1 were to experience a failure, the load balancer would take any incoming request from worker nodes or kubectl and route it to a master which is actually working, using standard load balancer functions. When that master comes back up, the load balancer might begin sending it requests if it is chosen as the active master. Understanding what happens and how multiple masters work together and what happens on a master is important. How each of these happen and the individual details of the processes are less important, although we'll go into them in further lectures. For now, just think about how this diagram works when multiple masters exist and what happens when a master might go away. In the previous lecture, we discussed setting up multiple masters as a key aspect of high availability in Kubernetes. Let's look a bit more into the master, what it does and how it does it, so we get a better understanding of what this key component of Kubernetes, and especially highly available Kubernetes, actually does. Kubernetes masters, as we discussed, typically run 3 key processes. They may run more, but they at least run these 3. Number 1, a Kuba API server. Number 2, a Kuba controller manager. And number 3, a Kuba scheduler. These processes access and rely on etcd. Remember from the previous lecture that etcd is a distributed key store that stores the data about the cluster that these services might need to use. To take a look at a master, we're going to need something bigger than a Minikube. Remember from earlier in this lecture series that Minikube packages the Kubernetes software into something that's convenient to run on a single machine. This makes some compromises to provide that ease of access to the Kubernetes software. One of these compromises is that a master is running in the same process on the same machine as the worker nodes and a variety of other items required to run the Kubernetes cluster. Examining the master is going to be difficult if it's all on the same machine. So we'll take this opportunity to set up a Kubernetes cluster on Amazon Web Services. This will be an actual Kubernetes cluster on a cloud computing provider. You'll need an AWS account. Don't worry if you don't have one, we'll show you where you can create one. If you already have one, you can use that. Regardless, there are a few things that we'd like you to know. First, AWS, or Amazon Web Services, is a cloud computing provider that provides access to virtual servers, along with a variety of managed services ranging from object storage to DNS databases and beyond. AWS accounts are free to set up, although they do require a credit card, but are not necessarily always free to use. This is important to understand. Even though they provide a free tier, setting up a Kubernetes cluster like we're going to do on AWS does not fit inside this usage allowance. It will incur costs to you, depending on how long you leave it running. Amazon sells the use of their services, virtual machines, networks, etc., based on how long you use them and how much you use them. There will be a cost associated with it, and make sure that you know that your account is set up and authorized to incur that spend, and that you're willing to do so. So unless you're prepared to accrue and pay these charges, and you're confident that you'll able to properly stop and release all the cost incurring resources, you may want to consider just watching and following along. The choice is up to you. About an hour's worth of use at current prices for what we're going to demonstrate would cost around $10, but that's not a guarantee. And make sure that you know how to track costs if that's something that's important to you. You can set up an account at www.amazonaws.com or log into your existing one. Once you have an account or using your existing one, we'll log in and we'll grab a few important security credentials we need to set up our Kubernetes cluster. Regardless of whether you need to set up an account or log into your existing one, let's begin by going to www.amazonaws.com in a web browser. Whether you need to create a new account or log into an existing one, http://aws.amazon.com is your starting point. Let's click Sign into the console. Whether we need to create a new account or log into an existing one, we can do that here. If you want to create a new account, click the Create a New AWS Account button. It will collect some information, including your credit card and email address. You'll have to verify your email address by clicking on a link they'll send you in an email. At that point, your AWS account should be ready to use, and you can come back after you've paused this video. If you have some problems signing up, Amazon offers support throughout the process by clicking any of the help buttons or replying to the emails that you get to verify your account. If you already have an account or you're returning from the sign-up process, let's log into our account by entering the email address, clicking Next, and typing in our password. Once you've completed that, you'll be logged into the console. The AWS Management Console provides access to nearly every Amazon product and service. As we mentioned earlier, AWS provides a wide gamut of services that are well beyond the scope of setting up Kubernetes. If this looks a little daunting to you, don't worry. We're only going to use a few services, and we'll walk through each of them independently as we use them. This console can provide you with access to the full breadth of services, and if you'd like to explore it, feel free. For our purposes, we're going to focus only on the EC2, or the Elastic Computing Cloud service, and the Amazon S3 service, the Simple Storage service, which provides a storage service accessible easily for applications running on and off Amazon's cloud. Since we're going to use the COPS toolset to create our Kubernetes cluster, we won't need to access the management interface for too many tasks. However, what we will need to do to provide the COPS toolset with access to our Amazon account is download some security credentials, which uniquely identify our account and allow us to securely communicate with AWS's API. To do this, let's go into the upper right-hand corner where our name is and go to My Security Credentials. If you receive a warning message, which you might if you're logging in from the root account that you've created, which is the default, click Continue to Security Credentials. This warning message is for production customers running large Amazon Web Services deployments in an organization with needs to have segmented roles and applications using the IAM product. For now, accessing using our root credentials is exactly what we would like to do. From here, click the Access Keys button. We'd like to create an access key, which we'll share with the AWS command line tools that we'll install on our system, so that those tools can be used by COPS to create instances and provision our Kubernetes cluster. Click Create New Access Key. Click Show Access Key, and note these values down. You can copy them to the clipboard and save them in a password manager of your choice. You can print them, or you can click a download key file to download the file to your machine. We'll need both of these values exactly over the course of the next lecture and this lecture to be able to access our cluster. They will only be displayed once, so make sure that you copy them down and store them in a secure place, as these offer full access to your Amazon AWS account. Now that we have an Amazon.com AWS account set up and some security credentials created, let's set up a simple cluster on AWS. Just like anything in the cloud computing world, you have a bit of choice in how much you'd like to do manually or how much you'd like to buy pre-built from a given solution provider. Amazon provides Kubernetes clusters out of the box now. It's their service called the Elastic Kubernetes service. They manage all of the redundancy and high availability items of your master and etcd for you. The setup is highly automated and very friendly. It's definitely production grade. However, because it is so simple to use, it doesn't give us the experience of setting up our own cluster and introspecting the various parts of it. So we'll use COPS, KOPS, a suite of software provided by Kubernetes maintainers to do a bit more of the manual work to set up our own cluster. Now, we could manually set up each Linux node from scratch and manually edit countless text files, Or on the other extreme, we could buy a cluster set up for us using the Elastic Kubernetes service. However, using kops will provide us with a happy balance between the two. It will give us the flexibility to look at and specify things about our masters and actually interact with our masters once it's set up that other services may not let us do. They may hide those details from us, but at the same time, it'll take a lot of the manual drudgery of having to set up manual configuration files and upload them and set up a base Linux system and automate that for us, because those are largely outside the scope of this lecture anyway. It'll allow us to focus our time and our energy on learning the key parts of Kubernetes, so we'll use kops. Doing this has a few key steps. First, we'll download and install kops on our local machine. Next, we'll download and configure and install the AWS command line tool suite. We'll also use the security credential we just created so AWS knows what account to create our resources in. The kops toolset will rely on some of the AWS toolsets and APIs to create resources for us so we don't have to do things like spin up our own Linux instances. Then we'll create an AWS S3 bucket, which is Amazon's block and object storage facility, as a state store. That will store the state of our cluster, what the machines are, how they're configured, etc. Finally, we'll create the cluster using kops. Let's get started. Our first step is to download and install kops on our local machine. Depending on your configuration and the type of system you're using, we'll have to install kops using a package manager or manually. To get the latest version of kops, let's go to Google and find the kops GitHub repository by searching for Kubernetes space KOPS. In this case, the first hit is the appropriate one, the GitHub page for Kubernetes kops. If we scroll down, the install instructions are available in the README file. On a Mac OS system, you can use the brew package manager as described here to install the kops binaries. This is the preferred and easiest way to make sure that it's properly installed and up to date. On Linux systems, you can use the following commands to download the latest version and install it and make it available for use. Both of these methods should simply, with one run of the respective commands, create a working kops install. No other configuration is required at this step. Whether you're running an OS X or a Linux system, run the commands, and they should return successfully, and we'll continue. For example, on a Linux system, let's copy the 3 commands to the clipboard by selecting them, copying them to the clipboard, going to our terminal, and pasting the commands. This will download the kops toolset. Depending on the speed of your connection, this may take a moment. It will then unpack the tools, make them executable, and copy them into a common area in the path. Typing kops should give us the help screen for kops. We know it's successfully installed. We'll configure it to access Amazon AWS in the next step. It should be noted that kops was natively developed for Linux and OS X. Windows support was introduced in mid-2010 and is claimed to be working, but remains highly experimental and relatively undocumented. You can search the kops GitHub repository for Windows support if you're adventurous. There are a few notes on the GitHub issue as to kops.exe working. However, the documentation as of now was relatively sparse and it's not recommended. Cygwin and the Windows Linux subsystem are untested and unrecommended. Again, however, if you're adventurous and familiar with these tools, you may want to try running kops under these Linux emulation or substitution systems in Windows, but there's been no guarantee and there is no official support. If you'd like to run kops on a Windows machine and don't want to be that adventurous, it's suggested to run a Linux VM on your Windows machine and follow the Linux instructions for kops and for the AWS toolkit in the next step inside the established virtual machine. You have a few options here. VirtualBox is free and well documented. By Googling VirtualBox and going to the VirtualBox website, you can download a free piece of software that will run a Linux virtual machine and has step-by-step instructions on how to establish it. There's a relatively large community, and this has been done by many people in the Kubernetes community, so your support options are pretty strong. Hyper-V is Microsoft's virtual solution available on some Windows platforms. As an included Microsoft technology, of course, it offers great support. However, documentation on this route doesn't appear to be as voluminous as setting up a Linux VM on VirtualBox. There are other commercial options also available. Evaluate which one might be best for you and search the documentation to set up a Linux virtual machine. A recent version of Ubuntu Linux is likely to be the most well supported for the kops toolset. However, if you're familiar with a different Linux distribution or have a different Linux distribution available on your machine already, feel free to use that as well and follow the Linux instructions for both the kops toolset and the upcoming step for AWS. Now that we've set up and installed kops, let's do the same for the AWS command line tool suite that we will need to access and create resources on Amazon AWS. Let's take a similar approach to installing the AWS command line tools. Since systems vary, let's go to Google and consult Amazon's documentation for installing their toolset. You can Google any search terms, of course, but the most precise would be something like AWS command line tool install. Let's see what that gets us. Your mileage might vary, but in this case, the official documentation from Amazon AWS is probably the best bet. Let's click on it. This documentation changes from time to time, so it might look a little bit different. However, the general idea is likely very much the same. The default instructions require Python installed in your system. If you're experienced with the command line use and are comfortable using these instructions, go ahead, assuming that you know that you have Python installed. To be safe, we can also use AWS's bundled installer. This doesn't require Python, and if you're unsure if you have Python installed or don't know what that means, click Try the Bundled Installer. Next, let's go to the Install the AWS CLI using the Bundled Installer section. We'll follow these directions in order to install it properly. If you're on Mac OS and you have Homebrew installed, you can also use the brew install AWS command if you'd like and are comfortable with that. The first step is to download the AWS CLI bundle. Let's do that. Depending on your connection speed, this may take a moment. Once it's downloaded, let's use the next command to unzip it. Next, let's run the install executable. Depending on the speed of your system, this may take a moment. Once this is complete, you can run the AWS command to ensure it was installed properly. We should see the help screen when typing AWS. Now we're ready to configure AWS with the security credentials we created earlier so it can connect to AWS's API on our behalf. COPS will use the AWS command line tool, and we will directly use the AWS command line tool to provision and configure resources to create our Kubernetes cluster, so it needs to know how to access our account. Let's type AWS space configure. At this point, AWS is asking for the security information which we previously created. It's asking for the AWS access key ID. Remember when you created this earlier in the lecture? Cut and paste or type in the access key identically from that earlier step. Once you're sure that it's the proper value, press enter. Now, let's enter our secret access key. Remember, these values give full access to your AWS account. Keep them secure, not like I'm doing here and publishing them for the world to see. These credentials were simply created as an example and have been disabled. Now it's asking for a default region name. This is important to consider. As we've talked about in creating redundant systems, where you create your resources matters. Different regions provide different isolation levels. Creating a server in one region and another region hopefully makes both servers immune from any one event which might take them down, like a power outage or loss of network connectivity. AWS provides a variety of regions all across the world. For a full listing of these, you could consult Google by looking at or searching for AWS regions and availability. Looking at the regions and availability zones document, you should be able to choose one which is optimal for your needs. Remember, regions and availability vary service by service. In this case, the first Google hit referred to the relational database service. This just gives you an idea of what region strings are available. The one nearest to me happens to be the US West 1 region. However, remember, pricing may vary region by region, so in making your decision, consult the pricing tables to ensure that you choose a region near you that fits your cost needs. US West 1 is a little bit more expensive, so I'm going to choose US West 2. You can always choose a different region when you're issuing a command. This is simply the default if you don't specify one. We don't need to specify an output format. AWS should now be configured. Now that COPS and AWS are installed, let's create an AWS bucket that we can use as a state store. A state store is simply where information about our cluster that COPS needs to be able to operate is stored. S3, again, is an object store. It allows us to create files, store them in a bucket in the cloud, and have anyone who has access to those resources write and read them in a reliable, consistent fashion from anywhere that has internet connectivity that we've allowed to do that. There are many ways to create an S3 bucket, but the most convenient is to use the AWS command line tool. You can also use the web interface, which is also convenient. However, we'll use the command line tool to make sure that we keep everything in one place and are able to simply do everything from a command line. We'll type AWS, which is the toolset we just configured, and we'll type S3 API as the next parameter to indicate that we'd like to access the S3 API. Then we're going to type create-bucket, as that's the command we'd like to issue. Next, we'll use the --bucket flag to indicate the name of a bucket. Bucket names must be globally unique. That means if anyone has already chosen a bucket name you're trying to use, it will fail. A good rule of thumb is to ensure that you use your name, your organization's name, or something highly unique when creating bucket names. This will be globally viewable. So don't use anything you'd like to keep secure or something that might be embarrassing. I'll use bosith-k8s-demo-bucket for mine. Let's specify a region using the --region flag. You can use whatever you'd like, but to keep it consistent, let's just use the one that we had used earlier when we were specifying and configuring the AWS command line tools. I used us-west-2. Then we'll have to provide a create bucket configuration item, which further indicates this location constraint. Using the location constraint option equals the name of the bucket again, or the name of the region in which you're creating the bucket again. Press enter. This may take a moment. The bucket is being created. You can see that the output indicates that the location of our bucket is a URL with the bucket name .s3.amazonaws.com. This indicates successful creation of the bucket. You may get a user message or an error message which indicates your name is already taken. If so, change your name and try again until you see successful completion like this. Our bucket has now been created. Now that we have the groundwork laid, with kops installed, AWS working, and a bucket created to store information about the cluster we're about to create, let's actually create the cluster using kops. Now that we have a state store created where kops can store critical information about our cluster in S3, a globally available, highly reliable storage service, we can now create a cluster. The first step to doing that is making sure that kops knows where the state store is. We'll set an environment variable where the kops tools expect it to be. To do this, let's type export, and in all capitals, kops _ state _ store equals s3:// and the name of the bucket that you created. We only want to copy the name of the bucket and nothing else in that URL. Press enter, and the environment variable is set. Now we can use the kops tools to create a cluster. We'll type kops create cluster, a relatively obvious command, and then we'll provide the name of the cluster. This doesn't have to be unique globally, only unique within your AWS account. I'll choose bosith-k8s-demo.k8s.local. Next, we'll provide the --zones flag. Choose the zone and the region that you had already chosen for your S3 bucket and is your default. We'll type US-west-2. But because this is a zone and not a region, we have to provide a letter after it. Within all AWS regions are separate zones. These are simply, you can think of them as separate data centers within a given zone. They provide fault tolerance and isolation of power, network, and other aspects of availability. Each zone has a variety and a different number of availability zones. They start with the letter A and run through however many are set up in that given region. You can consult the documentation, which we looked at earlier, to see how many availability zones exist in your given region. However, it's a safe bet that an A exists in nearly every region. So let's just go ahead and choose A. We'll specify the --yes flag. This way, it won't prompt us to create resources every single time. Let's press enter to get going. This will take a moment. Quite a few things are going on here. kops is using the AWS command line. If your SSH configuration error occurs, this is normal and may happen in certain situations. If you receive an error like this, It simply means that you don't have a public key created by default. We'll use the ssh-keygen command to create one. Type ssh-keygen, press enter, and let's just accept the defaults by pressing enter. Let's try the command again. We can see with the public key created, everything's all right. You may or may not have that error if you already had a public key created. This is creating a variety of resources on Amazon AWS in our account. From here on out, charges will begin to accrue. This will take a moment, and you can watch each individual step. Basically, what's occurring is that the cluster is creating a variety of resources, including machines, masters, and workers, and networking them together. Once it's complete, you can see that COPS has created the cluster. It'll take a few minutes to get ready. It gives some suggestions, and we'll follow each of those. But let's give it a minute for resources to come up. It's worth noting that COPS has automatically switched the kubectl configuration on our machine. If we type kubectl, we will no longer be accessing the minikube which is running on our machine. Instead, kubectl has now been bound to the cluster on AWS. Any commands issued to kubectl will now run against our cluster that has been created, not the minikube. After waiting a few moments, let's type the COPS validate cluster command, its first suggestion. The last line seems like an error. Cannot get nodes. This means that it's not quite done with its setup items. Let's give it some more time. We can keep reissuing the command about every minute or so. In this case, we see we have a little bit of progress. The master has come up. It's ready. But the worker nodes don't seem to be ready. Let's wait a moment more. It seems like patience is not my virtue. Running the command again, now we have one node out of 2 is ready. Progress. But we're still not quite there. Seems like the third time is the charm. You can see that our nodes are up and running. 2 worker nodes, a master, and we have confirmation that the cluster is ready. This may take up to 5 minutes or more, depending on how busy AWS is. Now that our cluster is up and ready, let's have a look at the master. The COPS validate command has already indicated that the master is already running on this host. But let's scroll up to the list of suggestions that COPS gave us. First was validate cluster. We already did that. Let's list the nodes. The kubectl get nodes command is one that we've used before. We should be familiar with it, but let's look at the output anyway. This gives us information about each of the nodes, how old it is, and a variety of information about the versions and the labels assigned to it. Let's go back up to the suggestions again. Let's SSH into the master. Copying this command will give us direct access to a shell on the master. However, you'll notice that this doesn't work. The reason is since we're not logged in to a shell on AWS itself, the domain name cannot be resolved. Let's replace the domain name here with one that can be by any machine outside of AWS. We'll use the Amazon AWS console to get the externally available host name. Go back to the management console, or if you don't have it open, just open a web browser to aws.amazon.com and click Sign In to the console. Once you're at the console, in the upper right-hand corner, ensure that the console is set to the proper region. In our case, since I chose US-West-2, that corresponds to US West Oregon. The console is in the appropriate zone. That's good. Now, let's choose EC2 because we're looking at our servers. Servers are available as an EC2 service. Let's click on Instances in the left-hand corner. And let's choose the master. There should only be one. Let's cut and paste the public DNS name, the entire string, starting with EC2 and ending with .com. Let's take that to our clipboard. Returning to the shell, let's recall the previous command which failed by pressing the up arrow. Let's delete everything before the @ sign. And let's paste in the host name that we just copied. It may ask you to verify the public key, in which case you should type yes. It may not if that public key is something that you've used before. In our case, it didn't. But if you're asked to verify a public key and trust it, type yes. We're now on a shell on the master machine that Kops created for us. We can do a few things here. First, let's type ps space ax. You may be familiar with this command, as it was a process listing of everything that's running on this machine. There's a variety of processes running. Docker is running the Kuba scheduler. You can see etcd is running. You can see the Kuba controller manager is running. All of these services are running as processes on this master machine, as we would expect. You can see kubelet is running. All of these services were set up properly by the Kops system. We didn't have to do them by hand, but we can go and look at them as we need to. You can see that etcd is being logged to /var/log/etcd. Kuba scheduler is being logged to kubascheduler.log. Let's go have a look at our log directory. You can see that the logs are available on our file system if we'd like to look at them. Let's have a look at the Kuba API server-log. You can see we don't have permissions. Let's use sudo. This is the output from the Kuba API server since it's run. There's quite a bit here. Now that we've seen the actual processes running on our machine and examined some of the log output, let's look at how they're running. They're running as Docker containers. Let's use the sudo docker command to look at what containers are running on our system. We'll type sudo docker space ps. This will give us a listing of every single Docker container running on our master. There are quite a few. Much like we saw in the ps command. We can see Kuba proxy running, Kuba API server, etcd, controller manager. These are all individual Docker containers which comprise a variety of Kubernetes processes. These Docker containers are started and run by Kubernetes on our master, and we don't have to worry about them. This just gives us an inside look into the internals of our master. We'll type exit to log out. And now we've disconnected from our master. Next, let's use kubectl to look at a few other items. The first command we'll issue is kubectl git deployments. But let's provide the -- namespace equals kuba-system flag so we can look at services running in the Kuba system namespace. You can see the DNS autoscaler, and DNS controller are also running. These were running on our master as well. Feel free to explore more using the shell of the master. You can look at logs and look at what processes are running. It's not important necessarily to understand the intricacies of each process. Those are managed by kops and by Kubernetes for you. The whole point is Kubernetes provides transparent management of those underlying processes. The key idea is just to know that they're running, where they're running, so you can be a more effective user of them. You don't have to understand the log output. You don't even have to understand the individual processes. Those are managed for you by Kubernetes. The point of looking at these and logging into the machine is not to master them, but to know simply that they exist and how they're set up and managed. Hopefully, unless you become a Kubernetes system engineer, you'll never have to access them directly as we have today. But hopefully it gives you an understanding of what's going on in the master, where it exists, and having touched it, it now exists as a real practical component and not something as a theoretical black box. Because in future lectures, we'll work on setting up multiple masters using the kops tools. Now that we've had a look at our master, let's make sure that we stop our cluster. You're more than welcome to leave the cluster running if you'd like to examine it further or play with it. Just remember, you're paying for these resources. We'll use kops to delete the cluster. This should release all resources and terminate the billing. However, bugs are present in all versions of software, and we don't have control over kops. To be completely safe, close the AWS account you created to ensure all resources are released and you're not charged. Or wait until after you've completed this lecture series to do so if you'd like to follow along in the following lectures. Regardless, make sure that you're not accruing charges that you're unaware of or that you'd not like to accrue by stopping the cluster at this point, because all AWS resources are billed on usage, which includes how long they're running for some of them. Using kops to delete the cluster is simple. We'll type kops, delete, cluster, and we'll give it the name of our cluster. And we'll specify the -- yes command so it doesn't keep prompting us. This may take a moment as it communicates with the API. If you receive an error that your cluster was not found, check the name. If you're sure the name is correct, tie appending .k8s.local to the end to ensure you have a fully qualified name. You'll see it's going through, iterating through resources, and deleting them as appropriate. This may take a moment. If everything was deleted appropriately, the last line should be that the cluster was deleted. Deleted cluster with the name. Again, bugs may exist in the software, which leaves AWS resources still running. To be sure, to avoid any further charges, close your AWS account or look at the billing status in AWS to ensure no further billing is accrued. In the previous lecture, we created a simple Kubernetes cluster in an AWS account using kops. Now, let's examine how we can set up the key parts of a high availability cluster when creating a Kubernetes cluster using kops. Remember, a lot of the managed Kubernetes services will do this for us. We're using kops so we can examine how to do this ourselves. So that way, when purchasing a service, we at least have a good idea of what's going on under the hood. Or, if we need to, we can always do it ourselves in our own production clusters, which we manage in the future. Remember, one of the key high availability design considerations is how many masters we will have. An odd number is important. Because Kubernetes uses an algorithm to detect and choose how many masters need to be available, an even number would create the situation where there's an equal number of masters that are down and masters that are up. This would create a situation where we are not sure if the cluster should be considered up or down. It'd essentially be a tie. An odd number of masters never lets this happen. This is not specific to Kubernetes. It's called the N+1 problem in some ways. It is something that is specific to most systems that use redundancy for high availability. The second thing to consider is where the masters are located. Are they located in the same building, in the same data center, the same city, or even the same country? We discussed these a few lectures ago, and your choices that you make here are up to you. They have to match your needs. Otherwise, there may be a mismatch between your expectations and the requirements and what you can actually provide in terms of redundancy. Are you willing to tolerate a citywide disaster, a statewide disaster, or a nationwide disaster? Who knows? You have to make those choices based on the business line requirements of your application running on Kubernetes. Choosing where these masters are and how many of them can provide you with an idea of what you're going to need to provide resiliency for your high availability design. In our case, we'll start with only 3 masters, and we'll make sure they're located in different availability zones. AWS availability zones, if you're not familiar, are isolated failure areas. You can think of them as separate data centers. Even if they're technically in the same area, Amazon has warranted to us, because of the way they're designed, that a power failure, a network failure, or even a fire in one availability zone within a reasonable probability will not affect the other ones. We can consider them, for our uses today, independent data centers. We'll use the kops create cluster command as we did to create our cluster in the previous lecture, but this time we'll specify a few high availability options. We'll specify how many masters we'd like and in which zones we would like these masters provisioned. Let's actually create the high availability cluster and deploy an application to it. First, we'll use the kops create command to create the cluster with the high availability options. Then we'll look at the nodes to see where our multiple masters exist. And then we'll deploy WordPress and MySQL without volumes, as we have in previous demonstrations, to see how an application is deployed to a high availability cluster. Creating a high availability kops cluster using the kops toolset is remarkably similar to creating a non-HA cluster. In the previous lecture, we used kops to create a single zone, single master cluster. If anything were to happen in US-West-2, our cluster would not function. Or if something were to happen to the machine running our master, our cluster would not function. We'll use the same flow with a few new options to set up a high availability cluster using kops. Our first step will be to ensure that the environment variable for our state store is set. We'll use the existing one we already have. the export space, all capital cops underscore state underscore store environment command and setting it to the S3 bucket we created. Next, we'll use the same cops create cluster command to start with. Then we'll make some changes. Cops space create space cluster with a name, space, dash dash zones, and we'll provide a comma-separated list of zones in which we'd like to run. We only ran in US-West-2A in the previous lecture. In this case, since availability zones provide us with different redundancy and availability, if one goes down, it's relatively certain another won't, since they run in different places with different power, different connectivity, etc. Let's specify US-West-2B and US-West-2C. So 3 different zones separated by commas. Then we'll have to provide it dash dash node dash count. How many nodes do we like to run? In this case, let's run 3 nodes, 1 in each one of our clusters. So we'll say node count 3. Let's also specify what zones we'd like our masters to be in, not just our workers. That's done by specifying dash dash master dash zones. We'll do the same. US-West-2A, US-West-2B, and US-West-2C. It's worth noting we're creating a significant amount of machines with this command. You'll want to be sure that if you're going to run this command that you're willing to accept the charges. Since we're creating a replication factor of 3 different zones with 3 nodes, we're going to create many more nodes, 3 times more nodes than we had. Let's press enter to issue the command. Much like creating the cluster when we were only creating one zone, cops is executing commands. However, it has many more to run, so this may take even longer. Much like last time, we'll have to wait for our cluster to be ready. Let's use cops validate cluster to see the current status. As you can see, we can't even get the nodes quite yet because we're still waiting on AWS to provision our resources. Let's give it a moment. Let's run the command again to see where things are. Looks like we're still waiting on Amazon to provision our resources. It seems we have some progress now, but the masters still aren't ready. The nodes have been created, and we can see 3 masters have been created, 1 in each availability zone that we described, and that 3 worker nodes have been created. Again, 1 in every node in every availability zone that we described. Once the output from cops validate cluster looks like this, with a message, your cluster is ready with its name, you're ready to move on to the next step. This could take quite a bit of time, as AWS has to provision resources, and once those resources come up, they have to wait for processes to start. Once your cluster is ready, we'll move on to looking at it. Let's use the kubectl get nodes command to look at the nodes running in our cluster. You can see that we have 3 masters and 3 worker nodes. This is what we expect. This way, if any one master were to suffer an outage, another master would be able to take over. Seeing that all of our nodes are up in the ready state assures us that the nodes are up and properly working and accessible. You may recall that when we first set up WordPress in MySQL, we did so without specifying any persistent volume. We simply had WordPress and MySQL running as Docker containers. We'll use those exact same deployment files. In the Kubernetes in production directory, under the setting up high availability subdirectory of the GitHub repository for this course, we have copies of both the mysql-deployment.yaml and the WordPress-deployment.yaml files. These are identical configuration files to the ones that we used in the DNS and service discovery lecture. We'll use these two to deploy WordPress and MySQL without any persistence to our new highly available cluster. Let's use the kubectl apply --f /mysql-wordpress.yaml command to create the MySQL deployment on our cluster. We'll see that the service and the deployment were properly created. Let's do the same for WordPress. Let's use the kubectl git deployments command to look at the status of our deployments. You can see that MySQL is fully available, whereas WordPress is still coming up. Let's run it again to see if WordPress is available now. Both of our deployments have deployed just as they would on a regular non-redundant cluster, but in the high availability cluster, it's now running on top of a more resilient fabric. As you can see, nothing has really changed from a deployment perspective. It's simply the workings of the underlying services of Kubernetes which have become more resilient and robust. Whether working on a high availability cluster or a small cluster or a mini kube, the higher level commands largely remain the same. Let's use the kubectl describe deployment command to look at the status of WordPress. Everything looks normal to us. Now, since we have multiple nodes working, and this is something that we haven't done before, let's look at the pod that is running our deployment and see what node it's running on. Let's use the kubectl describe pods command to look at the pods running on our system. If we scroll up, there's quite a bit of output from this command. We can see the WordPress MySQL pod. This part of the string is defined as a unique pod name at runtime, is running on a node named IP-172-20-86-23. The scheduler chose this node based on a variety of factors: availability, CPU use, etc. If we keep scrolling up, we can see the WordPress pod. It's running on the same node. Kubernetes automatically decides which node to deploy a service to and deploy a given pod to. It manages all of that scheduling using the default scheduling algorithm, and you can see the history for that in events. The default scheduler assigned a node, the pod to run, and then further went, started the container, and made it available. Whether you have one or many nodes, Kubernetes handles that process for you. Of course, none of this is particularly interesting to us or to our users if we can't use the service. Remember, when we created the WordPress YAML file, we specified an external service. Let's get the details of this service using the kubectl describe service WordPress command. This will give us information about the service exposing our WordPress container. We created it as a load balancer. Since we're on Amazon AWS, we can look at the load balancer ingress, which is a host name. Let's copy that to the clipboard and look at a web browser and see what that does. Let's navigate to that URL in a web browser. This should look familiar. This is our WordPress installation now running on our highly redundant Kubernetes cluster. Unlike on our Minikube, this was actually served up from behind the load balancer described here. This was an Amazon Elastic Load Balancer, or ELB, that Kubernetes dynamically provisioned and provided us access to. In this exercise, you've seen how we've set up a highly available cluster by specifying the high availability options. We set how many extra nodes we'd like to create, how many extra master nodes we'd like to create, and where we'd like to create them to provide a more robust and resilient fabric for Kubernetes. We'll also note that simply doing this didn't change the way we interacted with Kubernetes. Because Kubernetes provides isolation and provides a relatively black box scalability system, we were able to create a more highly available Kubernetes cluster and not have to make any changes at the application layer to our deployments to take advantage of this new highly available cluster. This provides a variety of mechanisms to the system administrator and the application designer to be able to separate the needs of deployment, resiliency, scale, and the nature of being robust, and the application developer, which develops the individual application. This also provides us with the ability to grow the application as we may need to. We can start small on a non-highly available cluster and move to a highly available cluster without making significant or any changes to our application. Remember, unless you'd like to follow along in the next lecture immediately, take the time to delete your cluster. This will prevent any further charges from accruing on your Amazon AWS account. Of course, if you'd like to accrue these charges and leave the cluster running, that's your choice. Again, use the cop space delete space cluster space the name of your cluster space dash dash yes command to delete the cluster and release the resources. This may take a moment. Similar to last time, the cluster successfully deleted output is your confirmation that resources were released. As always, there could be bugs in software, and cops may not have succeeded in deleting everything. To be sure that charges are stopped, close your Amazon AWS account or access the billing interface to ensure no billable items exist. Earlier in this lecture series, we examined how volumes can be created to persistently store data used in or created by applications running on our cluster. You may recall that this involved deployments using something called persistent volume claims to ask the Kubernetes control plane for something called a persistent volume that functioned like a persistent disk in a physical computer system. In those demonstrations, we were responsible for explicitly creating a persistent volume and defining it so that Kubernetes could fulfill these persistent volume claims when we deployed MySQL and WordPress. Now that we have a cluster running on AWS, we have a chance to explore a useful function of Kubernetes, auto-provisioning of volumes. This feature isn't specific to AWS, but Kubernetes does support it on AWS. First, let's explore auto-provisioning of volumes in general and why it's interesting. When creating a volume and a persistent volume claim, you define certain things about each. You will recall that we created 10 gigabyte volumes so that in our MySQL and WordPress deployments, we had a 10 gigabyte persistent disk attached to each. We first created the volume, and then we created the persistent volume claim. When an existing volume doesn't match a claim in Kubernetes, the dynamic provisioning system of Kubernetes means that it may be able to, based on the provider type and configuration in which your cluster is running, provision volumes to fulfill the claim on its own. Depending on the underlying implementation's ability to create new volumes, things like available space, appropriate permissions, etc., it may be able to automatically create a volume to fulfill a claim at runtime. A good example of this, if the underlying system is a cloud provider with enough quota and access levels, Kubernetes may be able to create new volumes. One good example that we'll explore here is the Elastic Block Store services on Amazon Web Services. We'll discuss it in a second. An example where dynamic provisioning may not work is that if the underlying file system is a SAN or storage area network file system, and there simply is no more free space on the disks that make up this SAN, Kubernetes would not be able to create a new volume. It can't order and install more physical disks on its own, yet. However, on something like Amazon Web Services, where the Elastic Block Store, or EBS offering, offers essentially unlimited disk space to the user, where a user doesn't have to physically order a new disk. Kubernetes provides a facility that can use and even dynamically provision volumes on EBS to match or meet persistent volume claims made by pods. As long as your Amazon account is valid and you're not limited by an EBS quota, Kubernetes should be able to automatically provision volumes to match persistent volume claims. Let's explore how this works. We'll use our existing MySQL and WordPress deployment that we set up on our Kubernetes cluster on AWS in the previous lecture. We'll edit it to include persistent volume claims to mount a volume at the point where it's expected in our MySQL and WordPress deployments, just like we did several lectures ago on our Minikube, but this time we'll do it on Amazon AWS. This time around, however, we won't create the persistent volumes. We'll leave that up to dynamic provisioning. We'll only create the persistent volume claims, and we'll see in action the dynamic provisioning create EBS volumes for us and bind them to that claim successfully. Let's take a look. We'll need a clean cluster to get started. If you already have one running, you can use the kubectl delete deployments commands to delete the existing WordPress and MySQL deployments. This is if you didn't delete the cluster at the end of the last lecture. You'll need to run the delete deployment command for the WordPress-MySQL deployment and the WordPress deployment. Make sure to press enter after each of these commands. I'm just providing a demonstration of them here, as my cluster doesn't have them running at the moment. If you did delete the cluster, you can use the kops create command, as we have in the past, to create a new cluster. Remember, use the export kops state store command first to make sure that your kops state store environment variable is properly set. We've done this in the past. The commands will be exactly the same this time around. We'll export the state store. Then we'll use the kops create cluster command to create a small cluster. Remember, this will take a moment, and we'll use the kops validate commands to make sure that we check the state of our cluster and that it's ready for us to begin using it. It looks like things aren't quite ready, but they're progressing. Let's give it another moment. Running the cluster command again, we can see that the cluster is ready. Whether we deleted deployments or created a new cluster, we're now ready to demonstrate and walk through auto-provisioning of volumes. To do this, we'll use the files that are in the GitHub repository for this lecture series. These files are identical to the files that are used earlier to deploy WordPress and MySQL using volumes, with one omission. We're not going to create the volumes ourselves. the volumes will be created by the auto provisioner. In the earlier volumes lecture, we manually created persistent volumes. We simply won't do that. These files, available in the GitHub repository, in the Kubernetes in production directory, volumes on AWS subdirectory, are exact copies of what we used to define volumes on our Minikube. Again, the only difference being they simply lack the local volumes file. We can see two files exist in our directory, one for our MySQL deployment and one for our WordPress deployment. As I mentioned, they're exactly the same files that we used in the volumes one. We're simply lacking the third file that created the local volumes. We'll use kubectl apply to create our MySQL deployment first. You'll notice that it will create a service, a persistent volume claim, and a deployment, but no persistent volume itself. Remember, we're relying on the underlying auto provisioner to do this for us since we're running on AWS. Let's do the same for the WordPress deployment. Again, you'll note the service was created, the persistent volume claim will be created, and the deployment will be created. And yet again, no volume was actually created. Again, that's because we're relying on the underlying Kubernetes auto provisioner to create an ABS volume for us and bind it to the persistent volume claim transparently. Let's use the kubectl describe persistent volumes command to see if that's what happened. Let's scroll up in the output to see what this means. You can see that a persistent volume was created with a system-generated identifier. Looks good. A 20 gigabyte volume was created as an AWS Elastic Block Store persistent disk in AWS. This was done automatically for us. We didn't manually create this, and none of the files actually enumerated this. This was done by the auto provisioner. You can see the first one is for the MySQL PV claim. Further down, you'll see the same thing exists for WordPress. An important annotation that we can take note of is that Kubernetes will mark it with an annotation that indicates that it was created by the AWS EBS Dynamic Provisioner. This assures us that this wasn't something that was manually created, and it also provides us with the ability to distinguish between things that were auto-provisioned and things we might have created ourselves if we ever needed to. Now that we've examined everything in the actual kubectl interface, let's look at the other part that matters, the actual application. Let's use the kubectl describe service WordPress command as we have in the past to get the URL for the load balancer that's serving up our WordPress service. Let's copy the URL of the load balancer and open it in a web browser. Navigating to the URL, we can see that WordPress was successfully installed. Remember, the cluster running on AWS is accruing charges. And now that we're complete here, it's important that we either know that we're going to continue to accrue charges or use the cops delete cluster command to delete the cluster and terminate the resources so we're no longer billed for them. As usual, there are bugs in any kind of software, and there's no guarantee that cops will do everything and delete everything it needs to. It should, and that's what it's designed for. But the best way to be sure is that when you're complete and done with following along with the demos in this lecture series, delete and disable the Amazon AWS account entirely to avoid any chance for further billing. We've seen how the cluster auto provisioner can automatically leverage underlying resources to create volumes for us. We don't have to create a persistent volume to fulfill persistent volume claims because the auto provisioner is smart enough that when available and appropriate, it's able to allocate resources for us, for example, in the cloud. This may be something you would like to leverage or not, and the choice is up to you. Consult the Kubernetes documentation for what types of underlying volume types actually support auto provisioning. For example, a physical machine may not be able to provision any more space unless an administrator actually goes out and buys and installs more physical disks. This is somewhere where auto provisioning simply wouldn't work. The documentation has a wide array of information on auto provisioner and how it works in varying circumstances, as it varies from provider to provider or from situation to situation.
Hello and welcome. This video provides a brief outline of what you can expect from Helm Fundamentals as part of the Mastering Kubernetes course. Let's take a quick glance at what each video will cover in this upcoming section. We'll start then with what is Helm. We'll take a look at what Helm does and how it works with Kubernetes. We'll then move on to the installation guides for all operating system, in which we'll run through how to get up and running with Helm and the tiller on different OSs. And we'll cover the top 5 commands and what you can do with them. We'll also take a look at our Helm deployment in this video, and we're actually going to deploy a MongoDB cluster through Helm. We're going to take a look at Helm charts, and we'll start to create our first chart there. We'll then move on from charts a little bit, and we'll take a look at how we can integrate template calls into our chart and what they do. We'll look at Helm values and how we can configure our charts to be very flexible and dynamic. Then finally, we'll take a look at Helm commands and how to interact with the Helm CLI in a little bit more depth. With that then, I hope you're as excited as I am to jump into our first video. By this point in the course, you should feel that you've not only grasped the basics of Kubernetes, but you can now also handle some of the more advanced components of the platform. This Helm Fundamentals section is all about getting to grips with Kubernetes and the Helm Package Manager. As the following videos will show, Helm is the missing link between continuous integration, continuous delivery, and your components, and allowing you to flexibly work with multiple environments and with a flexible workflow. So let's dive into Helm and all of its uses. We know Kubernetes can become incredibly complex with all of the objects you need to manage, such as services, pods, configuration maps, persistent volumes, their persistent volume claims. And the YAML, although very powerful, is very static. And a common model you'll see is to copy and paste YAMLs for each new environment. Now this becomes very messy and is against our kind of do not repeat coding principles. And of course, all of this just adds up to create more work and duplicate work. And of course, the more we do that, the more we introduce errors. So Helm provides a way to avoid all of this by adding programmatical elements to create a package and dynamically configure that package as we try to deploy it. It can also allow you to manage your package dependencies, similar to something like apt on Linux, where if you're installing a piece of software, it will also install the dependencies. Helm allows us to do that. So Helm really fills the need to be able to quickly and reliably provision containerized applications through an easy installation module it also allows us to easily update and remove those same container modules. As we've already mentioned, with Helm, it's about charts, and you can define, run, and upgrade unique and complex Kubernetes applications with these charts. This is amazing if you want a simple way to publicly distribute maybe your open source app, but it's also a very good way of cleaning up your private app repositories and adding that additional level of flexibility and smooth control. The package manager helps developers streamline that installation and the management of their applications. And Helm charts are our deployment packages, and they are made up of our flexible Kubernetes YAMLs. Helm is actually made up of two parts. The Helm tool itself, which sits locally on your machine or as part of your CI pipeline, and then the tiller, which runs on the Kubernetes cluster and actually manages the installation of the charts. When you're working with Helm on the command line, it sends the command with the chart to the tiller and the applicable values with that tiller. The tiller then takes all of that information and compiles the Kubernetes static YAMLs and applies them to your cluster. This is how Helm has built in the dynamic ability to be able to deploy these charts. So Helm charts are our package, and they give us the ability to leverage other Kubernetes packages through a single CLI command line. Using the Helm tool, we can also locate and customize remote charts. And so we can go and search them. And all our charts contain two things: a package description, our chart YAML, which is a collection of metadata for a chart, and then our templates. And our templates are our dynamic YAMLs, and they are actually YAML files that sit in the templates file. And we'll look into this in more detail as we go through this section. Now, Helm itself offers a huge repository of official charts. And of course, on GitHub, you can find unofficial charts. Now, charts can also be stored locally if you want to pull them down and make modifications to them, or, as we'll do later in this section, create your own charts. Now, to install a chart, it's as simple as running Helm install, then the location of the chart. In the example here, it's the stable location of the official repository, and then the chart name. And that's really the most basic command that you can run. So to recap, Helm provides a simple way to package everything into one simple deployment. And with Helm, it's all about charts, and charts allow developers to quickly define, run, upgrade even the most complex of Kubernetes applications. On top of that, Helm offers a repository of official charts, and on GitHub we could also go and find unofficial charts. In fact, any software revisioning platform, we can go and find unofficial charts. And again, charts can be stored locally on your machine, or you can just pull them and let Helm and Tiller do its work. So next up, we're going to be looking at how to install Helm on the varying different operating systems available. In our last video, we looked at an overview of the package manager Helm and all it can help us achieve. Getting started with Helm can be accomplished through a simple DIY installation or by leveraging one of the automated installation from a vendor. Now, before we get started, the prerequisite for this section is a Google Cloud account and a project within that account. For those that are not aware, Google Cloud is an alternative service to AWS. And one of the main reasons for me introducing it here is A, to give you an idea of how other services compare, and B, because the actual setup of Kubernetes is extremely easy. We will also need to install the gcloud SDK. To create a GCP account, simply go to console.cloud.google.com and log in with your Gmail account. We also need to install the gcloud SDK. So simply search Google Cloud SDK install, and then we can see the results, and we'll jump straight into the first one. As you can see, there is an install for each of the operating systems, but I hope you decided to follow along with Linux, because that's exactly what we're going to do now. So we just need to copy and paste those scripts into our terminal, and we're away. Our next step, once it's installed, is to initialize that account and get us authenticated with the Google Cloud Platform. So we're going to jump back into the terminal, and in the terminal, you're going to just simply type in gcloud int and hit return. Now, I already have an account or several accounts set up on my machine, so it's going to be ever so slightly different. But it's a very straightforward follow-along process for a new installation. You're just going to select create a new configuration. I will actually just reinitialize my account as I've already got them up and running. So once you're in gcloud, you can either select a new product or you can select an existing one. We're then going to come down to the Kubernetes engine, and we're simply going to select clusters. Now, if this is a new project, this will take a minute to enable the Kubernetes engine, but you don't need to do anything, you just need to wait for it to finish. We're then going to just click create, as I've just done, and then we're going to fill in our cluster detail. So I'm going to call this one Helm Demo. I'm going to use the latest version of Kubernetes, not the default version. I'm going to change down our nodes to 1 because we don't want to incur too much cost. And I'm going to hit create. So that is our creation of a Kubernetes cluster on GKE. Now I'll skip forwards and we can take a look at all the varying details. So we can look at our storage, we can look at our nodes. We can take a look at workloads. Now, of course, there won't be any on here at the moment. But what we can do is look at the system workloads, and that's what's in the kube system namespace. We can also take a look at services, and again, we can show the system services. We've got Heapster, kubedns, metric servers, and of course the default backend. Now to connect to that, we're just going to come in and copy our gcloud command, and we're going to jump over to our terminal, and we're just going to paste that in. Now we have a cluster, and we are fully connected to it, and so again we can check for those services and compare them. But if we do a get kube control all namespaces, we can see all of the existing services. So as we mentioned previously, there are two parts to Helm. There's the Helm client, which we're going to install locally, and then there's the Helm tiller. So we'll start with the Helm client because we install the tiller using that client. Now, for all OSs, we can go and download the binary and just copy that into one of our paths. For Linux, we can use the Snap distribution. For Mac OS, we can use Homebrew, and then for Windows, we can use Chocolatey. Now, I would advise you may find this section easier if you're on Windows to download the Linux Windows subsystem and install Ubuntu. It's easy to set up, and then you can follow along exactly the same way as I'm doing throughout this module. So if we were going to install it with the binary, which is what I will demonstrate, you'll go and download that binary, which I'll show you how to do. We're going to decompress it using tar, and then we'll move it into our user local bin, and we'll call it Helm. And it's dead straightforward. It takes a couple of seconds. The other option for Linux, if your OS supports it, is you can use Snap to install the package that's maintained by the Snap crafters. And to do that, it's just simply sudo snap install Helm. With Mac OS, it's Homebrew, and it's just a case of brew install Kubernetes -Helm. And then with Windows, if you're going to go down the Chocolatey route, you just need to make sure Chocolatey is installed, and then you're going to do a choco install Kubernetes Helm. Once we have Helm installed, we need to be able to connect to the cluster. So we're going to make sure that we're still connected to our Kubernetes cluster that we've just got set up. And then we're going to install the tiller, and we do that with a Helm int. And that will initialize everything for us. This checks the local environment for the Kubernetes security and allows us to connect to the cluster. Once connected, it's going to deploy the tiller for us into the kube system namespace. And then we can go and check that it's up and running by running kube control get pods namespace kube system. So first, let's go and get our releases. So just Google Helm releases. Then we're looking for the GitHub Helm repo, and it's Helm releases. Then if we scroll down, we can see the varying different binaries. So I'm running Linux, so I'm just going to download the Linux AMD 64. There we go, that's finished. I'm going to jump over to the terminal. Now all I'm going to do is decompress the file and extract the files out of our tar. Now that's decompressed. We just need to copy that bin, that Helm file, into our user local bin. Now you may need sudo permissions. I'll just go back and add sudo and hit return. Just going to fill in my details here. So we can see that Helm is installed, but there's no tiller attached. So we're going to run a Helm int. So let's just do a kube control get pods all namespaces. And there at the bottom, we can see our tiller deployment. So that's it then for this video. Once you've got everything installed, let's move on to the next video. In this video, we'll hit the ground running with all we've covered in the Helm fundamentals. And we'll start with our first deployment. We're going to take a look at MongoDB, quickly examine what it is and why I've chosen it as our deployment, and then we'll go ahead and actually deploy it. Now, if you're more interested in building your own charts before trying a deployment, you can skip this one. It's a simple example that we will repeat in later lessons and we'll go over. It's simply so you get to try Helm out very quickly and easily. MongoDB is a free open source database management system. It uses a document-oriented database. And so instead of laying out tables and rows in a relational database, it just comprises of these documents. Now, the reason I've chose it is because database usage within Kubernetes is becoming more popular, and it can be really quite tricky to set up. With a database application, you're very heavily reliant on state. So they're not stateless applications, they're very stateful, which means we have to keep persistent data in place. But not only that, we also have to build out our pods in order, and pod naming becomes a priority as well, especially with Mongo. Like, the Mongo master must be able to communicate with Mongo 2 and 3, but we must build our master first, and then any other nodes that we add into our Mongo cluster must connect to that master and then join the cluster. Not too dissimilar to how you manually build a Kubernetes cluster with something like kubeadmin. And so when you're doing this in Kubernetes, a deployment doesn't work, because in a deployment, we don't care about order. So this is one of the things that Helm starts to help you with. So for our deployment, we need our Google Cloud account that we set up in our earlier video. We need our gCloud SDK, which we've already set up and connected, and we need Helm and Tiller already installed. I've covered that in our previous videos of this section. So basically what we're going to deploy is a 3-node MongoDB cluster. It's actually going to use stateful sets. Now, stateful sets are the Kubernetes object for managing the order. But we're going to use Helm, so we've got our flexibility of Helm on top of those stateful sets. Now, when I say order, that's order of creating the instance. It also names the machines in order. So the first one it creates will be called number 1, and then number 2, and number 3. And it's really that simple. It will also help you deal with persistency and volume claims, and making sure that the correct pod gets access to the correct volume claim. So this is what it looks like, and we can see we've got our 3 MongoDB pods inside our stateful set. They are connected and reliant on our storage pods, and then there's a couple of bits of metadata on this diagram as well. Like, Mongo will be able to be accessed through the stateful set Mongo service. So that's what we're going to deploy. To actually deploy it, we could simply just run the helm install stable /MongoDB -replica set. If you'd like to look at the chart itself, you can go to the URL that's currently displayed on the screen. Now, we will have to make sure that our local repository is aware of the repository, so we'll do an update and I'll show you that in the demo. But Helm will then bootstrap everything else, and we're pretty much done. However, we may also want to make this a unique deployment, and so we can give this release a name. And so we're going to call it My Release. And then if we wanted to call it My Release 2, we could have 2 Mongo clusters on the same machine. With that then, let's jump into our demo. Okay, so we installed Helm and Tiller, but within GKE uses our role-based access management. And that means we've got to make a slight modification. So we're going to do that now. The first thing we're going to do is we're going to create an account for Tiller, and we're going to call that servers account. So we're just going to run this kube control namespace kube system and create that. Now, I've already got that account set up. As you can see, it's errored, but it should just come back and said creating account. We're then gonna create a cluster role binding. It's going to bind the service account tiller to the custom tiller account. It's also going to bind that tiller instance to all of those configurations. And then we're just going to update Helm int to tell it to use the service account tiller. And there we go. Now, what this means is this will give tiller access to administer Kubernetes in the varying different namespaces. So we're going to do a Helm repo update first, and that will go and fetch all of our repositories. So we're going to run a Helm install name. We'll call this MongoDB demo. We're getting it from our stable official repository, and it's MongoDB. Oh, I missed the slash. MongoDB hyphen replica set. So this will download it. There we go. It's downloaded everything, and you can see it gives us a lot of information about the service that's been deployed, the stateful set that has 3 nodes in it, pods. Now we can currently see that there's 0 pods ready, and it's currently only wants one of that 0 pod. So we'll do a kube control get pods. Okay, that's in stage 2 at the moment of 3 stages of getting ready. So we'll skip forwards a little bit until all of these are ready. You can see I went back and I checked, and it built those out in order. There's then a couple of commands that you can follow to get access to that. But if you want to go and play with Mongo itself, it's fine. But what we'll do now is we'll jump over to the dashboard, and we'll take a look from the console of what's been deployed. So we can see our cluster, and we've still got our nodes in there. Nothing's changed, but if we come down to workloads, we can now see our MongoDB replica set. We can see that there are 3 pods running, and you can see the static YAMLs that have been created. We can also jump over and take a look at our services. That service is connected to 3 pods. And there we can see our 3 pods actually running, and you can see what I mean by the ordering from the stateful set 0, 1, 2, and 3. And we can take a look at that pod and just grab out any details. We can also go and see logs if we wanted to, or inspect or edit the YAML file. So in this video, we deployed MongoDB, an open source document orientated database. And we talked about that the traditional steps, especially within Kubernetes, would be very complex. And we saw how easy it was to deploy that with Helm. Hopefully by now, you're starting to see some of the benefits of Helm and how simple the CLI is to use. In this next video, we'll further familiarize you with Helm charts, and we'll demo how to easily create a Helm chart to your own specification. As mentioned previously, there's both official and unofficial repositories. And we're going to build an unofficial repository for our own private application. And these contain pre-packaged charts. So the official ones contain pre-packaged charts of open source software. And charts consist of a collection of YAML files. And these are the YAML files that are your Kubernetes manifest. But it has this templating capability, so it allows for dynamic values. So this is the basic structure of your Helm chart. We've got the package name, or the chart name, for the directory. And then in the root, we have a chart YAML that contains your metadata for your package, such as the name of it, the description of it, the version of it. We've then got any licensing, of course, your README. There's any requirements values if there's any dependencies. And then there's a values file, which we'll discuss later. And then inside of that, there's two subfolders. There's the charts one, where we package it all together into a kind of, it's similar to like a binary to download, and they're the different versions. But then we've got our templates, and inside our templates is where our Kubernetes manifest files will go. And that's really what we're going to be looking at in this video. So we can use the Helm command to create our charts and install charts locally from a pre-packaged version. But we're actually going to build ours out manually. However, if you did want to create it using defaults, you can do a Helm create and then just the name of your chart. But as I said, we'll go through it manually and we'll add in our requirements and discuss them as we go. So we need to come to our Git repository and come into chart creation. And we're going to actually take the Ghost deployment that you created earlier in the course and turn it into a Helm file. So we're going to make a directory called Ghost. We're going to cd into it. And then we're going to create our chart YAML. We're also going to create our templates directory. And then we're going to open up Vim and edit our chart YAML. So the first thing we want to add is our API version. And in this case, we're going to use version 1. And then it's our app version. And again, it's 1. These are fairly standard, so if you're doing this, these will be the same for each one. Your description then, a simple deployment of Ghost. Then we're going to give it a name. And we can only use alphanumeric and the hyphen in our name. So do not use underscores. And then we're going to give it a version. And this is the version of the actual chart that we're creating. So this is what we would increment every time. So that's it then for our chart. I'm going to copy in everything from the creation file into the template, and we'll go through and edit those. So this is our static files that we created. So you should recognize these. We created them earlier on in the course. And then we've got our local volume that's attached. Now you can see these are exactly the same as they were previously. We've not made any modifications to them yet. So that is a static Helm chart. I'm just going to check what deployments I have. I have no deployments in Helm. So now I can do a Helm install. Now at this point, like I say, we're just deploying a static version of that chart. So I'm going to give it a name called Ghost Demo. And then I'm just going to deploy the chart from this folder, hence the dot notation. And you can see it's gone and created our cluster. Now that is very static, but that's fine for this course. You can see how easy it is to create a chart. So we've got our service, our deployments, our pods, our persistent volumes, and our volume claims. So in this video, we quickly discussed Helm packages are called charts. We can go and fetch and use the Helm command to install charts locally, and Helm can output a scaffold default if we like, but I also showed you how to easily create your own. Before you progress onto the next video, make sure that you understand all of the elements within inside this one. The next video will build off the stuff that we've learnt here. So let's carry on where we left off then. And in this one, we're going to look into template calls and how we start to make our static chart more dynamic. Before we do that, let's just discuss the process that Helm goes through. So when we do a Helm install, the tiller evaluates the charts it's been sent in the templates file, and then it takes any additional values and combines them or does the calculation on them. Tiller knows where there's dynamic sections with the two curly brackets. And so it's curly bracket, your value or function, and then curly bracket. And that's really it. It's really straightforward to do, and you'll see it in action in a second. Now, with that, so a simple template call would be something like curly bracket dot release dot name space curly bracket. And all this is saying is go and fetch me the release name. Now the release name is a built-in. This uses the dot notation like namespaced objects. So to start off with, we have an object called release. And then within that release, we may have multiple objects. Maybe it's release version or release name. And so we can reference each of those by putting a dot between them. And that's really it. That's how straightforward it is to call various different things. So in this case, it's going to go get the top namespace, which is release, and then it's going to go and look inside that and get the object called name and pull that back. And then it's going to convert that into text within our Kubernetes YAML file before it submits it as a manifest to Kubernetes. If you want to test it and see what's going to be rendered, you can run a Helm install --debug space --, dry run. And then, of course, the path to your chart. This will send it to the tiller service. The tiller service will do the calculation, and then the tiller service will return to you the manifest files it's going to pass to Kubernetes. With that then, let's actually jump into our static template and start to introduce some templating calls to it and make this Ghost deployment a little bit more dynamic. So let's go into our template directory. What I'm going to do is I'm going to copy the Ghost repo from our previous video, and then I'm going to cd into it. Okay, so the first thing we're going to do is we're going to start to replace some of these static names and replace it to pull in our release name. So we're going to type in our curly bracket space dot release dot name. We're going to change our labels. So again, we're just going to replace Ghost with our release name. And we're also going to add in a couple of additional ones. And this will just help us to identify our deployments and our releases. So we're going to add in a heritage label called release service. So this is just going to call the release service. We're going to use an include statement, and this simply goes and fetches the value. Now, so this could be a series of YAMLs, but in this case it's just a single file. So we're going to fetch the temp chart, and we'll just continue through and replace each of these. So we're also going to add in release, and then of course release dot name. So I'm just going to copy this line and I'm going to paste it in below. So now the persistent volume will be release name followed by the -pv claim. Just going to add in that additional value there. We're going to take that entire section and add it into our deployment. Oh, I missed the release last time, so I'm going to add that in. And we're going to scroll that down to deployment and replace our metadata there. So we've got our name, we've got our labels. So we're going to set our selectors so they pull in the correct selectors. Going to change that label so it matches, and the release. Just need to tab those in so they're in the right location. Going to change this to release name. Then we just need to do the same for the persistent storage and the volume claim. And then finally, we're just going to change ghost. Let's head into the local volume and just make the change there as well. Okay, with everything in place, we can jump back to our command line. And we're going to do a Helm install. So we're going to do a Helm install. We're just going to do the -debug dry run and do a dot to show this. And then you can see we can scroll through. It's given an auto release name that it's called mast zebra. And then it's filled in all of our parameters for us. So we don't need to deploy this at the moment. Let's move on to our next video and start to introduce the values file. Today's video extends on the subject of our previous template calls because value files and template calls work hand in hand. Accessing several types of values in Helm charts is done through both built-in objects and our values. Some of these are directly configured by you, our values, while others are generated dynamically by Helm or taken from other parts of our chart. The three main built-in objects you'll most likely use are chart, release, and values. And it's values we're going to focus on. Values are by far one of the most important built-in objects in the template directory. It gives you access to all of the values configured in your values YAML, or we can define our own other YAML, and we can pull it in using the dot notation. As I've mentioned, the values file is in plain YAML, so it's clear and easy for us to read, and we can have more than one. We also have the option to override YAMLs, and we'll discuss how that's done later also. Now, one of the good things about using a values file is that it avoids the problem you have of passing in things like environmental variables. And if you pass these in wrong, it can actually break your deployment. Well, in a production environment, that gives us a really high level of risk. By putting our values into a predefined file, we get to test it before we go out to the production environment, and then we're much more certain of that deployment working, and hence you're less likely to bring your production application down. So it adds in this level of consistency into our interface, and we also can test it at very different points. And so all of this dramatically reduces the complexity and elements of our deployment. And as we stated in the previous one, we can have a production-values.yaml. We can have a staging.values.yaml. And we can still have the values.yaml. We can pass in as many combinations of values files as we like. We can also inspect our values file, and we can do that by running a helm inspect values to see the current configuration that is currently running. And then when we're doing our updates, we can also see whether we're resetting values to the previous ones or we're overriding them with new values. So to provide values, let's just clarify, you can either pass in the default and in the root chart called values.yaml, and you don't have to pass in any arguments. So your standard Helm install will go and look for the values.yaml file, and it has to be spelled exactly as it is on the screen. Or you can specify and supply your own YAML file with values in it. And at that point, we pass in the -f or the full -- values, and then the name or the path to the values file. There's also a couple of other things we can start to do with values. We can start to leverage values with if or range statements. So an if statement is kind of like, if this is yes, then add this text or add this into my manifest file. And the loops, let's say we've got a selection of, in this case, we've got volumes. We can loop through each one, and through each one, we'll give it a name, and then the secret, and then the secret name, and we'll pull that in. So that volumes will also have to pull in the secrets. Now, a couple of things to note here. This volumes here is an object, and within that object, it has a name and a secret name. So in your YAML, these would be sublists or sub-objects within your deployment volumes. Right, so for each volume, we would have a name and a secret name within there, and it will loop through, and it would add this volumes name secret onto your pod. So this way, you've only got these 8 lines of code, but potentially that could create as many internal volumes for your application as you need without having to repeat code. You can also use the with statement. And again, the with statement pulls in your object. So in this case, the object is deployment. And then it goes through each of the elements within the object and pulls those down. Again, we change the root when we use the with statement. Hence, this time we're just using the dot to specify that the deployment is the root. And then we're pulling in the max unavailable property. And again, we'll pull the max surge and then everything else. And that's all we're doing in there. So we specify that we're going to change to the deployment route, call those in, and then we're going to end that and go back to our standard route where we could go and call values again if we like. Again, there are several predefined values that we've already covered, but just to confirm, that's release name. So we've got the release object, name, time, namespace, service, and there's a couple of others in there as well. With that then, let's jump into our demo and take a look at values with our Ghost deployment. Okay, so now that we're in our values file, let's make our Ghost demo. Let's go and copy our old template called Ghost demo. And then we're going to CD into it, and I'll just check. So we've now got our chart and our template from our previous example. So I'm going to add a values file. And then we'll just open Vim and go to our values file. So I'm going to add a couple of elements in here, and then we'll reference that within our chart. So I'll just leave a bit of a comment. This is our default values. So to start with, we'll add replica count of 1. We'll specify our storage. So let's say 10 gig. We're going to specify our image. And so we'll do the image repo, which is Ghost. We're going to specify a pod. And then for the pods, we're going to specify the port. Need to make sure we leave a space. So that port is 2368 as it was previously. Of course, now we've got the option for dynamic. We're going to specify a name override. Now I'm going to leave this blank. But this is a handy feature that Helm looks for. So if you want to force an override, you can in these value files. And the same goes for a full name override. I'm going to leave these blank so they don't actually have any impact. Then we're going to specify a couple of values for our service. So we're going to say that this is enabled, so we can do a true statement on it, an if statement. I'm going to specify the tier. It's going to be front end. And then the type, we're going to specify as load balancer. And then, of course, we're going to specify the port, which again is 2368. So this will be the external port. Now let's go into our templates and let's start to call some of these values. So here we have our service. Let's start by modifying our port. So we're going to change this for a template call, curly bracket, space dot values dot service, and then it's port. Then we're going to change our tier, again, curly bracket dot values dot service dot tier, and then we're going to specify the type. So again, values dot service dot type. So there we specified our value calls within there, and that would run as it is. But what we're also going to do is going to wrap this in an if statement. So above the service, we're going to do curly brackets, hyphen, if dot values dot service dot enabled. We're going to close that up. And then we're just going to put the curly bracket hyphen end at the end. So now, if we were to change that enable to false, we won't add service to that template. That entire section between those will get cut out. So let's go and modify our storage. And of course, let's change our replica counts. Let's also change our image. So this is going to be .values .image .repo. Then we're going to change our ports. So this one we're going to call pod.port. And then of course we need to change the storage value to values.storage there in our local. So I've duplicated this, and now I'm going to say that we're going to have a replica count of 3. We're going to change the storage to 20 gig, and we're going to disable the service. Maybe we want it so it's a bit more secure. So with that then, let's do a Helm install. And there we can see it's pulled everything in. Now, in our default, we enabled service and we can see it there. We can also see that there was one pod and the capacity was 10 gig. So you can see it's pulled in those default values. So we can see that that's configured, we can see that the ports are correct, it's pulled everything in, and we can see that that's deployed okay. With that then, let's move on. Let's deploy our production version then. So with that, let's do a Helm install, -n for name. We'll call this one production demo. And we're going to do -f, and we're going to pass in the prod YAML. And then of course we've got our dot to say this chart. So now we're going to pull in that production YAML, which if you remember we set it as 20 gig. Now see that there's no service. It's trying to deploy 3 pods, which is what we've set, and the persistent volume capacity is set to 20. And you can see how this has changed ever so slightly. So again, just to double check, we did a kube control to get services, and you can see that the only service available is the default demo. So we've actually got 2 copies of that application running alongside each other, and it's been our release names that have allowed us to do that. So that's it for this demo then. So in this section, we looked at the values file, which is by far one of the most important built-in objects. It gives you access to configure values within the values YAML, and we can also use multiple different values. We can customize our charts a lot through this configuration, and we can also allow overrides. And there is also some predefined values: release name, release time, release namespace, and many others. This video takes an in-depth look into what I consider are the top commands, or the commands you're most likely to use within Helm. We've already covered the fundamentals command, the Helm int and the Helm install, and we've covered how Helm interacts with the tiller on your cluster. With that in mind, let's begin. So we'll start by covering the Helm create, which although extremely simple, is really great. And I brought it back up again here because it's so fundamental. Or leveraging scaffolding really helps you get up to speed with an application super quickly. We've then got the Helm fetch, which goes and downloads and unpacks a chart. We've got a Helm rollback, which is super helpful if you have a bad deployment. We've got the Helm status, and then we've got the Helm upgrade. So starting with the Helm create, this simply creates a new chart for you with the given name and builds out your de facto YAML files. And again, in case you ever forget which files that you need and are default, really this is the simplest way to go. So if you have to remember anything from this course, remember the Helm create. It will build you a pretty much working Helm chart right out of the bag. Then the Helm fetch, as it sounds, it will go and fetch you a chart, it will pull it down, and it will unpack it into the location that you specify. And again, it's useful if you want to examine, adjust, or repackage a chart. It will also run cryptographic verification against the stable chart so that you know that that chart has not been tampered with from the original specification. To run that verification, you need to run the verify flag, and that chart must have a provenance file. So to actually use that, the syntax is going to be Helm fetch any additional flags, and then the chart URL or the repo and chart name. Then we've got the Helm upgrade command, and this is where we create new releases and new versions of our application. So once you've deployed it, maybe you update the application, you change the Docker file, or you need to change the values file. It's the Helm upgrade command that we're going to use to update it. So arguably, this is probably one of the most common commands you're going to use. So with Helm upgrade, we need to specify a release and the chart that we're going to pass it. And it's not too dissimilar to our install. So the chart can again be a chart reference for a remote argument. We can also use the version of the developer flags with those if we want to use older versions. We can also specify the chart directory, similar with the dot notation. We can also specify other package charts or just a full URL. So the syntax for that is going to be Helm upgrade release chart and flags. Don't worry if you're not remembering all of these. We will go through it in a demo at the end. Our Helm status shows the release status of a deployment. So it's going to show you the last deployment time, the Kubernetes namespace, the release state can be unknown, deployed, deleted, suspended, failed, or deleting. Now, it will show you deleted deployments. If you don't want any information stored about deleted deployments, when you're deleting, you have to use the purge command. It will also show you a list of resources that are attached to those releases. And it will also send back any additional notes that we've set up in the charts. Finally then, we've got our rollback. And as I've said, if you have a bad deployment or you deploy it and something didn't quite go as expected, you can roll back to the previous version or even an older version, and if you need. And again, it's really straightforward. So the syntax for this is going to be Helm rollbacks, any additional flags that you want, the release name, and then the revision number that you want to roll back to. If you're not sure of the revision number, you can use the Helm history release name to get a full list of all of our revisions. With that then, let's jump over and we'll go through a demo of each of these commands. Let's start with the Helm create, which we've already seen before, but I'll do it again quickly. So Helm create. Again, if you want to check anything, you can always use the H command here, which is what I've quickly done just to demonstrate it. So let's do a Helm create and then call it quick-demo. That will give us a new directory, quick demo. We can cd into there and we can see all of our files that are inside it. Again, we've got our charts, that's where you'll save your charts. We've got a load of YAMLs already in place. We then got our charts and you can see it's automatically filled those out for us. And then we've got a default values file. It's definitely worth taking a quick look at this and understanding how they recommend filling everything out. Let's do a Helm fetch -d, and we're going to specify that this is the location we're going to extract it. And we're going to fetch stable Kibana. So that has downloaded our tar. And we can see that with the ls command that we've run. This time we're going to add in the flag to untar that file. And now we can see that we've got the folder and we can go into Kibana and then we can go and see our YAMLs and all of our additional files within there if we wanted to. So there we can see our deployments for Kibana and how they filled it out. And you can see it's relatively standard setups and stuff that you will have seen and be used to already. Okay. Before we carry on, we're going to need to install a chart. So I'm going to install helm-n Kibana demo. Just press dot. And there we can see it's installed Kibana for me. So if we run a Helm status on that Kibana demo, there's a new command, Helm list. I called it Kibana demo. Sorry, not Kibana. That will output that additional information again, and you can see we've got our notes and everything else at the bottom. Let's do a Helm history for Kibana demo. And so we can see our revisions. And of course, we should only see one at the moment. So I'm just going to change the replica count here to 3. I'm going to save that. Just want a Helm upgrade Kibana-demo. And then it's just called this chart. And of course that will pull in those defaults. Of the history, we can now see we've got our desired states. With that, let's run a Helm history. We should now see 2 versions. There we go, version 1 and version 2. And so we can run a Helm rollback. Kibana-demo. And then we're going to specify the version. So of course we're going to do version 1. That will roll that back to version 1. And if we do a Helm history again, we should see a 3rd revision, and that revision in the description should say that it's been rolled back to version 1. So in this video, we looked at Helm create, Helm fetch, Helm rollback, Helm status, and Helm upgrade. I hope you find those commands helpful, and I hope you look forward to using Helm in a production environment.